Hello and good morning everyone guys. I welcome you once again to this wonderful channel. Good morning everyone guys. I welcome you once again to this wonderful channel. Good morning everyone guys. I welcome you once again just to this wonderful channel. Moment. I once again welcome you all to this wonderful channel by Unacademy NEET English. I believe you all are doing great and having a good time. Well, my name is Kar Khurshid Alam and you can also call me KK Sir. Before we move ahead, I want quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats quickly. Let me know in the chats if I am audible and visible to each and every one there. Let me know in the chats if I am audible and visible to each and every one there. Okay, I believe we are live now and super excited for today's session. I was expected, this session was expected yesterday. But unfortunately, I was down with fever and body ache. I still have fever and ache, but knowing your time is too precious, so couldn't reschedule today's session further. So let me tell you that today's session is going to be a game-changing session because we are covering entire class 11th organic chemistry in one shot. NEET 2026 is getting very closer. So stay fully focused. This marathon is all about concepts, clarity, and confidence. So this session is very important. So be with me till end of this session. I would want you all guys to be with me till end of this session. And I would want you all guys to mark the attendance by smashing the like button and do share the stream with everyone around. So let me know in the chats, how is the Josh for today's session? Should we start today's session? Let me know quickly in the chats, how is the Josh? Let me know quickly in the chats, how is the Josh? Come on, let me know quickly. Let me know quickly. Should we start today's session? Should we start today's session? Because today's session is very important as we are going to cover entire class 11th organic chemistry in this. Obviously, it will be around 10 to 12 hours session. It will be a mega marathon. Okay. Yes, I will provide notes of this session in Telegram of Unacademy NEET English. I'm fine, but having a little fever and aches as well. Yes, I will teach GOC, I will teach Isomerism, I will teach nomenclature, I will teach hydrocarbon, I will try to teach each and everything. So don't worry at all. We will try to solve questions, we will try to solve PYQs as well in today's session. Is everything clear? Is everything clear? Am I audible and visible to each and every one? Duration will be, it's a mega marathon, so 10 to 12 hours, obviously. And there will be another session of me and Wasim sir on Saturday. There we will complete 12th chemistry as well. Okay. Okay. Without wasting time, let's get going. First of all, we will simply start with nomenclature, IUPAC nomenclature. After that, we will discuss GOC. After that, we will discuss isomerism. And at the end, we will discuss hydrocarbons. So, there are many slides. So, don't worry about that. Be with me till end of the session, because if you have not studied yet in organic chemistry, this session will be very, very, very much helpful to you all. This session will be very much helpful to you all. Give me a second. Give me a second. Give me a second. Okay. So, let's begin our today's session. And today's session is complete class 11th organic chemistry. You know that. First of all, IUPAC nomenclature. But before doing this, you must know few things as per IUPAC naming is concerned. First is you must know secondary prefix. And remember, this secondary prefix gives us information about substituents present in the parent chain. This gives us information about the substituents. And primary prefix gives us information whether the compound is cyclic or acyclic. If compound is cyclic, we have to write down cyclo. And if it is acyclic or open structure, then primary prefix is absent at that time. Word root gives us information about number of carbon atoms in a parent chain. Gives us information about number of carbon atoms in a parent chain. After that, primary suffix gives us information about whether the compound is saturated or unsaturated. If it is saturated, we have to write down ane. If it is having double bond, then ene. If it is having triple bond, then ine. But if it is having more than one double bond, then it's diene. Say for example, 2 double bonds diene, 3 double bonds triene, similarly diene, triene. Secondary suffix gives us information about functional groups. It gives us information about functional groups. So this is the systematic way with the help of which we will write down IUPAC nomenclature. After that, you must know the priority. First of all, principal functional group got priority. After that, multiple bonds, then number of carbon atoms, then maximum number of substituents, then lowest locant, then alphabetical order. What is this? I will show each and every one in different examples. Now, after that, there are few functional groups which will act as, when they act as a principal functional group, main functional group. When carboxylic acid acts as a main functional group, we have to write down secondary suffix for that as oic acid. Similarly, sulfonic acid, for sulfonic acid, it's sulfonic acid. For acid anhydrides, it's oic anhydride. For esters, it's OH at the end. Then for acid chlorides, it's OIL chloride. For acid amide, it's amide. For cyanide, it's nitrile. For isocyanide, it's isonitrile. For aldehyde, it's al. For ketone, it's on. For alcohol, it's OL, all. For thioalcohol, it is thiol. And for amine, it's amine. Similarly, if functional groups act as secondary functional groups, that means substituents, at that time we have to write down prefix for them. For example, carboxylic acid acts as a secondary functional group. At that time, its simply prefix is carboxy. For sulfonic acid, it's sulfo. For ester, it's alkoxycarbonyl or alkanoyl carbonyl. Alkanyl oxy, or alkanyl oxy. Similarly, for acid chloride, it's chlorocarbonyl. For acid amide, it's carbamyl. For cyanide, it's cyano. For isocyanide, we write isocyano as prefix. Similarly, for aldehyde, it can be aldo, or we can simply write down oxo as well. Or sometimes we will write formyl. When aldo, when formyl, I will show that in different examples. Now, for ketone, you write down keto or oxo. For alcohol, hydroxy. For thiol, it's mercapto. And for amine, it's amino. Then, there are few, functional groups. When these are attached to an alicyclic compound or a cyclic ring, at that time, we consider them as the functional groups. That's why we write special suffix for them. But we never, include those carbon of the functional group in the parent chain. At that time, carboxylic acid is known as carboxylic acid. ester as carboxylate, acid chloride as carbonyl chloride, acid amide as carboxamide, cyanide as carbonitrile, and aldehyde as carbaldehyde. Now, after that, we will be having few, IUPAC naming of benzene derivatives. First, we will complete this, and after that, we will, go without, aromatic compounds. Now, have a look. There are few rules. Rule number 1 is, if organic compound is having one functional group, then sometimes their common name is retained in IUPAC. That means their common name as well as the IUPAC name, they are same. That means common name is very important for them. For example, if we are having a benzene, attached to that is OH, then we will simply call that as phenol. We know that. Similarly, this is known as anisole. This is known as anisole. This is known as benzaldehyde when CHO group is attached to benzene ring or benzene is attached to CHO. Remember these. This is known as acetophenone. So these are basically the common names which are retained in IUPAC as well. This is known as benzoic acid. Benzoic acid. This is an anhydride functional group. Anhydrides are obtained from acids by removing water. That means intermolecular dehydration. After intermolecular dehydration of acids, we get anhydride. So this is benzoic anhydride because it's obtained from 2 molecules of benzoic acid. So benzoic, remove acid, and after that add anhydride. So this is benzoic anhydride. Similarly, this is known as aniline. You have to remember these compounds. This is known as benzamide because these are basically their common names but are retained in IUPAC nomenclature. Now, this is known as benzoyl chloride. This is known as benzene sulfonic acid. Then this is known as benzonitrile. And this one is known as this is ester. In case of ester, first of all, you have to write down, when ester acts as a functional group, then you have to write down first alkyl part of ester, which is attached to O. That means this alkyl. So this is known as methyl. After that, this is known as benzoate. So this is methyl benzoate. So after that, we will be having another next rule. If more than one functional groups are present, then numbering is done according to IUPAC. That means numbering is done according to IUPAC and name is given according to IUPAC. Say for example, we are having benzene, and to this benzene, we will be having 2 OH groups at 1 and 2 positions. So this is known as benzene 1,2-diol. Then this is what we call main functional group, principal functional group, and this acts as a substituent. When OH acts as a substituent, it's hydroxy. So we will simply say this is 2-hydroxybenzaldehyde. 2-hydroxybenzaldehyde. Commonly known as salicylaldehyde, a very, very important name. Now, this is 2-hydroxybenzoic acid, commonly known as salicylic acid. 2-hydroxybenzoic acid. After that, this is known as 2-amino-benzoic acid, commonly known as anthranylic acid. This is benzene, and then 1,2-dicarboxylic acid. Benzene 1,2-dicarboxylic acid. Now, these 2 carbons are not included within the chain. When COH is not included within the chain but acts as a functional group, then carboxylic acid. So this is known as benzene 1,2-dicarboxylic acid. Obviously, this is known as benzene 1,3-disulfonic acids. Benzene 1,3-disulfonic acid. After that, we will be having another rule, that is, if hydrocarbon is combination of both open as well as ring part, both are hydrocarbon part, then they are generally called as arenes. Have a look. Then this is methyl and this is benzene. So this is known as methyl benzene, commonly known as toluene. methyl benzene, commonly known as toluene, and that toluene is retained in IUPAC as well. So you can say toluene. This is known as ethyl benzene. That means here benzene part acts as, in these examples, benzene part acts as what we call a parent chain. This is known as ethynyl. Ethynyl, because this is ethene whose H has been removed. So this is ethynyl benzene. This is propyl benzene. This is also propyl benzene. But what is the difference between these two? Both are propyl benzene, but what is the difference? Difference is this propyl is attached at one position. I mean, say hydrogen has been removed from one position. So this is one propyl and this is 2-propyl benzene. This is also known as isopropyl benzene or cumene. After that, we will be having another, that's if organic compound is having functional group, then part having functional group is taken as main part. That means that part which is having functional group. Here, functional group is having this open structure. Open structure contains functional group. So this becomes main, I mean say parent chain. So this is our parent chain. This is the parent chain. So this is 1, this is 2. So this benzene will act here as a substituent. Whenever benzene acts as a substituent, it is simply known as phenyl. So what will be the name of this compound? This is 2-phenyl. This is 2-phenyl. And then 2 carbons are there. So ethan. You can say 1-ul or you can write down ethanol because CHO is a chain terminating functional group. Whenever it acts as a functional group, it will be always present at position number 1. Similarly, this is our parent chain. So I will number in such a way so that this functional group gets lowest number. So this is the parent chain. This parent chain is containing 3 carbons and it's a ketonic functional group. So this is basically propan 1-on. This is basically propan 1-on because first position contains, I mean say ketonic functional group. But to this propan 1-on, we will be having phenyl at one position. So this is 1-phenyl propan 1-on. After that, once again, this parent chain, this is the parent chain as this side chain contains functional group. So this is 1, this is 2, lowest number. Functional group carbon gets lowest number. So it is 2-phenyl then. At second position, substituent is phenyl. So it is 2-phenyl, then it is ethan 1-ol. 2-phenyl ethan 1-ol. What about this? This is the, I mean say, parent chain because it contains functional group CN. Cyanide, when it acts as a functional group, included in the parent chain, this is nitrile. So this is propane nitrile. This is propane nitrile or propane 1-nitrile, but it's not necessary that you will use 1 because cyanide is also, nitrile is also that, I mean say functional group. Whenever it acts as a functional group, it will be always present at position number 1. That means chain terminating functional group. So third position contains phenyl. So it is 3-phenyl. It is 3-phenyl propane nitrile. After that, this ring is having, I mean say functional group attached to this. That means this will become carbon number 1. This is carbon 2. This is 3. This is 4. 5 and 6. That means this is attached to COH. So this is known as benzene carboxylic acid, or we can simply say it as benzoic acid. And to this benzoic acid, fourth position is having ethyl. So I will write down 4-ethyl benzoic acid, or we can say it is 4-ethyl benzene 1-carboxylic acid. After that, if both parts are having functional group, then part having principal functional group is taken as main part. This is having functional group, this is having functional group, but this is principal functional group. So this is the parent chain. Now this is 1, this is 2, this is 3. So this will be our substituent. This will be our substituent. And carbon of that substituent which is attached to parent chain gets 1. So to differentiate from this one, let me write down 1 prime. Then it will be 2 prime. So obviously its name will become 2 prime hydroxyphenyl. 2 prime hydroxyphenyl. And it is present at position number 3. So let me write down the name. as this phenyl was the substituent, this is another substituent, so this becomes substituted. Substituent means complex substituent, and complex substituent is always written in parentheses. So its name will be 2-hydroxy. I will write down 2-hydroxy or 2'-hydroxy, then phenyl. And this complex substituent is present at third position of, then it is propane, then nitrile. Now here, main functional group is this one. That means this becomes parent chain. This becomes, side chain. So this is 1', this is 2', this is 3'. So this was actually propyl, and to this propyl, it's hydroxy at second position. So it is 2'-hydroxy propyl, which is present at 3 position. So I will write down 3, then it is the substituted substituent or complex substituent, which is present at third position, and its name is 2-hydroxy propyl, 2-hydroxy and then benzoic acid or benzene carboxylic acid. So benzoic acid. So this is 2'-hydroxy propyl, but at third position, and this is benzene 1-carboxylic acid or benzoic acid. Similarly, here it is COH and CN. Have a look. This is the preferential order as well. If you are having COH, carboxylic acid, as well as you will be having a cyanide. So who will got preference? This is preference order basically as well. So obviously we will get, according to preference order, COH will act as a main functional group. So this is the principal functional group. So this becomes our parent chain. So this is 1, 2, and 3. To this 3, this group becomes substituted substituent, and this is having 1', then 2', then 3', then 4'. But this 4' is having substituent. When cyanide acts as a substituent, it is cyano. This is phenyl. So this is 4-cyanophenyl. But this is present at third position. So I will write down 3, 4' or 4', then cyano, then phenyl. After that, I will write down propanoic acid. Because these are the 3 carbons. So 3 carbon means prop. All are having single bond. So ane, then oic acid. As it starts with O vowel, we have to, elide E of ane. Is this clear till now? Am I clear till now? Let me know quickly. Am I clear till now? So that we will try to solve these questions as well. Am I clear till now? Let me know quickly. Am I clear till now? Okay, thank you, King. Thank you at the rate of Asad Ali Khan. Thank you at the rate of Shafat, at the rate of Paramila. Okay, thank you everyone. Come on, let's do this one. Let's do this. First of all, you have to find out the parent chain. After that, you have to number in such a way that substituent got lowest number. That means according to lowest locant rule. So I will write down simply like this. I will number like this. It's 1, 2, 3, then this is 4, this is 5. That means this 3 and this 2, both are having substituents. So what will be the name of this compound? It is simply 2 and then 3, then dimethyl. Both are having methyl groups. And then 5 carbons are there, so it's pent, and all are having single bonds, so this is pentane. After that, this is having 2, substituents at this position, 1 at this position. We will write down numbering in such a way so that lowest locant rule will follow. So it is 2, 2, 3. If we write like this, and if we write from this side, it will become 2, 3, 3. So 2, 2, 3 will be followed. After that, it is 3-bromo. Then it is 2, 2 dichloro, and then butane. So what will be the name of this compound? I will number in such a way so that lowest locant rule will be followed. So it will be like this. So it will be 3-bromo, and after that 1, 1 dichloro, But this is having cyclic structure, so cyclo. And after that, 5 carbons are in a chain having single bond, so cyclopentane. What about this? What about this? It's having double bond. So parent chain should be that which contains maximum number of double bond. That means this is the parent chain or this is the parent chain. So I will number 1, 2, 3 and 4. That means it's having 2 ethyl. Substituent is ethyl there. So it is 2 ethyl. After that, it's having but and then 1 ene. It's having 2 ethyl but 1 ene. What about this? What about this? 1, 2, 3 and 4. This is simply buta. Why we have added a to the word root? Because after that, this suffix, primary suffix, starts with a consonant. Whenever it starts with a consonant, we have to add letter a to the word root. Okay, after that, we will number from this side, because whenever double bond and triple bond are present at equivalent position, double bond got preference over triple bond. So these are in total, this is having 6 carbons, so it's hex. After that, first we will write down ene and then ine. So it is hex 1 ene and then 3 and 5 diene. So this will be the name of the compound. So this is hex. After that, we have to write down ene first and then we have to write down triple bonds, that means ine. Because it comes with, starts with alphabetical order E and ine starts with Y. So first E and then after Y. So this is having 1, 2, 3. This is an alcohol. It's named as propan 1-ol. First, you have to think of word root, primary suffix, secondary suffix. Then before word root, primary prefix. Before that, secondary prefix. So this is known as cyclohexanol. What about this? This is the main functional group. So this comes in the chain and this will act as a substituent here. So it is 2-hydroxy. 2-hydroxy. Then we will say propan 1-oic acid or simply propanoic acid, as COH is the main functional group and it acts as a chain terminating functional group. So no need to write down 1. Is this clear? Am I clear till now? Am I clear till now? Let me know quickly. Let me know quickly. Yes, 2-hydroxypropanoic acid. 2-hydroxypropanoic acid is the right answer. Okay. After this, then we will be having this one. Now this is functional group containing carbon. So carbon containing functional group when attached to the ring is not included in the ring. Then what will be the name of this compound? It will be simply cyclohexane. Now this will act as a functional group but not included in the ring. So this is cyclohexane carboxylic acid. So this is cyclohexane carboxylic acid. What about this? This will be cyclobutane, as CHO will act here as a functional group but not included within the parent chain. So this is carbaldehyde. Carbaldehyde. So cyclobutane carbaldehyde. What about this? 1, 2, 3, 4 and 5. Have a look. We have included carbon of this CHO. But we have not included this CHO. This is outside the chain. That means when CHO is not included within the chain, use formyl. If it is not acting as a functional group, because main functional group is COH. This is not the functional group. This is not the functional group. But this is not included in the chain. So write formyl. This is included in the chain. So you can write down aldo or oxo. So what will be the name of this compound? First of all, 1, 2, 3, 4, 5. 5 carbon acid is known as pentanoic acid. It's pent, then an, then oic acid. To this pentanoic acid, we will be having at 2% formyl and at 5% aldo. So aldo starts with A and formyl starts with F. So let me write down 5 aldo, 2 formyl. 5 aldo, 2 formyl. Let me write down it clearly. 5 aldo, 2 formyl. And here it's a hyphen. Okay. So this will be the name, or you can write down 2 formyl, 5 oxo, then pentanoic acid. After that, we will be having this one. As this contains parent chain, so this functional group, main functional group, so this is the parent chain, this will act as a substituent. So at 2 position, it is cyclopentyl. So let me write down 2-cyclopentyl ethanoic acid. 2-cyclopentyl ethanoic acid. Okay. Have a look. Here, this is the main functional group. So this will act as a substituent. When it acts as a substituent, it's named as chlorocarbonyl. So let me write down numbering like this. So it is simply 4-chlorocarbonyl. 4-chlorocarbonyl. Then it's cyclohexane. And then 1-carboxylic acid. Why not oic acid? Because this COH acts as a functional group, but it is not included within the parent chain. After that, it is 1, 2, 3, and then 4. So its name will be simply 3-oxo, as this is the ketonic functional group, either keto or oxo. So 3-oxo, then you can write down butanoic acid or butanoic 1 acid. So it is simply butanoic acid or butan 1-oic acid. So am I clear? Am I clear till now? Let me know quickly. Am I clear till now? 4-chlorocarbonyl, cyclohexane, 1-carboxylic acid. Exactly, Asith. Exactly. Am I clear? Am I clear? Let me know quickly. Let me know quickly. After that, we will be having another example like this. This is the main functional group. So we will number from this. This will act as a substituent. So numbering is done in this way. So we can simply say 2-cyano because cyanide will act here as a substituent. After that, it is cyclohexane. And then it is 1-carboxylic acid. Now, what about this? 1, 2, 3, 4, because this is the main functional group. So this will act as a substituent. So it is 4-amino. NH2 acting as a substituent is amino. So 4-amino, and after that word root, but, then primary suffix an, and then oic acid. So it is butanoic acid, or you can write down butan 1-oic acid as well. So this is the main functional group amide. So what will be the name of this compound? It will be simply word root but, then an, and then amide. Butan amide or butan 1 amide. What about this? This is an ester. When ester acts as a functional group, you have to number from this. But first of all, we have to write down, in case of ester, when ester acts as a functional group, we have to write down that alkyl which is attached to oxygen. So I will write down methyl first. But this is not the substituent. This is the part of, I mean to say, ester attached to O. Now, first of all, this methyl, after that, 4 carbons, so butan, but, then single bonds, then N, and then at first position, it is ester, then OH. So you will write down like this, methyl butan OH or butan 1 OH. Both are correct. So this is the main functional group. But this is carbon containing functional group. When carbon containing functional group is attached to ring, it is not, included within the parent chain. So I will write down cyclopentane, and then this is acting as a functional group but not included in the parent chain. Then it is carboxamide. So have a look. Here CONH2 carboxamide, but here CONH2 amide, because this is included within the parent chain, this is not included within the parent chain. Now, what will be the name of this compound? Have a look. This is methyl. First, we have to write down this because this is an ester. After that, it is cyclobutane, and then this one. It's not included at this time within the parent chain. So this is carboxylate. So have a look. Here we write for ester carboxylate, but here we write OH. When OH, when it acts as a functional group and is included in the parent chain. When carboxylate, when it acts as a functional group but not included within the parent chain. I hope this is clear till now. Let me know quickly. Is this clear? Let me know quickly, is this clear? Let me know quickly, is this clear till now? Let me know quickly, is this clear till now? Okay, 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 that's great. That is great. After that, we will be having another compound, a very, very important, compound. Have a look. This is having COH and COR. Whenever COH and COR is there, COH will act as a principal functional group. So this is a chain terminating functional group. So this will act as a substituent. But when your ester is having a substituent, have a look, have a look, have a look. Here, once again, ester is acting as a substituent. This is RCO. This is also what we call ROCO. That means this is ester part. This is ester part. This is ester part. Whenever functional group is like this. But when C double bond O is attached to parent chain, acting as a substituent. This is carbonyl. And to this carbonyl, this alkoxy or methoxy is attached. So we will write down methoxycarbonyl here. That means alkoxycarbonyl here. But here it is oxygen, which is basically attached to parent chain, and to that oxygen we will be having carbonyl. So this is simply what we call alkanoyl oxy, but this is alkoxycarbonyl. So what will be the name of this? This is 4, then it is 4-methoxycarbonyl. So whenever C double bond OR is there, C double bond OR, C double bond OO, and to this R is attached like this, then here it is this alkoxy part written first and then carbonyl. Now after that it is butanoic acid or butan-1-oic acid. Butanoic acid or butan-1-oic acid. Here it's once again butanoic acid, but in this case, here it was alkoxy first and then carbonyl first. Here it is alkanoyl first and then oxy. So this is having 2 carbons, so it is 4-ethanoyl oxy. 4-ethanoyl oxy. Then butanoic acid or butan-1-oic acid. Have a look. If you are having carbon containing functional groups, 3 or more than that, attached directly to the parent chain. This is attached directly to this carbon chain. So we will not, include such functional groups at that time. So we will write down this is propane. And to this propane, these carboxylic acids are present at 1, 2, and 3 position. But all are functional groups but not included within the parent chain. So this is 1, 2, 3 tricarboxylic acid. 1, 2, 3 tricarboxylic acid. What about this then? What about this? Once again, a carbon containing functional group, 3 or more than that. So this is once again propane. And to this propane, it's 1, 2, 3. But these cyanides, when acting as a functional group but not included within the parent chain, special suffix will be used as carbonitrile. So 1, 2, 3 tricarbonitrile. 1, 2, 3 tricarbonitrile. Now here, this cyanide is directly attached, but this cyanide is not directly attached to this chain. Have a look. This is the chain. This is the chain. Have a look. Have a look. Have a look. This is the chain. To this chain, cyanide and cyanide directly attached, but this is not directly attached. So when you are having 3 or more than 3, carbon containing functional groups, in which suppose we will talk about 3 functional groups, carbon containing functional groups, among 2 are directly attached and 1 is not. When 1 is not directly attached, that is treated as the substituent and will not include within the parent chain, and which are directly attached, they are considered as functional groups and they are included within the parent chain. So numbering will be done like this: 1, 2, 3, then this is 4, this is 5, this is 6. So this is hexane, this is hexane. In this hexane, 1 and 6 position contains 2 functional groups, and this is known as dinitrile, because whenever cyanide acts as a functional group and included within the parent chain, it's known as nitrile. Now this will act as a substituent. So this substituent is cyanomethyl. So I will write down 3-cyanomethyl, 3-cyanomethyl, and after that I will write down hexane 1,6-dinitrile. Similarly, I will write down this as this becomes the substituent. So I will write down 3-formyl, because whenever CHO acts as a substituent, it will be 3-formyl methyl. 3-formyl methyl. This was 3-cyanomethyl. This is 3-formyl methyl. After that it is hexane, and then 1,6-diol, because CHO here, these two CHO groups here are included in the parent chain, that's why ol. Now, let me know quickly, am I clear till now? Let me know in the chats quickly, am I clear till now? Let me know quickly. Let me know quickly, am I clear till now? Come on, today you have to support me a lot as I'm down with fever and I am having body aches as well, but I'm here only for you guys because I know your time is very, very, very precious. So you have to be with me, you have to support me till end. Now, we cannot complete session as soon as it is possible, my dear Bhavani, because this session is basically a long marathon. It's a mega marathon. It's 10 to 12 hour session, my dear lovely student. Okay. Now, after this, we will be having few, say for example, alkanes like this. This is the complex substituted alkane. Now, how will we number? First of all, we will find out a parent chain like this. This is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, and 10. That means, that clearly indicates this will act as a substituent. And carbon of that substituent which is attached directly to parent chain is 1. To differentiate this one from this one, let me write down 1 prime, 2 prime, 3 prime, 4 prime. That means it is butyl. And to this butyl, there is another substituent, ethyl. So what will be the name of this substituent? It is 2-ethyl butyl. So the name of this substituent is 2-ethyl butyl. Okay. What about this and this? These are further two substituents. This is methyl, this is methyl. That means their name is dimethyl. But this di is not included in the alphabetical order. So it starts with M, it starts with E. So first we will write down this. After that we will write down this. So I will write down at 5 position. There is a complex substituent, substituted substituent, whose name is 2 prime ethyl butyl. Whose name is 2 prime ethyl butyl. After that, we will be having at 3rd position, we will be having dimethyl. And after that, we will be having 10 carbons. So it is dec, and all these carbons are having single bonds. So it is decane. So it is 5, 2 prime ethyl butyl, and after that 3 dimethyl decane. First, we have write down this because it starts with E, it starts with M because di is not included within the alphabetical order. So I hope this is clear. I hope this is clear. After that, we will be having another like this. First of all, we will write down the numbering of parent chain like this. Numbering is done in such a way so that lowest locant rule will be followed. So this will act here as a, say complex substituent. But let me write down that carbon as 1 to which substituent that carbon to which that carbon which is attached to parent chain of the substituent is given 1. So it is 1 prime, 2 prime, 3 prime. That means it is basically propyl, and to this propyl there is another substituent. So its name will be 1 prime methyl propyl. So its name will be 1 prime methyl propyl. Or you can call this as, this is also known as sec butyl. Commonly we can call this as sec butyl. Okay. What about this? This is once again a substituent, and this is 1 prime, this is 2 prime. So this is carbon, this is the substituent having 2 carbons basically, and to this is another substituent. So this is 1 prime, this is 1 prime methyl ethyl. It's also known as isopropyl. Also known as isopropyl commonly. You can use both these names. So the name of this compound is, this is 1 methyl 1 prime methyl, but this is ethyl, starts with E. This is propyl, starts with P. So first of all, first point of difference is E and P. So I will give preference to E. So I will write down 4. At 4 position, we will be having 1 prime methyl ethyl. Methyl ethyl. And after that, at 5 position, we will be having 1 prime methyl propyl. And then we will be having 10 carbons, so dec, and all these carbons have single bonds, so decane. Or you can write down another name like this. Have a look. This is sec butyl. Sec and tert and N, or means a normal, they are not included within the alphabetical order, but iso and neo are included. So it starts with I, it starts with B. So it starts with B, it starts with I. So B got preference as per alphabetical order is concerned. So its another name is 5. At 5 position, we will be having sec butyl. At 5 position, we will be having sec butyl because it starts with B. That's why I will write down this first. After that, we will be having 4 isopropyl. 4 isopropyl and then decane. This is another name for this compound. After that, if we are having a structure like this, so let me write down a numbering. So this is 4, 5, 6, 7, 8, 5, 6, 7, 8. So we can number in any direction. So this is our one substituent, and this is another substituent. But if I write down 1, 2, 3, 4, 5, 6, 7, 8, 9, have a look, 1, 2, 3, 4, 5, 6, 7, 8, 9, then number of carbons are maximum over here. So that's why this is not the correct numbering. That's why we have to, say first of all, we have to find out the longest continuous chain of carbon as per alkanes is concerned. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. But 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So I will write down 1, 2, 3, 4, 5, 6, 7, 8, and 9. That means this becomes what we call a substituent. But this is 1 prime, this is 2 prime, this is 3 prime. So this is having, propyl substituent, and to this propyl we will be having 2 methyl at second position. So its name will be 2 prime, comma 2 prime. Then it is dimethyl propyl. Dimethyl propyl. This is the only substituent of the parent chain, and it is attached to 5th carbon. So it is 5. Then it is 2 prime, comma 2 prime dimethyl, then it's propyl. After that, we will be having the name like this. It's nonane. I hope everything is clear till now. If you start from now at the rate of Johann Natham, you can easily score 500, but the question is, you have to, start. Okay. Am I clear till now? Let me know quickly, am I clear till now? Quickly. Quickly. So let us start our another topic, and another topic is general organic chemistry. Simply we call that as GOC. Let's move to GOC. Okay. Now have a look. In GOC, there are electronic displacement effects which are very, very, very important. And we know we will be having 2 electronic displacement effects. One is permanent, another is temporary. And in permanent, its inductive effect, its resonance effect, also known as mesomeric effect in your class. After that, we will be having hyperconjugation effect. We will be having these three, and these three are very, very important as GOC is concerned. After that, we will be having temporary effect. In temporary effect, we will be having electromeric effect and inductomeric effect. But these two are important for reaction portions, but as per GOC is concerned, these three are very, very important. And remember, among these three, it is resonance which is stronger effect. After that, hyperconjugation. After that, it's inductive effect. But except halogens. In case of halogen, inductive effect is considered stronger effect as compared to resonance. So let us take these one by one so that we can complete, say whole GOC. Have a look. Have a look. First of all, it's inductive effect. What is inductive effect actually? Inductive effect is actually displacement of sigma electrons, or we can simply say whenever displacement of sigma electron takes place, that means polarization occurs. So displacement of sigma electron in any sigma bond or polarization in any sigma bond, but due to displacement of sigma electron in its adjacent bond, or we can say polarization of sigma bond of or any sigma bond due to polarization of its adjacent sigma bond. So remember, polarization of a sigma bond caused by polarization of adjacent sigma bond, or you can simply say displacement of sigma electron in one sigma bond, but caused due to displacement of sigma electron in its adjacent sigma bond. So what is that? Have a look. Have a look. If we talk about a carbon chain, all these carbons are having similar electronegativities. That means there will be no displacement of sigma electron at all. But whenever, say for example, electron withdrawing group like Cl is attached to this carbon chain, which was first, say non-polar, because there was no electronic displacement effect, or suppose we will attach a metal like MgBr. Mg will act as a metal. So whenever metal or electron donating group is attached to carbon chain or electron withdrawing group is attached to carbon chain, what will happen? Have a look, my dear lovely students. As there is electronegativity difference between carbon and chlorine, so chlorine is more electronegative, so it will attract its electrons, sigma bonded electrons towards itself, more towards itself as compared to carbon. So this will acquire a partial negative charge and it will acquire a partial positive charge. So what will happen? What will happen in this sigma bond? If this bond is bond number 1, what will happen? Here, displacement of sigma electron takes place or polarization takes place. So, have a look. If carbon and carbon both are neutral species, then no carbon will attract electron towards itself because both are having same electronegativity. But here, this carbon will acquire a partial positive charge. Now, this will attract electron towards itself. That means in this bond, in bond number 2, displacement of sigma electron has been taken place only because this carbon acquires a partial positive charge, and this acquires partial positive charge because of Cl. That means the polarity which was basically, or polarization which was taking place in this sigma bond, due to this polarization occurs in another sigma bond. Now let me know quickly, is this clear? So polarization in sigma bond 2 occurs due to polarization of 1. If there is no Cl, if there is no polarization in this bond, there will be no polarization in this bond. But here polarization takes place or displacement of electron takes place because of polarization of this bond. So this bond induces polarity in this. That's why this effect is known as induced effect, or what we call inductive effect. This is also known as transmission effect. Similarly, this positive charge will withdraw electron towards itself, and in this third bond polarization takes place or displacement takes place due to this second or due to first bond. So polarization in any sigma bond due to polarization or caused by this bond, say adjacent bond, is known as inductive effect. Similarly, what will happen over here? This Mg will donate electron and it will acquire a partial positive charge, this will acquire a partial negative. But before that, when this and this both are neutral, there will be no polarization in this bond. But once it becomes partial negative, so once polarity is in one bond, now this partial negative carbon will repel this electrons. That means they will repel, that means donate electron towards this, and it will acquire a partial negative charge. So now polarity will acquire in second, it acquires in second only due to polarization in its adjacent carbon and magnesium bond. That means polarity in this bond occurs due to polarization of this bond. That's why what is known as inductive effect? It is polarization of any sigma bond caused by polarization of its adjacent sigma bond. Similarly, it will donate electrons. That means there will be polarity or polarization in bond number 3 as well. But remember, as distance increases from electron donating or electron withdrawing group, as distance increases, inductive effect decreases. That means inductive effect and what we call distance, they are what we call inversely related. That means inductive effect is distance dependent and inductive effect is inversely related to what we call distance. So more the distance between electron withdrawing and carbon or electron donating in carbon, there will be lesser inductive effect. That's why beyond 3 carbons, we generally do not take inductive effect. Now, let me know in the chats, am I clear till now? Let me know in the chats, am I clear till now? Let me know quickly. Let me know quickly. Let me know in the chats, am I clear till now? Let me know chats, let me know in the chats, am I clear? Am I clear? Is definition of inductive effect clear to you? Okay, that's great. That is great. That is great. Okay, have a look. Have a look. After this, there are a few points. There are a few points. Point number 1 is inductive effect is a permanent effect. It's a permanent effect. Point number 2, it involves displacement of sigma electrons. Sigma electrons only. Number 3, you must remember that it is distance dependent. It is distance dependent effect. And remember, we can write down inductive effect is inversely proportional to the distance. So more the distance, lesser will be the inductive effect. And point number 4, hydrogen is taken as standard reference over here. Hydrogen is taken as the standard reference. As standard reference. And its inductive effect is assumed, inductive effect of hydrogen is assumed to be 0. Remember this as well. After that, we will be having types of inductive effect according to Ingold convention. Ingold, according to this chemist, we have 2 types of, inductive effect. One is minus I effect, that means electron withdrawing inductive effect. Another is plus I effect, that means electron donating inductive effect. Remember, when any atom or group is capable of withdrawing sigma electrons more strongly than hydrogen, we call such atoms or groups as minus I groups. And similarly, when any atom or group is capable of donating sigma electrons more strongly, we call such groups as plus I groups. But remember, minus I and plus I are basically relative terms. Now, there are a few groups which I have written over here. There are a few groups. You have to remember these groups. You can remember these groups with the help of this trick that no Ferrari, no Rolls Royce, so rich, no home, no soap can stop carbon, Father Carl Braun in office collecting orders, chopped sushi sir, and oh, triple new phenyl double. After that, these are few electron donating groups, that means plus I series. So there is a trick, can no one cook, try some extra meals, it's a tasty dinner. After that, we will be having applications of inductive effect. First application is stability of positively charged species. Remember, it is directly proportional to plus I and it is inversely proportional to minus I. That means plus I groups basically attached to the positively charged species stabilizes the stability of positive charge, and minus I groups attached to positively charged species simply destabilize the positive charge species. Okay, now first you have to remember this. Second you have to remember is this one. You have to first of all check whether plus I group is there. After that, that group which neither shows plus I nor minus I, so we can call that neutral, and after that minus I. But here plus I should be strong first and then weak one, and among minus I, first write weak and after that strong. Now, what is this? How we can solve a question with the help of this? Have a look. Have a look. Suppose we will be having a question like this. Compare stability. Compare stability. Suppose we will be having question like this. First question is like this. We will be having CH3 with a positive charge, and then we will be having CH3CH2 with a positive charge. Then we will be having CH3, then CH, then CH3 having a positive charge. Suppose we will be having CH3, CH3, CH3 having a positive charge. Now, please try to understand. Have a look. This is very, very, very easy. Now, here carbon having a positive charge, that means positive charge species carbocation is attached to nitrogen, is attached to hydrogen. Hydrogen neither shows plus I nor shows minus I, because hydrogen is taken as standard reference and its inductive effect is considered 0. That means it neither donates electrons nor withdraws electrons. Now, we will simply say here that it is neutral which is attached to carbon. Here, carbon having a positive charge is attached to methyl, and methyl shows plus I effect. Similarly, it is methyl plus I one group and plus I two groups. And remember, inductive effect is additive effect. That means more the plus I groups, more stronger inductive effect is present. More minus I groups, more stronger minus I effect is present. So similarly, here it is plus I and plus I. 3 plus I groups are present over here. So we have to find out, first of all, plus I. But plus I groups are 3. Now, we will write down stronger one first. So, more plus I means more stronger plus I groups are attached to a positively charged species. So, stability order will be simply 4. After that, it will be 3. After that, it will be 2. So, first plus I. Then neutral. Neutral is this one. So, this will be the answer of stability simply. So, this will be the stability order. After that, suppose we will be having, like this. Suppose we will be having like this. We will be having CH3 having a positive charge. Then second is ClCH2, CH2 positive. Third is FCH2, CH2 positive. Then fourth one is, say for example, NO2, CH2, CH2 positive. Let me write down another option. Let us suppose fifth option is like CH3, CH2, CH2 positive. Sixth option, say for example, is like this. CH3, CH3, CH2, CH2 positive. Now have a look. Here I will write down here. This is hydrogens only which are attached to carbocation, so neutral. Because of this Cl, it becomes minus I group. And because of this F, it is minus I group. Because of this NO2, it's minus I group. Because of this CH3, CH2, I mean say alkyl, it is plus I. This is also plus I group. And remember, you must remember this, that in case of alkyl groups, plus I order is directly proportional to branching. So more branching, more plus I power. But if branching is same, at that time plus I power is directly proportional to number of carbon atoms. Here, have a look. And these are minus I, these two are plus I. First, we have to write down plus I. But which plus I? Plus I. We have to write down stronger plus I first. So this is having branching, so stronger plus I. So I will write down 6 first. And then I will write down 5 first. After plus I groups, I have to write down neutral. Neutral is this first one. So I will write down first. After that, we will write down minus I. But minus I, weak first. After that, strong. We know minus I power of NO2 is more than F is more than Cl. That means we have to write down weaker first. So we will write down weaker. That means Cl first, then F first, and then NO2 first. So this will be the order of this question simply. I hope this is clear till now. Let me know in the chats quickly, am I clear till now? Let me know in the chats, am I clear till now? 6, 5, 1, 2, 3, 4 is the right answer at the rate of Sharon. Come on, my dear lovely students. Yeah, how can I forget KK? I can never forget KK. Okay. Now, after this, we have stability of negatively charged species. Remember, when negative charge is there, minus I groups attached to negative charges stabilizes the negative charged species and plus I destabilizes them. That's why it's directly proportional to minus I and inversely proportional to plus I. Remember. You can also write down like this, first minus I, then neutral, and then plus I. But here, strong to weak, and then weak to strong. Now, have a look. Suppose we are having a question like this. Compare stability. Now, give me a second. Okay, compare stability. Say for example, first question is like this. You will be having CH3 having a negative charge. Then you will be having CH3, CH2 having negative charge. Then you will be having CH3, CH3 having negative charge. Then you will be having CH3, then CH3, CH3 having negative charge. Very simple. Okay. Now we know this is neutral. Here this CH3 is plus I group attached to negatively charged species. Here 2 plus I groups are attached. And here 3 plus I groups are attached. Plus I and plus I. 3 plus I groups are attached. Now, what will happen over here? So, we have to write down first minus I, but no minus I group is there. After that neutral. So, this is neutral, so I will write down 1. After that plus I, but weaker one first. So, this is weaker, so I will write down 2, then 3, then 4. So, this will be the stability order. Very easy. After that, if you are having CH3 having a negative charge, then you will be having, say for example, CH3, CH2 having negative charge. Then you will be having Cl, CH2, CH2 having negative charge. Then you will be having, say for example, F, CH2, CH2 having negative charge. And let us suppose you will be having CH3, CH3, and then CH2 having a negative charge. Then what will happen over here? This is neutral species. This is having plus I group. This is having minus I group. This is having minus I group. This is having plus I group. First, we have to write down minus I. But which minus I? Stronger or weaker? Stronger one first. So, F and Cl. Among F and Cl, I will write down 4 and then 3. Then I will write down neutral. That means 1. After that, I have to write down plus I, but weaker one. This is weaker plus I. That's having branch. More branches, stronger will be the plus I. So, I will write down 2. And after that, I will write down 5. Now, is this clear? Is this clear till now? Let me know quickly. Am I clear till now? Let me know quickly. Am I clear till now? Let me know quickly. Am I clear till now? Let me know in the chats. Am I clear till now? Quickly. Let me know. Let me know in the chats. Am I clear till now? Thank you at the rate of Arjun. Thank you. Okay, thank you everyone. Thank you everyone. It's clear. Thank you everyone. It's clear. After that, my dear students, we will be having acidic strength. And for acidic strength, you have to remember few formulas. Say for example, first of all, acidic strength is directly proportional to stability of its conjugate base. This is the first formula you have to remember. After that, you have to remember few more formulas like strength of acid is directly proportional to what we call minus I and inversely proportional to plus I. That means whenever minus I groups are attached to an acid, it increases its acidic character, and when plus I groups are attached to, this acid, then it decreases its acidic strength. After that, strength of acid is directly proportional to Ka and it is inversely proportional to pKa. it is directly proportional to pKb and inversely proportional to Kb. After that, strength of acid is directly proportional to H positive ion concentration and it is inversely proportional to pH. Similarly, strength of acid is directly proportional to pOH and inversely proportional to OH minus concentration. And you have to remember also that for strength of acid, we have to find out minus I first and then neutral and then plus I if we are basically explaining acidic strength on the basis of inductive effect. Now, this is minus I, strong to weak, and after this we have to write down plus I from weak to strong. So this is another factor. So this is 1, these are 2, 3, so these are further 2, 5, so these are further 2, hence 7, further 2, 9, further 2, 11, and this is 12. Now, after this, compare acidic strength. Compare acidic strength. Compare acidic strength. Suppose you are having first question like this. You are having HCOOH, you are having CH3COOH, and you will be having third option ClCH2COOH. Now have a look. This hydrogen is attached to COH, so this is neutral. This is plus I group which is attached to COH. This is minus I group which is attached to COH. Which will increase acidic character? Minus I. So I will write down simply 3, then 2, then 1. So this is the acidic character. This is the acidic strength order. So remember, it's having more Ka in the same order. pKb value will be in the same order. H positive will be in the same order. pOH will be in the same order. And in inverse, I mean, say if this order is reversed, then pKa order will be reverse of this, Kb will be reverse of this as this is inversely related, pH will be reverse of this, OH minus concentration will be reverse of this. Similarly, my dear lovely students, if you are having structure like this, Cl, CH2, 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 COH, and you will be having Cl, you will be having structure like this, CH3, CH3, CH, Cl, then CH2, then COH. Have a look. Here this is minus I group, this is also minus I group. But from acid, in between Cl and COH, there are 3 carbons. Here, there are only 2 carbons. That means this Cl is closer, this Cl is, I mean, say far from this. So, you have to check first of all distance. Distance here is more, so is less. Here, hence, distance less, inductive effect will be more. So, this is stronger minus I as compared to this. So, I will write down 2 greater than 1. So, this will be the acidic order. Similarly, if you are having acid like this, say for example, you are having COH in this ring, then here it will be I and I which is attached to this. After that, it will be, say for example, COH once again, then it will be Br which is attached to this. Then third one is like this, COOH, and then it is Cl. Then fourth is like this, COOH, then it is F. So first of all, check out these groups. These are all minus I groups, but in case of minus I, you have to remember this rule, and this rule is DNP. For minus I and plus I, you can use this rule, DNP, distance, number and power. First of all, give preference to distance. These two are closer to COH, these two are, I mean, say farther from them. So more closer minus I groups, more stronger will be the acidic character. So these two will be stronger acids, but distance is same of these groups, but here number is more. So number. So I will write down 1 first and then 2, then 3, and afterwards 4. Why? Because distance is got preference over number as compared to power. So first distance. Distance is same. When distance cannot differentiate your answer, then number. Here number is 2, number is 1. So number. After that, number is same, but distance. Distance is, say first these two, then this one, then this one. Okay, I hope this is clear. After that, if you are having a structure like this, you will be having COH, and then you will be having COH, and then it's CH3. Then you will be having COH, and then F, and after that you will be having COOH, and then CH3. Have a look. This, okay, CH3, this is Cl. This is plus I group. This is what we call minus I group. This is minus I group. But to this para position, there is hydrogen. So let me write down that as neutral. So first of all, we have to write down minus I. But which one minus I? Stronger minus I. Distance is same. Number is same. So check out power. So F is more stronger as compared to Cl. So I will write down 3 first. After that, I will write down 4. Then neutral. And lastly, I will write down plus I. So that is the order of acidic strength. I hope this is clear. I hope this is clear. Let me know quickly. 3412. 3412 is the right answer. Exactly. Right answer. Right answer. Similarly, if you are having acids like this, if you are having acid like this, one is this one, another is this one, another is this one. That means hydrocarbons are there. And number 4, this is what we call ammonia. Now, what you have to do is, you just remove one of the hydrogens and form a conjugate base. This is the conjugate base. This is the conjugate base. Here, conjugate base will be like this. And conjugate base will be like this. Then, after that, these are the carbons, and this is nitrogen. So, which among carbon and nitrogen is more electronegative? Never say nitrogen. Nitrogen in general is more electronegative than carbon, but it depends on hybridization. That's why whenever carbon and nitrogen are there, you have to check first of all hybridization. This is sp, this is sp2 hybridized, this is sp3 hybridized, and this is also sp3 hybridized. Remember, whenever you are having carbon which is sp hybridized, it's more electronegative than nitrogen which is sp3 hybridized. This is electronegativity order. Otherwise, if this condition is not there, otherwise nitrogen is always more electronegative than carbon. So remember this. Similarly, if you are having nitrogen which is sp hybridized, it's more electronegative than oxygen which is sp3 hybridized. Otherwise, we know oxygen is more electronegative than nitrogen in general. But if hybridization of nitrogen and oxygen, nitrogen and carbon is like that, then this is the electronegativity order. So can I say this is more electronegative carbon as compared to more electronegative nitrogen. So negative charge present on this is more stable. Hence, this is more stable as compared to that, which clearly indicates 1 is more stronger acid than 4. After that, we know it is 2. After that, it is 3. So this will be the acidic order. This will be the acidic order. 1, 4, 2, 3. 1, 4, 2, 3 will be the acidic order. Is this clear? Is this clear? Is this clear? Yes, among these it will be 1, 2, 3. But 4 is more electronegative than this carbon, but not this carbon. That's why this will become the acidic order. This will become the acidic order. Let me know quickly. Am I clear till now? Am I clear till now? Let me know quickly. Yeah, sure. I will explain once again. Have a look. First, remove H positive and form a conjugate base of each and every one. But here, nitrogen is sp3 hybridized. Carbon is sp, sp2 and sp3 hybridized. Whenever you are having carbon sp hybridized, that carbon is more electronegative than nitrogen if nitrogen is sp3 hybridization. So this is more electronegative element as compared to this. Negative charge present on more electronegative element is more stable than this. So this is more electronegative. Negative charge present on this carbon will be more stable as compared to this. But this is nitrogen sp3, but this is not carbon sp. This is not carbon sp. Hence, this will be more electronegative than these carbons. So that's why negative charge will be present on nitrogen, more stable as compared to these two. So this conjugate base is more stable than this. So this acid will be more stronger than this. So 1 and 4. After that, among these two, one is sp2 hybridized, another is sp3 hybridized. We know carbon, when sp2 hybridized carbon is there, this is more electronegative carbon as compared to sp3 hybridized carbon. So negative charge present on more electronegative carbon is more stable than this one. Among these, this is the most electronegative carbon than this, but among all four, this is more electronegative element than this is more electronegative element than this is more electronegative element than this. That is why this is the order. I hope this is clear. I hope this is clear. After this, we will be having basic strength. We will be having basic strength of amines. Remember. In general, you can say basicity. In general, you can say basicity is directly proportional to plus I and inversely proportional to minus I. Even you can say in general that basicity is inversely proportional to electronegativity if bases belong to the same period. If bases belong to the same period. And similarly, you can say in general, basicity is inversely proportional to size if bases belong to same group. If bases belong to the same group. So these are few formulas which you have to remember in general, and let me write down first few questions related to this. After that, we will discuss basic strength of amines. Have a look. Say for example, we will be having compare basic strength or compare basicity. Have a look. First question is like this. If you are having CH3, CH2, NH2, then you will be having Cl, CH2, NH2. Have a look. This group is basically plus I, and this group, as we know, this is, say NH2, it can act as a base. This NH2 can also act as a base. Now, both are primary amines, but to this primary amine, to this base, plus I group is attached, and to this base, minus I group is attached. What will happen? Plus I group increases basicity and minus I group decreases basicity. So I will write down 1 greater than 2. So 1 will be the stronger base as compared to 2. Similarly, you can also write down like this, basic character like this. Basicity you can write down like this. First plus I, then neutral, then minus I. But in this, you have to write down strong to weak, and here you have to write down weak to strong. That means plus I groups basically increases the basic character in general, and minus I groups generally decreases the basic character when attached to base. Similarly, if you are having this one, this is NH3, then this is having CH3, NH2, and then this one, F, CH2, NH2. This base is attached to nitrogen, so this is neutral. This is neutral. This is plus I group attached to base, and this is minus I group attached to base. Now, first of all, we have to write down plus I. So I will write down 2, then I will write down 1, and then I will write down 3. Plus I, neutral, and minus I. Plus I, neutral, and minus I. So if more than one plus I group is present at that time, you will write down simply stronger one first, then weaker, and then accordingly minus I groups are more, then weaker and stronger in general. But after this, we will be having example. Say for example, we will be having CH3 minus. Second one is NH2 minus. Third one is having, say for example, OH minus. And fourth one is having, let us suppose, F minus. All these belong to the same period. Carbon, nitrogen, oxygen, fluorine. They belong to the same period. But when bases belong to the same period, it's inversely proportional to electronegativity. We know from this to this, electronegativity increases. Hence, basis T decreases. Hence, basis T will be decreased. That means among these, what will be the order? Order will be 1, 2, 3, and 4. This will be the basis T order. This will be the basis T order. Similarly, if you are having structure like this, F minus, Cl minus, Br minus, I minus. Now, these belong to the same group, fluorine, chlorine, bromine, iodine. So what will happen? On moving from top to bottom, size increases. Size increases, therefore basis T decreases. Therefore, basis T decreases because size and basis T are inversely related if bases belong to the same group. Now, after that, I will write down simply, it will be 1, 2, 3, 4 because this is having smaller size, more basic character. Similarly, if you are having structure like this, HC single bond, this is having CH2 and H2. After that, it's having CH2 double bond CH, single bond CH2, single bond NH2. And we will be having CH3, CH2, and then NH2. Now, all are primary amines, but to this primary amine, there is alkyne part, means sp hybridized carbon is there. In this amine, sp2 hybridized carbon is there, but in this amine, only sp3 hybridized carbons are there. And we know because of sp3 carbon, this becomes plus I group, and these becomes electron withdrawing or minus I groups. But this is stronger minus I, this is weaker minus I, and that is plus I. First of all, we have to write down plus I group, then weaker minus I is 2, and then stronger minus I is 1. So this will be the answer. I hope this is clear till now. Now, am I clear till now? Let me know quickly so that I will start basic character of amines. Come on, let me know quickly. This is very important session. Okay, that's great. Have a look. Our question was basically like this. Our application is actually like this. It's basic strength of amines, and remember, basic strength of amine is solvent dependent. Basic strength of amine is solvent dependent. Basic strength of amine is solvent dependent. It is solvent dependent. That means in gaseous phase or you can say non-aqueous media, or aprotic solvents. That means those solvents which cannot donate protons. If we talk about these solvents, have a look. If we talk about these solvents, you have to remember simply 3-degree amine. Basis T order will be simply 3-degree amine, 2-degree amine, 1-degree amine. Just remember 3-degree amine, 2-degree amine, 1-degree amine if solvent is like this. Just remember. Just try to remember this order. This is the basis T order. Obviously, ammonia will be always, weaker base than amines. This is the basis T order. Number second, in aqueous media, that means if solvent is water, or you can say protic solvent. That means solvent which can donate proton, protic solvent. What will happen? My dear students? Have a look. In such solvents, you have to remember its secondary amine, which is stronger base. After that, it can be 1-degree amine and then 3-degree amine, or it can be like this. Secondary amine first, then it can be 3-degree amine, and then it can be 1 degree amine. Ammonia will be obviously at the end. Now the question is, when is this order applicable and when this order is applicable? Remember, this order is applicable if R is equal to alkyl group is CH3. That means whenever nitrogen primary amine, that means NH2 is attached to CH3. Similarly, NH is having 2 CH3 groups, N is having 3 CH3 groups. If R is CH3, then this is the order, and this is if R is CH2 CH3. Remember these two orders as well. Remember these two orders as well. I hope this is clear till now. So this was all about what we call inductive effect. Now let us take resonance. Let's take a resonance. But before that, let me know in the chats, am I clear? Am I clear till now? Let me know quickly. Let me know quickly. Let me know quickly. Am I clear till now? Okay. Yes, isomerism will be after GOC. Okay. Now we will be having another very important, effect, and that is resonance. What is resonance? As per conjugated systems are concerned, resonance means delocalization of pi electron. But remember, this delocalization of pi electron takes place only in that structure which is the actual structure. For example, actual structure of benzene known as resonance hybrid or the true structure. This is the structure where delocalization of pi electron or resonance takes place. And the information about those that hybrid is given by, say for example, these two structures. And these are the structures which basically cannot explain all the properties of a benzene. Suppose benzene, we know about benzene, one of the properties that all carbon-carbon bonds in benzene, they are identical. But neither this structure explains that property nor this. So basically phenomenon during which single structure cannot explain all the properties of a particular species. That's why those all species, information given by those all species, with the help of that we simply draw a resonance hybrid or actual structure. Now during this actual structure, bonding is delocalized and delocalization takes place over here, and it can explain all the properties of a species. Here bonding is localized and these structures are known as resonating structures, canonical structures, delocalized structures, because they give basically information about delocalization and resonance. And they are also known as Lewis structures. These are hypothetical structures. They cannot be, exist. They does not exist in nature, but they exist only on paper or board. Or so they are separated always by means of double-headed arrow. But these are the structures which give us information about this one where resonance takes place. And so what is resonance? Simply for conjugated system. For conjugated system, it is delocalization of pi electrons. So without wasting time, let's move further. Now the question is, what is meant by conjugated system? What is meant by a conjugated compound? Conjugated compound is that compound in which conjugation is present. Now the question is, what is conjugation? Conjugation means presence of orbitals, whether p or d, at three adjacent positions parallel with respect to each other and within the same plane. Whenever you are having three p orbitals or three d orbitals at three adjacent positions parallel and within the same plane, you simply say that compound is having conjugation and the compound is known as conjugated compound, and the alternate position of that conjugated compound where conjugation is present, they are known as conjugate positions. Now, so this conjugated compound or the conjugation is basically of two types. One is pi-pi conjugation, another is pi-p conjugation. When pi-pi conjugation is present and when pi-p conjugation is present. Have a look. Whenever you are having carbon-carbon double bond, for example of alkene, for example of benzene, and to that an atom or a group is attached. If this atom contains pi bond, then pi-pi conjugation is present. If this atom contains either lone pair, negative charge, vacant orbital, odd electron, then we simply call that conjugation as pi-p conjugation. That means pi-pi conjugation, simple example of pi-pi conjugation is this one. This is the simple example of pi-pi conjugation. Similarly, pi-p can be pi lone pair, pi negative charge, pi odd electron, pi vacant orbital. So This is the simplest example of pi lone pair conjugation. Now, this is having simple example of pi negative charge conjugation. Similarly, this is having simple example of pi odd electron conjugation, and this is having an example of pi vacant orbital, because this carbocation is having vacant orbital, or it can be like this. If boron is also there forming 3 bonds, boron is also having vacant orbital. So this is pi p, what we call conjugation. So this is pi conjugation. After that, there are conditions for resonance. Remember, first condition is that all the resonating structures must have same energy or nearly same energy. That means there should not be very much energy difference between resonating structures, otherwise there will be no resonance at all. Now have a look. If you talk about this structure and this structure, both are similar structures. That means their energy, their stability will be same. Hence, both can be separated by means of double-headed arrow, because potential energy of both these are similar. Similarly, if you talk about this, this is neutral, this is charged. Neutral species is slightly more stable than charged one, but that means there is energy difference, there is stability difference, but not that much, because this charged species having negative charge and positive charge is having complete octet. So whenever charged species having complete octet, that is also considered what we call a stable species. Yes, this is more stable as compared to this, but this is also considered more stable as well, but not as compared to this. Slight difference will be there in stability. That means there will be slight difference in potential energy. Hence, as there is slight difference in potential energy or energy, hence these can be also considered as what we call resonating structures. But here, this is a charged resonating structure. This is also a charged. But this charged resonating structure is such that positive charge is present on less electronegative element. When positive charge is present on less electronegative element, it's considered stable. But if positive charge is present on more electronegative element, it is considered stable provided that electronegative element contains 8 electrons in its outermost shell. That means there at that time electronegative element must have complete octet like this. But this is more electronegative element having positive charge, but its octet is not complete. That means this is highly unstable. That means it's having very high potential energy as compared to this. So energy difference is very much. That's why we will never say that this will show resonance like this. We will never show this. This is wrong. This is wrong. This will not show resonance like this. Because you generally simply remember whenever carbocation is attached directly to polar pi bonds, remember, there will be no resonance. That positively charged species will not be stabilized by resonance, because otherwise it becomes a more, unstable or less stable species. I hope this is clear to each and every one. After that, we will be having another point like this, that arrangement of atoms or position of atoms should not be changed. That means arrangement or position of atom should be same. Have a look. Here, no atom has changed its position. But here, this hydrogen is attached to carbon. Now it's attached to oxygen. That means position of hydrogen has been changed. Hence, these are not resonating structures. Hence, they cannot be separated by means of double-headed arrow, but they can easily separated by means of double-headed arrow. These are the conditions. You have to remember these conditions. After that, resonating structures must have same number of paired and unpaired electrons, but they only differ in way of distribution of electrons. What is meant by that? Have a look. These and these are having almost same energy. That means they are having same energy, number one. Second point was that there must be, no atom should be like that its position is changed. So position of atom should be same. So that's also there. And now this point number third, this is having number of paired and unpaired electrons same. Have a look. 1 pair, 2 pair, 3 pair. This is also bond pair, 4 pair, 5 pair, 6 pair, 7 pair, 8 pair. Here, 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs, 1 unpaired. That means number of paired and unpaired electrons are same. But there is distribution. Have a look towards this oxygen and to this oxygen. This is negatively charged oxygen. This is neutral. This is neutral. Now this becomes negatively charged. That means only way of distribution of electrons. In way of distribution of electron, they differ. But they do not differ in position. They do not differ in energy, hence they can be resonating structures. After that, all those atoms which take part in resonance must be planar or nearly planar. That means if they are not planar, if they are perpendicular to each other, or if they are not planar, they are in different plane, they can never overlap, they can never show resonance. Have a look what is meant by that. This nitrogen and carbon overlaps. This orbital of nitrogen carbon orbital of carbon, they will overlap because they are within the same plane. Hence resonance will take place, because resonance means basically overlapping. Now have a look. Here this carbon, p orbital of carbon, and nitrogen, p orbital of nitrogen, they are in same plane in this case, but here they are not in the same plane. Why? Because this is considered as a bulky group. This is also a bulky group. When two bulky groups are present at two adjacent positions, there will be electronic cloud repulsion between two bulky groups. That means steric repulsion will be there. Due to steric repulsion, one group is changing its plane because of repulsion. Suppose this was like this was like this. Now what will happen? It will be like this. Its p orbital will be like this, and its p orbital will be like this. That means they are not present within the same plane. Hence there will be no resonance. So there is no resonance means there is no overlapping. That means resonance has been inhibited. So inhibition of resonance has been taken place because of steric repulsion. This is known as SIR, means steric inhibition of resonance. That's why here there will be no resonance like this. There will be no resonance like this. That's why I have put a cross over here, because they are not formed. This structure cannot be formed, because if this structure has been formed, we have to overlap these two, but they will never overlap as they lie in different planes. Here they are resonating structures. Here they are not resonating structures. Next is that if elements belong to second period, remember, then all the atoms which take part in, say resonance, if they belong to second period, must have a maximum of 8 electrons. But if they belong to third period, then they must have maximum of 18 electrons. Have a look what is meant by that. This nitrogen, it belongs to second period. It belongs to second period. We know that. So it can have a maximum of 8 electrons. But if we form a resonating structure like this, this nitrogen is having 10 electrons. That means it's a pentavalent nitrogen, which is not possible at all. That's why there will be no resonance in this. That is why these two are not resonating structures. But this can be like this. It can overlap. It can form pentavalent, what we call phosphorus, because phosphorus, it belongs to third period. It belongs to third period, and in third period it can have a maximum of 18 electrons. So it's having 10 electrons. So that is possible. So that is why here resonance will take place. Now have a look. Here, if resonance takes place over here, all the conditions are fulfilled. Hence there is no problem at all. Hence these two are resonating structures of each other. Now let me know in the chats if I am clear till now. Let me know in the chats if I am clear till now. Let me know quickly. Let me know quickly in the chats if I am clear till now. Let me know quickly. Okay, thank you at the rate of King. Okay, Pramila at the rate of Angry. Thank you. God bless you. God bless you. Now we will be having another, that is stability of resonating structures. Remember that resonating structure is considered more stable resonating structure, which is neutral as compared to charged one. So first rule is like this. You have to, whenever question is given in this, topic, first you have to follow these, rules, and you have to answer that question. Have a look. So neutral resonating structure is more stable than charged, because more charge, more reactivity, lesser will be the stability. So this is neutral, this is charged. Obviously this is more stable than this. That's why one is more stable than two. After that, if first rule does not answer the question, you have to use second rule. And what is second rule? More number of chemical bonds in a resonating structure is more stable than that resonating structure which is having lesser number of chemical bonds. But chemical bonds are basically sigma, pi, all bonds, but for a trick purpose, you can simply use pi bonds. You have to find out pi bonds. Here, 2 pi bonds are there, only 1 pi bond is there. So this is more stable as compared to this. So 1 greater than 2. But suppose this question was asked in your NEET examination, then you don't have to use rule 2, because by using rule 1, your answer will be there, 1 is greater than 2. But when 1 is not giving your answer, use rule number 2. But here, when we try to explain rule 2, this is the simplest example, that 1 is more stable than this, because more number of bond means more force of attraction. More force of attraction means more stability. Now, after that, rule number 3. If we will having resonating structures, which resonating structure is considered more stable? That resonating structure is considered more stable in which all the atoms have complete octet except hydrogen, because hydrogen is not having complete octet, that's having complete duplet. Now have a look. This is the resonating structure. These two are the resonating structures. But here, we have to use rule number 1. Both are charged. So you cannot use rule number 2. Rule number second. Rule number second is more number of pi bonds. So 2 is more stable than third. 2 is more stable than 1. So this is the order. So no need to use rule 3. But to understand rule 3, have a look. This is having complete octet, carbon is having complete octet, but this carbon is not having complete octet. This oxygen is having complete octet, carbon is having complete octet, carbon is having complete octet. That means all the atoms have complete octet in this. All the atoms do not have complete octet in this. That's why 2 greater than 1. After that, we will be having another rule. Another rule is that if all the resonating structures are charged resonating structures, then that resonating structure is considered more stable, in which negative charge is present on more electronegative element and positive charge is present on more electropositive element. Have a look, have a look. If we use rule number 1 cannot distinguish these. So rule number 1 cannot explain the stability of this question. Similarly, rule 2, you cannot use rule 2. Rule 3, you cannot use rule 3 because this is not having complete octet, this is not having complete octet. Then, if all 3 rules cannot be used, then you have to use rule number 4. Have a look. Here, positive charge and negative charge are present on carbon and oxygen. Similarly, here, carbon and oxygen, positive and negative charge are present on carbon and oxygen. Both belong to the same period, and we know on moving from left to right, electronegativity increases. That means this is less electronegative element. This is less electronegative element. This is more electronegative element, men. Now, tell me, negative charge should be present on more electronegative element and positive charge should be present on less electronegative element, and at that time, that resonating structure is considered more stable. Now, negative charge on oxygen and positive charge on carbon, that means this. That's why 1 is more stable than 2. I hope this is clear. After that, if positive and negative charges, that means unlike charges, are separated more. When more separation, more charge separation, but between unlike charges is there, that means there will be distance between two opposite charges. More the distance between two opposite charges. Remember, lesser will be the force of attraction, lesser will be the stability. And if distance between two opposite charges will be less, that means if charge separation between unlike charges is less, more will be force of attraction, more will be the stability. So, have a look. Here charge separation is less, positive, negative. Here charge separation is more, distance is more. So this is more stable as compared to this. I hope this is clear to each and every one. After that, we will be having another factor. That means when you are having like charges on two adjacent positions, positive, positive, negative, negative, lone pair, or lone pair, negative charge, then like charges, you know, repel. And when like charges repel, its energy is increased tremendously. Hence, it becomes least stable. This is what we call this rule. Now, Let's apply these on these two questions. Have a look. First of all, we have to find out neutral, rule 1, but there is no neutral species, so rule 1 cannot, distinguish these. After that, rule 2, number of pi bonds. It's 2 pi bond, 1 pi bond, only 2 pi bonds are there. So 2, 2 and 1. That means having lesser number of pi bond will be at least. That means 2 will be least stable. After that, this and this. We have to, compare now these two. Rule 1 and rule 2. We have used. After that, we have to use rule 3. This is having complete octet. Every atom is having complete octet. Every atom is having complete octet. That means rule 3 cannot be used. Rule 4. Negative and positive charge is present on. Have a look. Here, negative charge is present on nitrogen and positive charge is present on nitrogen. Here, negative charge is present on carbon, positive charge is present on nitrogen. So positive charge is present on nitrogen both. So positive charge will not distinguish them. Now, it will be negative charge. One is carbon, another is nitrogen. We know carbon and nitrogen. It's like this, electronegativity increases. Now, this is men, more electronegative element, and this is len, less electronegative element. Now, negative charge is present on more electronegative element. Negative charge present on more electronegative element is considered more stable. Now, so can I say this is more stable as compared to 3? So 1, 3 and 2 will be the answer. 1, 3 and 2 will be the answer. Here, first of all, it is 1 because 1 is neutral. After that, we will be having number of pi bonds. It's 2. It is 2. After that, we have to compare these two. Then octet. This is not having complete octet. This is not having complete octet. Then charge. Now charge. Here, Carbon and oxygen is having negative and positive charge. Carbon and oxygen is having negative charge. Now we have to find out electronegativity. We know this is Len, this is more electronegative element, and this is Len, less electronegative element. So here negative charge will be more stable. Here positive charge will be more stable. That means it is this one. So it will be 4, and after that it will be 3. And in 3 you can see here lone pair and lone pair are present on adjacent position. Hence this is very, very less stable, or this is least stable among them. Now let me know in the chats, am I clear? Let me know in the chats, am I clear? Let me know in the chats, am I clear? Am I clear till now? Now, there are few more species whose stability can be explained on the basis of resonance. So remember, on the basis of resonance, we will simply say stability of any species is directly proportional to extent of resonance. That means more resonance, more will be the stability of species. But resonance depends on equivalent resonance or non-equivalent resonance. Remember, if there is equivalent resonance, extent of resonance will be more. If there is non-equivalent resonance, extent of resonance will be less. That's why it's directly proportional to equivalent resonance, inversely proportional to non-equivalent resonance. Now the question is, what is meant by equivalent resonance? Have a look. These are the two structures given. First of all, just write down the resonating structure of this. We will write down the resonating structure of this. When we form a resonating structure of this, its resonating structure will be like this, and hybrid will be like this. Have a look, have a look, have a look. So this will be the hybrid. So the information related to this hybrid is given by this and this. And remember, the information given by this or this, we will simply say contribution of this and this towards hybrid. And contribution of any resonating structure is directly proportional to stability, as both are equally stable. Hence, contribution will be equal. When contribution of all resonating structure towards hybrid is equal, resonance is known as equivalent resonance. Have a look here. Have a look. When we form its resonating structure will be like this. Its resonating structure will be like this. And hybrid will be like this. Hybrid will be like this. Partial positive, partial negative. Now, if we look towards this hybrid, its contribution is because of this and because of this. But contribution is directly proportional to stability of resonating structure. This is neutral, this is charged. Its contribution will be more, its contribution will be less. That means whenever resonance taking place in hybrid is such that all resonating structures do not contribute equally, that is known as non-equivalent resonance. So in this case it is equivalent resonance, in second case it is non-equivalent resonance taking place. So more resonance will be over here as compared to this. More resonance means more stability. So we will simply say one is more stable than 2 as per resonance is concerned. So 1 is more stable than 2, but as per resonance is concerned. Or we can say in 1 resonance will be more as compared to 2. I hope this is clear. Second is that extent of resonance is directly proportional to linear conjugation, and it is inversely proportional to cross conjugation. Directly proportional to linear conjugation, inversely proportional to cross conjugation. Have a look. If you have a look towards this, these, electrons, delocalization of electron is in one direction. But here, it's not in one direction. It's in opposite direction. This is one, or you can simply say like this. So it can be like this or this. That means in the opposite direction. It's in one direction. So this is linear conjugation. This is cross conjugation. Linear conjugation is having more resonance as compared to cross conjugation. So I will write down 1 greater than 2. I will write down 1 greater than 2. Let me know quickly. Let me know quickly. Am I clear? Am I clear? Come on. Come on, come on, come on. Okay. Okay. After this, we will be having another. That means any atom which takes part in resonance, if that is more electronegative element, its, resonance at that time will be less. What is meant by that? Have a look. Here, it is nitrogen which takes part in resonance, lone pair of oxygen which takes part in resonance. We know nitrogen is less electronegative, oxygen is more electronegative. So more electronegative element, lesser will be the resonance. So here resonance will be less, resonance will be more. So 1 is showing more resonance as compared to 2. After that, more the number of conjugate positions, more will be the resonance. Have a look, have a look. We know here conjugation is there. This is 1, this is 3rd, and this is 5th. Alternate position of conjugated compound. Similarly, 1, 3rd, but this 5 does not have any conjugation. So I will not take 5. So in this case, only 2 conjugate positions are there. Here, 3 conjugate positions are there. So in 1, resonance will be more as compared to 2. After that, resonance is directly proportional to strength of overlapping. Have a look. This is the 2p orbital which contains this, I mean to say, lone pair, and this is also 2p orbital of carbon. So here it is 2p overlap, or 2p pi overlapping taking place. Here it is 3p which is overlapping with 2p orbital of carbon. So here it is 2p 3p overlap, and we know that when orbital overlap takes place in such a way that identical orbitals overlap, that overlap will be stronger. Stronger overlap, stronger will be the resonance. So 1 greater than 2, 1 greater than 2. This will be the resonance order. After that, my dear students, if you are having those, I mean say, pi electrons, because pi electron means either the electron of double bond or a triple bond, or it can be a lone pair, it can be negative charge, depending upon, it's simply those electrons which are present in conjugated orbitals. Now here, in this conjugated orbital, it is lone pair of electron. Have a look, have a look. It is lone pair of electron. As it is lone pair of electron which takes part in resonance. Here, it is lone pair, but it is basically the negative charge. Electron density is more over here. So remember, energy order, you have to remember energy order of pi electrons. Energy order of pi electrons, you have to remember this, is like this, is like this. First negative charge, then lone pair, then double bond, and then triple bond. You have to remember this order. So here, energy order will be like this. So I will write down 2 greater than 1. So this is the resonance order. After that, we will be having an effect known as resonance effect. Now the question is, what is meant by resonance effect? Resonance effect means when any substituent donates electron towards conjugated system and increases electron density of that conjugated system, or withdraws electrons away from conjugated system and decreases the electron density of conjugated system, and this all is because of resonance. When this all takes place due to resonance, we simply call that as resonance effect. So what is resonance effect? Resonance effect is simply electron donating or electron withdrawing capability of any atom or any group because of resonance. So resonance is basically the mechanism through which resonance effect operates. That means if resonance is absent, there will be no resonance effect at all. I hope this is clear. Have a look. This donates electron towards this. This withdraws electron towards this. Whether it donates electron, whether it withdraws electrons away from conjugated system because of resonance, we call that effect as resonance effect. Sometimes we can also call this as mesomeric effect. Now this resonance effect is of 2 types. Either electron donating or electron withdrawing. That means if resonance effect is such that any atom or any group donates electron towards conjugated system and increases its electron density. For example, conjugated system, benzene is there. If any group donates electron towards a benzene ring, it generally increases electron density of benzene ring at ortho and para position. That means ortho and para position becomes electron rich. So during electrophilic substitution reaction, it is electrophile which allows more electron density region. That's why such groups are ortho-para directing groups, and such groups increase electron density of the ring. That means such groups activate benzene ring except halogen. Halogens are ortho-para directing, but they are deactivating because in case of halogen, minus I is more powerful than plus R. Have a look what is written over here. It is that resonance effect due to which any atom or any group donates pi electron towards conjugated system and increases electron density of conjugated system. For example, in case of benzene, such groups increase electron density mainly at ortho and para position. So such groups, I mean say, are known as plus I groups. So plus R groups and plus R groups are always ortho para directing with respect to electrophile because they have increased electron density at ortho and para position. That's why electrophile loves those positions ortho and para. So similarly, plus R groups are activating groups except halogen. That means halogen is plus R group. Halogen is ortho-para directing group due to resonance, but it is what we call deactivating group as its minus I. Their minus I power is more powerful than plus I. So there are few plus R groups. That means there is a series of plus R, so known as plus R series. For that, you have a trick like this: crazy, negative, outlaw, naughty nuns, never obey, old orange nurses offering fresh, clean brown ice. But remember, it's very, very simple that which can show plus R or plus M. This is very simple. When you are having either double bond or a benzene ring, to that atom or group is directly attached. If that atom contains non-polar pi bond, lone pair of electron or negative charge, and if resonance is also present at that time, such groups always show plus R effect. I hope this is clear to you, because this is having negative charge, negative charge, negative charge. This is having lone pair. Have a look. Similarly, this is having lone pair, lone pair. So whenever negative charge, lone pair, or what we call this atom attached to benzene ring or attached to, I mean say conjugated system, if it is having negative charge or lone pair, negative charge or lone pair, or if it is having pi bond, but that pi bond is between similar elements, say for example CH double bond CH2, then it can also show plus R effect. After that, we will be having minus R. Minus R is opposed to that of plus R. So minus R groups are those groups basically which withdraws electrons away from conjugated system. When they withdraw electrons, which electrons? Pi electrons away from conjugated system, they decrease electron density of conjugated system. Hence, if benzene is there, that means they withdraw electrons away from, I mean say benzene, because of resonance, and decreases electron density mainly at ortho and para position. That means if electron density is decreased at ortho and para position, can we say meta becomes rich by default? That's why electron-loving species, electrophile, goes to meta position. That means such groups are meta-directing groups, and such groups are deactivating groups as they withdraw electron and decreases electron density of the ring. So this is what we call plus or minus R effect. So minus R or minus M, what is this? It is that resonance effect due to which any atom or any group withdraws pi electrons away from conjugated system and decreases electron density of conjugated system. For example, in benzene, such groups decrease, this is decrease, have a look. Such groups decrease, electron density mainly at ortho and para positions. So such groups are meta-directing with respect to electrophile, and such groups are deactivating. There are few groups which show minus R effect, and this series is known as minus R series. You have to remember this minus R series. You can use trick as well. So this is pro-nitro scholars can always keep all eggs away and conclude. Now, trick is, how can you find out whether this group is minus R or plus R? Simple. When conjugated system is there or benzene ring is there, and to that atom or group is attached, if that atom contains what we call a polar pi bond, that means it forms a pi bond with more electronegative. Suppose carbon is forming electronegative pi bond with oxygen, with nitrogen, then it's polar pi bond. So if polar pi bond is there, or it contains a vacant orbital, at that time it shows minus R effect, provided resonance takes place, because there are conditions for resonance. Now, have a look. This is having a positive charge. That means vacant orbital is there. This is having, this positive charge, so it will withdraw. This is having, polar pi bond, 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 polar pi bond. Either vacant orbital or polar pi bond is there. It will show simply what we call minus R effect. After that, we will be having applications of resonance. But before that, let me know if everything is clear to you. Yes, I will give you break. Once we will finish GOC, I will give you break. And after break, we will be taking isomerism. We will be taking isomerism after break. When we complete isomerism, I will give one more break to you. So don't worry about that. And after that, we will be discussing hydrocarbons. So don't worry at all. Don't worry at all. You have to be very much focused, as your NEET examination is getting very closer. Today it is, 23rd. That means within 10 days, there is your NEET examination. Okay. So application of resonance. Suppose stability of carbocation, carbanion and carbon free radicals are there. you can use simple formula. That means any carbocation which is having more resonance, according to resonance, is more stable. Similarly, any carbon anion or carbanion having more, resonance is more stable. Similarly, any carbon free radical having more number of more resonance is stable according to resonance. So this is application of resonance. Have a look. Here, this carbocation is more stabilized because it shows it is stabilized due to resonance of both these rings. It is stabilized by resonance of this ring. It is stabilized by resonance of one pi bond. We know. Here resonance is more, after that this, after that this. So I will write down 1, 2 and 3. I will write down 1, 2 and 3. This will be the stability order. Similarly, this negative charge can resonate over here. Similarly, this negative charge can resonate over here. That means it can resonate more here as compared to this, as compared to this. So more resonate negatively charged or more dispersion of a charge, more stability. So once again, order will be 1, 2 and 3. Similarly, my dear lovely students, have a look, have a look, have a look, have a look, have a look. Have a look. This free radical is taking resonance either to this side or to this side. That means it can take resonance from this side as well as this side, more dispersion. It can take resonance in this ring. So more dispersion as compared to this, because it is dispersed to another place. That means only 2 carbons. Here it can be dispersed to 4 carbons. It can be dispersed to 7 carbons. So more dispersions, more will be the stability. So the answer will become once again 1, 2 and 3. After that, we will be having bond length. We will be having bond length. Have a look. Bond length, single bond is larger bond, then partial double bond, then double bond, then triple bond. So this is the order. But partial double bond seems to be single bond. It seems to be single bond. It seems to be single bond, but if it undergoes resonance, it's actually a partial double bond. Similarly, a double bond which seems to be double bond, but in actual sense is a partial double bond. That means there can be 2 single bonds. One is a normal single bond, another seems to be single bond, but in actual sense it is partial double bond because of resonance. Similarly, there can be 2 double bonds. One is a normal double bond, actual double bond, but another seems to be a double bond, but is in actual sense is a partial double bond. If such type of single bond is there, then bond length is inversely proportional to resonance. If such type of bond, say double bond is there, then bond length is inversely directly proportional to resonance. What is this? Have a look. Here, there will be no resonance. That means this is a normal single bond and this is a normal double bond. That means X will be first, normal single bond, and normal double bond will be at last. That means it will be Y. And between X and Y, this and this seems to be single bond, but they are basically partial double bonds. They are basically partial double bonds because they take part in what we call resonance. They take part in resonance. They take part in resonance. So here partial double bonds are there. So these are the partial double bonds. These are the partial double bonds. But which type of partial double bonds are they? They seems to be single bond. They seems to be single bond. That means I have to use this formula. So more resonance, lesser will be the bond length. Have a look, have a look, have a look. This is the conjugate position 1. This is the conjugate position 2. This is the conjugate position 3. More conjugate positions as compared to this. This is having only 2 conjugate positions. So 2 conjugate position, 3 conjugate position. This is having more resonance. More resonance, lesser bond length. That means if this is A is having lesser bond length as compared to Z. So X greater than Z greater than A greater than Y. So this will be the answer. This will be the bond length order. This will be the bond length order. First, normal single bond, at last normal double bond, and partial double bonds will be between single and double bond, single and double bond. Partial double bond will be between single and double bond. But amongst partial double bond, first check whether it seems to be like that of say single bond or double bond, because we have to find out bond length of Z and A. We do not have to find double bond length. We do not have to find out bond length of this double bond. We have to find out bond length of this single bond named as Z and bond length of this single bond named as A. So this is having Both are those, I mean say partial double bonds which seems to be single bond. That means more resonance, lesser will be the bond length. So more resonance, lesser will be the bond length. So it will be having lesser bond length as compared to Z. So Z first and after that Y. I hope this is clear. I hope this is clear. I hope this is clear. Let me know quickly. Am I clear till now? Am I clear till now? Let me know quickly. Let me know quickly. Let me know quickly. Okay. I will send notes of this session on Unacademy NEET English Telegram channel. You can join that Telegram channel, Unacademy NEET English. I will send notes on that channel. Now have a look. Now have a look. This is X, this is X, this is Y, and this is Z, and this is A. You have to find out bond lengths of X, Y, Z, and A. But X is a double bond, A is a normal single bond. That means A will be first and Z will be, X will be at last. A and X. Between A and X, have a look. This shows resonance. When it shows resonance, double bond which shows resonance is basically a partial double bond. Similarly, this double bond shows resonance. That means this double bond is also what we call a partial double bond. That means among these two, Y and Z seems to be, it's a partial double bond basically, but it seems to be double bond. It seems to be double bond. Here, it seems to be single bond. Here, it seems to be double bond. That means we have to use this formula. Now, here we know conjugate positions are from this to this. Here, conjugate position is from first this to this and then to this, because it is like this. So, more conjugate position, more resonance, bond length will be more. Here, more resonance, bond length will be less if partial double bond seems to be single bond. So, I will write down first Z and then I will write down Y. First Z and then Y. First Z and then Y. Why Z first as compared to Y? Because in Z, it is partial double bond which seems to be double bond. That means more resonance, more will be the bond length. I hope this is clear. I hope this is clear. I hope this is clear till now. I hope this is clear till now. Let me know quickly, is this clear? Let me know quickly, is this clear? Let me know quickly. Let me know quickly, is this clear? Okay. Okay, after that, relative acidic strengths or relative acidic character. One is sulfonic acid, another is carboxylic acid, another is phenol. You can remember acidic order like this as well if you want. First, let me write down an acidic order over here. After that, I will try to explain this. First, you have to write down sulfonic acids, after that picric acid, this is picric acid, then squaric acid, after that dinitrophenols. If you are having two nitro groups attached to phenol, after that carboxylic acid, I mean to say if you are having COOH group, functional group, so carboxylic acids. After that carbonic acid, I mean say H2CO3. After that para nitrophenol. After that orthonitrophenol. After that metanitrophenol. I mean say mononitrophenols. After that you can write down phenol. After that you can write down alkyl ammonium. You can write down methanol. You can write down water after that. After that, you can write down alcohol, but remember R is not equal to CH3, because if R is CH3, then it is stronger acid than water. And after alcohol, you can write down terminal alkyne, in which H is attached to sp hybridized carbon. Then it is what we call NH3. Then it is alkene. And lastly, it is alkane. You can write down this order. You can remember this order as well. So if you have, remember this order, if you know this order, you can directly write down the answer. It is 1, 2, and after that is 3. It's 1, 2, and after that it is 3. But have a look. How actually this is, you have to first form the conjugate base of this. R, S, double bond O having a negative charge. This is the conjugate base. Remove H positive and form a conjugate base over here. You can remove H positive and form a conjugate base over here. Have a look. When you form different resonating structures, it forms another resonating structure in which negative charge from oxygen to oxygen takes place, and another once again oxygen to oxygen. That means all the resonating structures are equally stable. That means contribution of these resonating structure towards hybrid will be same, so equivalent resonance will be there. Similarly, in this oxygen to oxygen negative charge, that means once again resonating structures will be equally stable, so their contribution towards hybrid, towards resonance will be equal. That means equivalent resonance. But here negative charge will be resonating from oxygen to carbon. That means first it is more stable, after that it is less stable. That means because negative charge on oxygen is more stable as compared to negative charge on carbon. That means here resonating structures are not equally stable. Hence here it's non-equivalent resonance. So among these two are having equivalent resonance. This is having non-equivalent resonance. That means this is less stable. So it is what we call weaker acid. But among these two, both are showing equivalent resonance. But here what we call conjugate positions are 1, 2, and 3. More resonance. Here conjugate positions are less. That means less resonance. So this is more stable as compared to this. Hence this is stronger acid. After that this. After that this. I hope this is clear to each and every one. After that, basic character of amines. Have a look. This lone pair is delocalized. This is taking part in delocalization. This is also taking part in delocalization, but it takes part more in delocalization. This takes part more. So more delocalization. Remember, more delocalization of an electron, lesser will be its availability. Lesser will be its availability. For proton. If lesser will be its availability for a proton, hence it will become weaker base. In nutshell, we can say if bases are such that, then we can simply draw a formula. We can write down a formula that basis T is inversely proportional to extent of resonance if bases are like this. That means if we are having bases in which that lone pair will take part in resonance. So if it takes part in resonance, more the resonance, lesser will be its availability of electron density. Lesser available electron density will be there where more resonance is there. So here resonance is less, so it will be more available. Here resonance is more, that means it has been used in resonance more, so it is less available for protonation. So this will become weaker base. So answer of this will be 1, 2, and 3. So more resonance. If bases are such that if more resonance is this, more resonance, weaker will be the base. Lesser resonance, more stronger will be the base. In nutshell, you should know this one. You should know this one. If you are having bases, say for example, one base is like this. One base is like this. This nitrogen will act as a base. Another base is like this. Another base is like this. This lone pair is localized. It will not take part in delocalization. It's not, taking part in any resonance. But this is what we call delocalized. This is delocalized lone pair. When it is delocalized, that means it is taking part in resonance. If it is used in, say for example, or taking part in resonance, its electron density will be lesser available. Here, it's not used. That means it is much more available for protonation. So remember, localized lone pair and delocalized lone pair. Among these two, it is always localized lone pair which is more stronger base as compared to delocalized lone pair. So this will become the basis T order. So this will become the basis T order. I hope this is clear. I hope this is clear. After that, we will be having another question, that is aromatic, non-aromatic and anti-aromatic. First of all, you must know that aromatic species are more stable than non-aromatic, which in turn are more stable than anti-aromatic. But when question is asked in your NEET, question will be like this. Which of the following is aromatic? Which of the following is anti-aromatic? Which of the following is non-aromatic? Or how many aromatic species are there? Which of the, how many anti-aromatic species are there? For that, you must remember these conditions. That means, if you are having complete cyclic conjugation, as well as you are having 4n plus 2 pi electrons present in a compound, then remember compound or species is aromatic. And if you are having complete cyclic conjugation with 4n pi electrons, compound is anti-aromatic. If any one among them condition is not applicable, is not applied, or is not fulfilled, if any one condition is absent, then you cannot say anti-aromatic compound, you cannot say aromatic compound, then that compound will be non-aromatic. For example, such compounds are cyclic compounds. That means if compound is acyclic, open structure, that will be always non-aromatic. Are you getting me? Now, have a look. Now the question is, what is the value of n here? 0 to infinity. Here it is 1 to infinity. So just remember, if you are having 2 pi electrons, remember 2 pi. After that, add 4 pi, 4 pi. 2 pi, 6 pi, 10 pi, 14 pi, 18 pi, 22 pi. If compound, if species is having such pi electrons, after that, if it is having complete cyclic conjugation, that means cyclic, planar and complete delocalization, with such pi electrons, it obeys simply Huckel rule and means it is aromatic at that time. Similarly, if you are having 4 pi, 8 pi, 12 pi, 16 pi electrons and a complete cyclic conjugation, at that time it's anti-aromatic. Now the question is, what is meant by pi electrons? How to find out pi electrons? Remember, one lone pair is equal to 2 pi electrons, one negative charge is also equal to 2 pi electrons, and one what we call pi bond is also equal to 2 pi electrons, provided lone pair, provided negative charge, provided that pi bond is basically of conjugated orbitals. If that is not of conjugated orbital, then you have not considered one lone pair as 2 pi electrons. Now, have a look. Let's do some examples over here. For example, first of all, this one. Have a look. As there is pi bond means there is p orbital and p orbital which are present within the same plane. This is having sp3 hybridization. That means there is no p orbital. No p orbital is available. If no p orbital is available, there will be no conjugation. Because what is meant by conjugation? Presence of at least 3p or 3d orbitals at 3 adjacent positions. So here only 2 p orbitals are present at 2 adjacent positions, so there is no conjugation. If conjugation is not there, it is neither aromatic nor anti-aromatic. Hence, we can simply say this is non-aromatic because of absence of conjugation. Now here, this is P because they have overlapped and form a pi bond. This is P, this is P. So conjugation is there because at least it should be present at 3 adjacent positions. It's present at 4 positions and all these 4 positions form a ring. That means complete cyclic conjugation is there. Now, these all orbitals are now known as conjugated orbitals. Can I say these two conjugated orbitals form one pi bond, these conjugated orbitals form one pi bond? That means it's a complete cyclic conjugation is there with 4 pi electrons. Hence, this is known as anti-aromatic species. I hope this is clear. Similarly, this is having p orbital, p orbital, p orbital, p orbital. Conjugation is there. But it's not having complete cyclic conjugation. Why? Because it's not only 4 carbon which forms a ring, it's a 5 carbon which forms ring. 5th carbon does not have any p orbital, so complete cyclic conjugation is absent. When complete cyclic conjugation is absent, this is non-aromatic. What about this? P orbital is there. So complete cyclic conjugation is there. And If complete cyclic conjugation is there, count how many pi bonds are there in these orbitals. 3 pi bond means 6 pi electrons. Hence, this is aromatic with 6 pi electrons. So, benzene ring is aromatic with 6 pi electrons. Have a look. This is P. This is P. This is also P because this is having a positive charge. So, this is having conjugation and that too complete cyclic. So, complete cyclic conjugation is there. But this conjugated orbital does not have any pi electron. These conjugated orbitals have 1 pi bond. That means this is complete cyclic conjugation with 2 pi electrons. Hence, this is aromatic with 2 pi electrons. Very, very, very simple. But if you have a structure like this, remember, this circle inside this ring means complete cyclic conjugation. That means you have to find out only pi electrons if structures are like these. Now, have a look, have a look. You have to write down only pi electrons. How to find out those pi electrons? How many atoms of a ring are there? 4. So write down 4. Here 4. So write down 4. Now inside this circle there is a positive charge. Positive charge means loss of electron. How many positive charges are there? 2. That means loss of 2 electron. Loss means -2. So answer is 2. This gives us information about pi electrons. So this is complete cyclic conjugation with 2 pi electrons. So it is simply aromatic with 2 pi electrons. What about this? 4. Negative means gain of electron. How many negative charges there? 2. So I will write down 2 plus 2. So answer is 6. So it will give us information about pi electrons. Once again, this circle indicates complete cyclic conjugation with 6 pi electrons. That means it's aromatic with 6 pi electrons because whenever you are having 6 pi electron species, after that you are having complete cyclic conjugation also. At that time it is aromatic. Have a look. Whenever you are having such type of compound, you have to break this double bond which is outside the ring. Whenever double bond is present outside the ring, endocyclic double bond, break in such a way that more electronegative element acquires those electrons. That means you have to form its resonating structure. So have a look. This is the negative charge, but you have to look towards the ring only. Those atoms which form ring only, not that atom which does not form ring. Now, so can I say this is p orbital, p orbital, p orbital, p orbital, p orbital. So complete cyclic conjugation is there, but this p orbital does not have any electron. This and this having 1 pi bond, this and this having 1 pi bond, that means 4 pi electrons. Complete cyclic conjugation with 4 pi electron, hence this is anti-aromatic. Anti-aromatic because it's having 4 pi electrons. Okay, this is known as benzene. This is known as benzene. Remember. If any conjugate position, let me tell you, this and this pi bond is formed by what we call p orbital, but another pi bond is formed by sp2 hybrid orbitals. This is sp2 hybrid orbital. Another pi bond is formed by sp2. This pi bond is formed by p and p. This pi bond is formed by p and p. Remember, these p orbitals are within the same plane and parallel with respect to each other. Hence, these are conjugated orbital. But this sp2 is not conjugated. So we have to simply count those pi electrons which are present in conjugated orbital. We do not have to count that pi electron which is not present in conjugated p orbital. Hence, we will count 1 pi bond over here, another we will not count. We will count this pi bond, this pi bond, this pi bond. That means 6 pi bonds are there. That means, 6 pi electrons are there. So this is benzene is aromatic with 6 pi electrons. So remember forever, if any conjugate position contains more than 1 pi bond is taken, another pi bond is not taken as per pi electrons are concerned. Why? Because that pi bond is basically in different plane with respect to conjugated orbitals. They are perpendicular. Have a look. They are perpendicular. Similarly, after this is having negative charge. So this is p orbital, p orbital, p orbital, p orbital, p orbital. So complete conjugation is there. This conjugated p orbital is having negative charge. When conjugated p orbital contains negative charge, it is equivalent to 2 pi electrons. So 2 pi electrons, 1 pi bond means 2 pi bonds means 4 pi electrons. So this is aromatic with 6 pi electrons. And remember, this is known as cyclooctatetraene. It always results in the formation of this structure. Remember, it's having a tub-like structure. It always exists in tub-like structure. It exists in this tub-like structure, and tub-shaped structure is actually non-planar. Hence, this is non-aromatic. Why non-aromatic? As it is non-planar. It is not planar. So, for aromatic or anti-aromatic, we must have planar. Cyclic complete conjugation is only possible if compound is planar. So, remember, if it is given like this or this, remember it is non-aromatic. After that, we will be having this structure. We will be having this structure. This is having complete cyclic conjugation with 2 and 2, 4 pi electrons. So, this is anti-aromatic. What about this? Here, you have to check whenever rings are more than one and they are fused rings, means two rings, between two rings there are at least two atoms common, then you have to check periphery only. You have to check, longest periphery conjugation or longest conjugated path you have to check out. For example, this is P, 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 this is P. You have to find out P. Have a look, only longest conjugated path. This is longest conjugated path, not this path, not this path. You have to check longest conjugated path if compounds are bicyclic compounds, fused bicyclic compounds. Now, have a look. Here, how many pi electrons are there? So, 1, 2, 3, 4, 5 pi bonds. So, this is aromatic with 10 pi electrons. Remember, if you are having what we call a lone pair, remember, one lone pair is in one orbital, another lone pair is in another orbital, but both are in different plane. When they are in different plane, then only you have to count only that which is in conjugation with these. That means, say for example, this is in conjugation with this, so this is having complete cyclic conjugation, but we will count only 1 pi electron because that is present in conjugated orbital, another is present in that orbital which is in different plane. That is why my dear lovely students, here this is aromatic with 6 pi electrons only. You have to count only one lone pair. So whenever any conjugate position contains more than 1 pi bond, only 1 pi bond is taken. Similarly, if any conjugate position contains more than one lone pair, only one lone pair is taken. Similarly, if any conjugate position contains a pi bond as well as a lone pair, pi bond is taken in delocalization, but lone pair is not taken. So similarly, we will say this is having complete cyclic conjugation, pyridine. This compound is pyridine. It's having complete cyclic conjugation with 2, 4, 6 pi electrons. So this is aromatic with 6 pi electrons. After that, let me show you this example. This is very important example. This is very important example. Let me show you like this. This is known as aniline. This is known as aniline. This is known as 10-aniline. This is known as 10-aniline. Aniline means completely cyclic but monocyclic. Completely conjugated monocyclic compound containing even number of atoms. Completely conjugated monocyclic polyenes containing even number of carbon atoms. Even number of atoms. So this is conjugated. If I write down the number of this, its numbering is done in such a way like this, that these two carbons will be numbered at last. That means, have a look, this carbon number 9 and carbon number 10, they are having hydrogens, but they are having very closer to each other. Because of that, there will be non-bonded hydrogen interactions, or there will be what we call electron cloud repulsions between them. Steric repulsion will be there, or there will be electronic repulsions between them, hydrogens, due to which 9 carbon and 10 carbon becomes, or due to this repulsion, carbon number 9 and carbon number 10 are now present in different plane with respect to 1, 2, 3, 4, 5, 6, 7, 8. That means 1, 2, 3, 4, 5, 6, 7, 8 will be in one plane, 9, 10 will be in different plane. If 9 is in different plane, 8 is in different plane, similarly 9 is in one plane, 1 is in different plane, they will not overlap. That means there will be no complete cyclic conjugation. Now, hence, this molecule becomes non-aromatic. This molecule becomes non-aromatic. One more is known as parabenzoquinone. Parabenzoquinone seems to be anti-aromatic, but remember, it is not anti-aromatic, it is non-aromatic, because if it is anti-aromatic, it should be highly unstable. But it has been seen that this, parabenzoquinone is stable even at room temperature. So it is stable at room temperature. Hence, it is not highly unstable. So that's why it can never be an anti-aromatic species. I hope this is clear. After that, we will be having another effect and another, definition, that is resonance energy. What is meant by resonance energy? Resonance energy is actually amount of energy which is decreased, but due to delocalization or due to resonance. And remember, this delocalization or resonance takes place only in resonance hybrid, not in resonating structures. That is why resonance hybrid is considered most stable. Even it's more stable than even most stable resonating structure, because resonating structures do not show delocalization, hence there will be no decrease in energy. But resonance hybrid, actual structure undergoes resonance, hence there will be decrease in energy. Less energy means more stable. So more resonance energy, more decrease in energy. More decrease in energy, lesser energy will be available. Lesser energy, hence more stable. That's why stability of any species because of resonance is directly proportional to resonance energy. Because resonance energy is not normal energy, it is decrease in energy. So more resonance energy, more decrease in energy, more decrease in energy, more stability of the species according to resonance. And remember, this resonance energy can be calculated by a simple formula: energy of resonance hybrid minus energy of most stable resonating structure. And this resonance energy is also known as delocalization energy or resonance stabilization energy. Have a look. So what is resonance energy? It is the amount of energy decreased due to delocalization, and it is also known as delocalization energy or resonance stabilization energy. And remember, resonance energy is energy of resonance hybrid minus energy of what we call most stable resonance structure. We know resonance hybrid is more stable as compared to more stable resonating structure. Reason is delocalization. So if this is energy graph, resonance hybrid is more stable, means less energetic as compared to most stable resonating structure. The energy gap between this is known as resonance energy. And remember, more resonance energy, more stability will be there. But resonance energy value will be always negative, because energy of resonance hybrid is less, energy of most stable resonating structure will be more. So less minus more is always negative. But that negative does not mean resonance energy is exothermic or energy is lost during this. No, it does not mean energy is lost, or resonance energy negative does not mean it's exothermic. That clearly indicates basically how much energetic this is as compared to this, or how much energetic this is as compared to this, or how much stable is this hybrid as compared to most stable resonating structure. After that, we will be having another effect, hyperconjugation effect. It's having many names. Few names are written over here, like what we call sigma delocalization, no bond resonance, Baker-Nathan effect, reversed inductive effect, secondary resonance, extension of resonance. Sometimes it's also known as enchimeric effect. So it's having many names, sigma P overlap. It's having, many names. So these are few names. You can remember such names. Remember, whenever you are having an sp hybridized carbon, and to that carbon, if alkyl group is attached, that means if to that carbon at alpha position you are having sp3 hybridized carbon, and to that alpha there is at least one hydrogen. Remember, hyperconjugation at that time takes place. Similarly, if your carbon is sp2 hybridized carbon, and to that sp2 hybridized carbon attached at alpha position is sp3, and to that hydrogen must be at least one. Now the question is, sp2 carbon can be either alkenic carbon, olefinic carbon, it can be of carbon of benzene, it can be carbocation, it can be carbon free radical. Now the question is, what is actually hyperconjugation? Hyperconjugation is actually delocalization of this, sigma electron of CH bond of alkyl group, which is directly attached to an unsaturated system. It can be an unsaturated system, whether triple bond, double bond, or benzene, unsaturated system. Or it can be directly attached to a carbocation or carbon free radical. That means to that atom which contains unshared p orbital. Now have a look, what is the definition written over there in your NCERT textbook. It is defined as delocalization of sigma electrons of CH, sigma bond of alkyl group attached to an unsaturated system or to an atom with unshared p orbital. Now, types of hyperconjugation. Remember, hyperconjugation is of two types. It's basically extension of resonance. Resonance was having two types. Conjugation there was of two types. One was what we call pi, another was pi p. So instead of pi, here it is sigma. So it can be either sigma pi or sigma p. So sigma pi means whenever you are having sp3 hybridized alkyl group, and to that you are having at least one CH sigma bond. So it overlaps with, that carbon which forms a pi bond. So this is sigma pi. And if it overlaps with p orbital of carbocation or p orbital of what we call carbon free radical, at that time we can simply call these types as sigma p. So have a look. What will happen? Either this will overlap and it will result in the formation of this hyperconjugated structure, or this can overlap, then it will be this, or this one can overlap, then it will result in the formation of this. But none of these is the actual structure. These contribute basically towards actual structure, and actual structure says that this bond is having what we call these CH bonds which take part in overlapping are such that their sigma electron density is equal at every CH bond. That's why this is known as sigma electron delocalization, because delocalization means sigma electron density remains same at this CH, at this CH, and at this CH bond, which basically overlaps. Similarly, you are having, sigma positive and sigma odd electron hyperconjugation like this. But there were two chemists, one whose name is like Muller and another is Mulliken. According to Muller and Mulliken, hyperconjugation is of two types. One is sacrificial, another is what we call isovalent. According to them, sacrificial hyperconjugation is that hyperconjugation in which there is charge separation. Have a look, negative and positive charges are separated, charge separation. That means according to them, sigma pi is sacrificial hyperconjugation, and according to them, hyperconjugation in which there is no charge separation, positive, positive, positive. So there is no charge separation. Odd electron, odd electron, odd electron. There is no charge separation. So according to them, that hyperconjugation is known as isovalent hyperconjugation. So in nutshell, isovalent hyperconjugation means sigma positive, sigma odd electron, or sigma p. Now have a look. This is sacrificial hyperconjugation and this is isovalent hyperconjugation. But number of hyperconjugated structures formed by any aliphatic species involving CH bond is equal to number of alpha hydrogens. 3 alpha hydrogen here. 3 alpha hydrogens will be involved, so it can form 3 structures. But in total, number of alpha hydrogen plus 1 plus that structure which involves CH sigma bond. Now, I hope this is clear till now. So this is hyperconjugation. Now its applications. It can simply, we can explain stability of carbocation, we can explain stability of carbon-free radical, we can explain stability of alkenes on the basis of hyperconjugation. So have a look. We will simply say that extent is directly proportional to hyperconjugation. Its stability is directly proportional to extent of hyperconjugation. But in case of heat of hydrogenation, remember that alkene is having more heat of hydrogenation, which is having more number of pi bonds. So it is directly proportional to number of pi bonds. But if pi bonds is same, then it is inversely proportional to stability. So there are few questions. Have a look. Here, we have to explain stability, but on the basis of hyperconjugation. Now, this is carbocation. To this carbocation, this is sp3 hybridized carbon. So this becomes alpha. So this is having 3 alpha hydrogen. There is no sp3 hybridized carbon attached to carbocation. So this is having 0 alpha hydrogen. To this carbocation, this is alpha because sp3 is this, sp3 is this. That means there are 6 alpha hydrogens, 3 and 3. sp2 hybridized carbocation attached to sp3 is alpha, attached to sp3 this is alpha, attached to sp3 this is alpha, having 9 alpha hydrogens. So what will be the stability order? Stability order will be 4, 3, 2, 1, because more number of alpha hydrogens in general means more hyperconjugation, means more stability. Similarly, here it is 0 alpha hydrogen. Carbon free radical attached to sp3 means 3 alpha hydrogens. Similarly, here it is 6 alpha hydrogens. It's having 6 alpha hydrogen. It's having 9 alpha hydrogens. Because whenever sp3 carbon is attached to carbocation, carbon free radical, or alkene in general, then we call those sp3 hybridized carbons as alpha carbon, and hydrogens attached to them will be alpha hydrogens. So once again, answer will be 4, 3, 2 and 1. I hope this is clear till now. Now after that, this is having 0 alpha hydrogen, but this double bond is having attached to sp3 carbon. So this becomes alpha carbon. It's having 3 alpha hydrogens. This is sp3 attached to sp2, sp3 attached to double bond. So 6 alpha hydrogens are there. Similarly, it's having 3, 6, 9 and 12 alpha hydrogens. So we will simply say that 4 is more stable than 3, 3 is more stable than 2, 2 is more stable than 1. So this is the stability order. After that, compare HOH. HOH is directly proportional to number of pi bonds, but if pi bonds is same, then it's inversely proportional to stability. Pi bonds in this case is same, so we will discuss their stability on the basis of what we call hyperconjugation here. So 3 alpha hydrogens, and here 6 alpha hydrogens. So number of pi bonds are same, so heat of hydrogenation order will be inversely proportional to stability. That means it will be 1, then it will be 2, then it will be 3. Inversely proportional to stability. Now, here pi bonds are equal, but here alpha hydrogens are 4 alpha hydrogens are there. Here, this is alpha, so here 3 alpha hydrogens are there. Here, 2 alpha hydrogens are there. Pi bonds are same. Then, heat of hydrogenation is inversely proportional to stability. That means heat of hydrogenation will be 3, then it will be 2, 3, 2, and 1. So this will be the stability order. After that, bond length. Bond length is similar to that of resonance. Have a look. Now, as we know, this is the X. This X is basically normal double bond. This Y is not normal double bond because this alpha is having hydrogen, so there will be hyperconjugation. Once hyperconjugation takes place, this double bond becomes partial double bond, single bond also becomes partial single bond. Similarly, this is alpha, so this Z double bond becomes partial double bond. So this is normal double bond, these two are partial double bonds. So these two are partial double bonds, but these two are those partial double bonds which seems to be double bond. That means I have to use this formula. Now, this is having 2 alpha hydrogen, this is having 3 alpha hydrogen. More alpha hydrogen, more extent of resonance, this hyperconjugation, more will be the bond length. So I will write down 2 first, after that 3, partial double bond. After partial double bond, I will write down double bond. So I will not write down 2, 3, I will write down bond length of, say Y. Y, after that it is Z, after that it's X, because we have to write down bond length and length of one bond, not of overall molecule. So it's Y, Z and X. YZ first because it's having more alpha hydrogen, more hyperconjugation. Now, here we are talking about those structures which seems to be single bond, but they are not single bond. They are actually partial double bond, and reason is alpha hydrogens are present. As alpha hydrogens are present, so we can simply say there is what we call partial double bond. Have a look. Here, no alpha hydrogen is present, so we can say 0 alpha hydrogen is there. Here, 1 alpha hydrogen is present. Here, 2 alpha hydrogens are present. And these two are the partial double bonds, which seems to be single bond. So for these two, we will use this formula. More alpha hydrogens means hyperconjugation more, bond length will be less. That means its bond length will be less. So I will write down 3 at last, at 2, and then this 1 is basically a normal single bond. There will be no hyperconjugation. So answer will be 1, 2, and 3. I hope this is clear. Now let me know in the chats quickly, am I clear till now? Let me know in the chats. Am I clear till now? Let me know. Quickly. Let me know in the chats, am I clear till now? Let me know quickly. Come on, my dear lovely students. We have to complete this whole class 11th organic chemistry. Otherwise, I also need break. You know, I'm not feeling good, but your time is very precious. My dear lovely students. So be with me, have a patience. I will give break to you once GOC is completed. Okay. Okay. Okay, my dear students. After that, we will be having a directive influence of alkyl groups. Have a look. When alkyl groups show hyperconjugation, they always donate electrons because of hyperconjugation towards ring and increases electron density of the ring mainly at ortho and para position. That means such groups are basically ortho-para directing with respect to electrophile. Such, say phenomenon, hyperconjugation, has no effect at meta position like that of resonance. Remember this. Have a look. Alkyl groups increase electron density of the ring mainly at ortho and para position due to hyperconjugation, and alkyl groups are ortho-para directing with respect to electrophile. So whenever toluene is there, electrophile prefers ortho and para position. Similarly, alkyl groups are ortho-para directing with respect to electrophile. Like resonance, hyperconjugation has no effect on meta position. Why so? Why not meta position is affected? Because electrons will move, will transfer, or this negative charge or electron density will be increased or decreased only to those positions which are conjugated positions. Meta is not conjugated position with respect to this. This is 1, 2 and 3. 1, 2 and 3. 1, 3 are conjugate position. Then 3, 4 and 5. That means 3, 5 are conjugate positions. Then 5, 6, 7. 5, 7 are conjugate positions. Or 1, 2, 3. 1, 3, 5. They are conjugate positions. 1 and 4 are not conjugate position. That's why meta is not affected at all. After that, there is another effect, that is reverse of hyperconjugation, known as reverse hyperconjugation, also known as minus H effect. What will happen over here and which groups show basically minus H effect? Have a look. Whenever you are having sp2 hybridized carbon-carbon double bond, or carbon-carbon double bond in the form of alkene or benzene, not carbocation, not carbon-free radical, such carbon should be present, and to this at alpha position there must be sp3 hybridized carbon, to which at least one group should be there, which is a good leaving group as well as electron withdrawing group, like that of halogen. So if you are having CH3 group, this CH3 group can show a reverse hyperconjugation or minus H effect. What will happen? This X is a good leaving group and an electron withdrawing group. It will leave and it will withdraw electrons from this. That means here electrons were donated towards ring. Here electrons are withdrawn away from ring. That's why this is reverse to that of hyperconjugation, and it decreases electron density at ortho and para position. When it decreases electron density at ortho and para position, that means such groups are meta directing groups, because electron density of ortho and para position has been decreased due to CH3. So CH3 group is meta directing, because it decreases electron density at ortho and para, electrophile will go to meta. That's why this is meta directing. But remember, reverse hyperconjugation or minus H has no effect due to reverse hyperconjugation. This CH3 has no effect at meta position like that of resonance or hyperconjugation. Now have a look what is written over here. Due to reverse hyperconjugation or minus H effect, CH3 group decreases electron density of the benzene ring mainly at ortho and para positions. CH3 group is meta directing with respect to electrophile, like resonance and hyperconjugation. Resonance and hyperconjugation, reverse hyperconjugation has no effect on meta position. I hope this is clear to each and everyone. And remember, in case of benzene derivatives, number of hyperconjugated structures which involve CH bond is 3 into number of alpha hydrogens. Have a look. With this hydrogen 1, 2 and 3. Similarly, with this hydrogen, another 3 structures. With this hydrogen, another 3 structures. So number of alpha hydrogens 3 multiplied by 3. Okay, this is clear. After that, we will be having a temporary effect known as electromeric effect. What will happen during electromeric effect? Pi electrons are completely transferred towards one of the atoms, linked together by means of a multiple bond, but all takes place in presence of a reagent. Have a look. Whenever you are having a pi bond, in absence of this H positive, there will be no electronic displacement. But once this H positive is present, it will act as a reagent. So in presence of this reagent, what will happen? Pi electrons will be transferred. Similarly, there will be no complete transfer of pi electron without this. There will be slight transfer because of electronegativity difference, but there will be no complete transfer of pi electrons. Complete transference of pi electron will take place because of this reagent. So whenever complete transfer of pi electron takes place because of presence of reagent, it is known as electromeric effect. If reagent is removed, there will be no complete transfer of pi electron. That's why this is known as temporary effect, because this effect takes place in presence of reagent and this effect is absent in absence of reagent. So there are two types of electromeric effect is there. One, during electromeric effect, if pi electrons are transferred towards an atom to which attacking reagent gets finally attached, at that time cations are obtained. This is known as plus E effect. And another effect, electromeric effect, is such that during which pi electrons are transferred towards an atom other than the one to which reagent gets finally attached. Reagent gets finally attached to this, but pi electrons are transferred towards an atom other than the one to which reagent gets finally attached, and during this effect anions are generally obtained. So this is electromeric effect and it is a temporary effect. And last effect is inductomeric effect. This is also what we call a temporary effect because it takes place in presence of reagent. So here complete transfer of sigma electron takes place but in presence of reagent. Whenever complete sigma electron transfer takes place in presence of reagent, we can call that as inductomeric effect, or we can simply say inductomeric effect is simply that effect with the help of which inductive effect is increased. That means displacement of sigma electron is increased. Because in case of what we call inductive effect, electron displacement takes place partially, but in presence of reagent, it takes place completely. In presence of this, it takes place completely. So increase or enhancement of what we call this inductive effect has been taken place, but it occurs only in presence of reagent. That's why this is known as inductomeric effect, my dear lovely students. Now, before we take break, I want to give you some formulas as well. Whenever you are having a stability of carbocation, remember it is directly proportional to what we call plus R plus H plus I, and inversely proportional to minus I, after that minus H, and then minus R. That means whenever you have to find out stability of carbocation, these groups stabilize the carbocation and these groups destabilize the carbocation, and stability of carbocation should be like this: first plus R, then plus H, then plus I, then neutral, then minus I, then minus H, then minus R. Here weak to strong and here strong to weak. Another thing you have to remember is this one. This is first. Another thing you have to remember is that first of all, that carbocation in which strain is less is more stable as compared to in which aromaticity is there. So first strain, check strain, after that aromaticity, after that back bonding, after that resonance, after that hyperconjugation, after that inductive effect. There are few exceptions, but this is basically 99.9% correct. So you can use this one. So this is first, stability of carbocation. Number second, stability of carbanion. Stability of carbanion. Remember, it is, let me erase over here this greater and less than. I have written that over here. So these are basically like this. Okay. Have a look, my dear students. Stability of carbanion is directly proportional to minus R, minus H and minus I, and inversely proportional to plus I, plus H and plus R. And remember, you have to write down first minus R, then minus H, then minus I, then neutral, then plus I, then plus H, and then plus R. Here you have to remember from strong to weak. Here you have to go from weak to strong. And in addition, you can remember always it's aromatic. First aromatic carbanions and then electronegativities like sp or sp2, sp3 at that. First, you have to check aromatic carbanion. Aromatic carbanions are more stable as compared to other carbanions, and other carbanions you have to check, like you have to check sp, sp2, sp3 hybridization, or you have to check negative charge holding capacity as well. So, after that, for acidic character, I have already told you, the overall order, so you can use that one. Now this is all about what we call GOC. Now let us take isomerism but after break. So let us take isomerism after break. So break is till, now it is 130, break will be till, as I'm not feeling good, so I need much more break. So break till 2:30 p.m. So it will be 1 hour break because I have to take a good rest as well. So it will be a break of 1 hour. After that, we will be discussing isomerism. So till that, you can have your lunch, you can also rest, and at 2:30 exactly I will be here and we'll discuss what we call isomerism. We will first discuss isomerism. After that, we will discuss hydrocarbons, and after that, we will discuss PYQs. And at the end, we will discuss a few techniques, quantitative and qualitative analysis, but at the end, if time permits. So, let's meet at 2:30. Till then, take care. Bye-bye. Welcome back, everyone. The moment you will all have been waiting for, you have all been waiting for is am I audible and clear? And am I audible and clear? Is something problem in this? Is there any problem in this? Let me know if I am audible and visible to each and everyone. Okay, welcome back, everyone. The moment you have all been waiting for is actually here now. We are diving into the isomerism. I know you have been asking for this one constantly. So let's get into it. But before starting isomerism, I would want you all guys to mark the attendance by smashing the like button and share this stream with everyone and grab your pen so that we will begin this isomerism. So should we start isomerism? How is the Josh? How is the Josh? Should we start isomerism? Should we start isomerism? Let me know in the chats. How is the Josh? How is the Josh? Quickly. Okay. Okay. This is the chapter. I know you have been constantly asking for this. So this chapter is here now. Okay, let's begin without wasting time. Let's begin isomerism. First of all, it's double bond equivalent or degree of unsaturation, or we can simply call this as index of hydrogen deficiency. What is meant by this? This is basically number of hydrogen molecules required so that you can convert an unsaturated compound to a saturated one. For example, if you are having an unsaturated compound like this, CH2 double bond CH2, and you want to convert this into a saturated one, say for example, CH3 single bond CH3. How many molecules of hydrogen do we need? We need one molecule of hydrogen. So, number of molecules of hydrogen required so that we can convert an unsaturated to saturated one is known as degree of unsaturation. That means for this, degree of unsaturation is, or double bond equivalent is 1, or index of hydrogen deficiency is 1. Similarly, how many hydrogen molecules are required so as to convert this into a saturated one? How will you get the number of hydrogen molecules? You simply compare these types of molecules, these are type of compounds with saturated one. When you compare with saturated hydrocarbon, this is having carbon 2, this is also having carbon 2, but this is having 6 hydrogens, this is having 2 hydrogens. That means we need 2 molecules or 4 hydrogens. Hence, for this molecule, degree of unsaturation is 2. So there is no need of any formula to calculate degree of unsaturation. So you simply compare compound given with saturated hydrocarbon, I mean say with alkane, and you know general formula of alkane is CnH2n plus 2, and remember this alkane, degree of unsaturation for saturated compounds is 0. Whenever degree of unsaturation is 0, that means it's saturated compound, and if it is not equal to 0, that means it's an unsaturated compound. That means compound must contain either pi bond or a ring. For example, let's have an example. For example, we have to calculate degree of unsaturation for C2H2. Now compare this with an alkane. Now, alkane having 2 carbon atoms, what will be the formula? It will be C2H6. So you have to compare this with this. When you compare this with this, you will have a look. Here, difference of 4 hydrogen atoms are there. That means there is the difference of 2 hydrogen molecule. So this molecule is having degree of unsaturation equal to 2. When molecule is having degree of unsaturation 1, let me tell you, if molecule is having degree of unsaturation 1, that means this molecule either contains 1 pi bond, means 1 double bond, or that molecule contains 1 ring. Similarly, if degree of unsaturation is 2, then at that time molecule contains 2 pi bonds, and 2 pi bonds can be in the form of 1 triple bond, or it can be in the form of 2 double bonds. Or we can say degree of unsaturation 2 means 2 rings are present in a compound. Or if degree of unsaturation for any species 2, at that time we can say that species contains either 1 pi bond, that means 1 double bond, plus 1 ring. Okay, now have a look. If degree of unsaturation is 2, that means this structure contains either what we call 1 triple bond, or this structure contains what we call 2 double bonds, or this structure contains, say 1 ring. But as this carbon is having only 2, this compound is having only 2 carbon bonds there, so there can be 1 triple bond between these 2 carbons, because 2 carbons can never have 2 double bonds and 2 carbons can never have rings, so there is 1 triple bond. Okay, after that, now you can compare this with alkane. If C10, that means if N is having 10, C10, H2N plus 2, that means H22. This will be the hydrocarbon whose degree of unsaturation is 0. Now compare this with this. So there is 4 hydrogen atom deficiency, that means 2 hydrogen molecule. Deficiency of 2 hydrogen molecule is there. So once again, it's having degree of unsaturation equal to 2. No need of any formula. No need of any formula. You can simply calculate degree of unsaturation like this. Now, this is also hydrocarbon. Carbon and hydrogen is there. Now, compare this once again with alkane. Alkane is having CnH2n plus 2 formula. Now, this is carbon 6. So, carbon 6, hydrogen should be 14. But this is having hydrogen 6. That means 8 hydrogen atoms, which means 4 hydrogen molecule deficiency. So, degree of unsaturation here will be 4. So, whenever you are having hydrocarbons given, compare that with saturated hydrocarbon and find out the number of, hydrogen molecules which are lesser in this as compared to, saturated hydrocarbon. That will give you simply an idea of degree of unsaturation. Am I clear till now? Am I clear till now? Am I clear till now? Let me know in the chats quickly. We have to find out hydrogen atom deficiency first. Then we know if hydrogen atom deficiency is 8, that means hydrogen molecule deficiency will be 4. We have to find out number of hydrogen molecules, not number of hydrogen atoms. Now, after that, this is not only having carbon hydrogen, it's also having chlorine. Remember, if it is hydrocarbon, then compare directly with, saturated hydrocarbon. But if it is having monovalent atom like fluorine, chlorine, bromine, iodine in addition to hydrogen and carbon, then you just remove that monovalent species. That means remove this monovalent species and replace that with hydrogen. That means formula becomes C6H6. Now it becomes a hydrocarbon. Now compare this hydrocarbon with, alkane having same number of carbons. That means you have to compare it with C6H14. When you compare this with C6H14, you will get, difference of 4 hydrogen molecules, which means Du is equal to 4. Du is equal to 4. Now, after that, this is having hydrogen and carbon, and in addition to that, if it is having oxygen, sulfur, divalent species, now you have to just remove divalent species. Remove divalent species, that's it, and form formula. And this formula is now hydrocarbon. Compare it with the saturated hydrocarbon, that means alkane having same number of carbons, that means C7 and H16. You have to compare it with C7H16. Now, what is the difference? Difference of 8 hydrogen, that means 4 hydrogen molecules. So once again, degree of unsaturation is 4. So for this molecule, degree of unsaturation is 4. For this molecule, degree of unsaturation is 4. If this is hydrocarbon, just compare with saturated hydrocarbon. If it's having hydrogen, carbon, and in addition to that, fluorine, chlorine, bromine, iodine, that means monovalent atom other than hydrogen, then remove monovalent atom, add similar number of hydrogen atoms, and then compare with saturated hydrocarbon. If it is having what we call divalent atom, for example oxygen, for example sulfur, in addition to hydrogen and carbon, then just remove oxygen or sulfur, remove divalent species, that at that time it becomes hydrocarbon, then compare with saturated hydrocarbon. But if you are having a trivalent species like nitrogen, phosphorus, then what we have to do is just remove trivalent species and remove equal number of hydrogens as well. So it will become C7H8. Now compare this with saturated hydrocarbon having same number of carbons, C7, and then at that time H should be 16. But if you compare this with this, we have a deficiency of 4 hydrogen molecules. That means we need at least 4 hydrogen molecule to convert this unsaturated to saturated one, hence degree of unsaturation will be equal to 4. I hope degree of unsaturation is clear to each and every one there. Now let me know quickly, is degree of unsaturation clear to each and every one? Let me know in the chats quickly. Let me know in the chats quickly. Is degree of unsaturation clear to each and every one? If you have not studied isomerism, let me tell you, you just be with me. You will be masters in, this isomerism chapter. You will simply be master of this isomerism chapter, but be with me, be sincere towards, this chapter. Have a look. Come on. Have a look. Have a look. After that, we will be having definition of isomerism. Remember, if you are having 2 or more than 2 compounds having same molecular formula but different physical and chemical properties, remember, such compounds are known as isomers and the phenomenon is known as isomerism. But when 2 or more than 2 compounds have different physical and chemical properties, that means such compounds are different compounds. So, simple definition of isomer is different compounds having same molecular formula, remember, are called isomers. Such compounds are called isomers and the phenomenon is known as isomerism. Now, this isomerism is basically of 2 types. Now, we will try to understand isomer with the help of different examples, but first of all, have a look. Isomerism is of 2 types. Number 1 is structural isomerism, another is stereoisomerism. But structural isomerism is also known as constitutional isomerism. It's also known as what we call linkage isomerism, or it's also known as regioisomerism. But first of all, we will discuss structural, constitutional, regio or linkage isomerism. After that, we will discuss stereoisomerism. So, what is meant by structural isomerism? These are basically the isomers which differ in connectivity, which differ in, structural formula. That means isomers having different connectivity or different structural formula are simply known as structural isomers, linkage isomers, regioisomers, or constitutional isomers. And the phenomenon is known as structural isomerism. So isomers which differ in connectivity or structural formula are called structural isomers, and the phenomenon is called structural isomerism. It's of further few types. Let's take these types one by one. First of all, we have chain isomerism, also known as nuclear isomerism, also known as skeletal isomerism. What is meant by chain, nuclear, or skeletal isomerism? Listen carefully. It is that structural isomer, basically structural isomer, which differ in chain. whether that chain is parent chain, whether that chain is side chain. When structural isomer differ in chain, whether parent chain or side chain, we can simply call such structural isomer as chain isomer, and the phenomenon is known as chain isomerism. Have a look, my dear students. We are having this molecule, and in this molecule we are having 4 carbon atoms in a chain, and its formula is C4H10. But if we talk about this molecule, this is also having C4H10 formula, molecular formula same, but connectivity here is different. Here it is CH3 attached to CH2, CH2 and CH3. Here it is CH3 attached to CH. That means connectivity is different, hence structural formula is different. But these are now structural isomers because structural formula is different, molecular formula is same, or connectivity is different, molecular formula is same, hence they are structural isomers. But these structural isomers differ in chain. This contains 4 carbon in chain, this contains only 3 carbon in chain, hence they are known as structural isomer, they are known as chain isomers. Those structural isomers which differ in chain, whether it is parent chain, whether it is side chain, they are known as chain isomers. But remember, this is an alkane, this is also an alkane. That means they are having same homologous series, same what we call functional group. They belong to same homologous series always. So chain isomers always belong to same homologous series. Remember this as well. Now have a look. This is ethyl benzene. In this benzene is, say parent chain, and side chain is ethyl. Here parent chain is once again benzene, but side chain is methyl and methyl. That means they differ from each other in side chain. Whether they differ in parent chain, whether they differ in side chain, but having same molecular formula, at that time we simply call such isomers as chain isomers. They are having same molecular formula, different structural formula, hence structural isomers. But those structural isomers which differ either in chain, parent chain, or in side chain, they are known as chain isomers, and chain isomers have same functional group and they belong to same homologous series. They are what we call alkyl benzenes. This is also alkyl benzene, that means these are arenes, hence they are belonging to the same homologous series. After that, we are having another that is known as position isomerism. So what is position isomerism? Structural isomers which differ from each other either in the position of double bond or in the position of triple bond, say in position of multiple bond, or in the position of functional group, or in the position of substituents. Such structural isomers are known as position isomers, and phenomenon is known as position isomerism. Have a look. Here, 1, 2, 3. 3 carbons are present in chain. What about this? 1, 2, 3. 3 carbons are present in chain. Both are having same chain. Both are having same chain. Both are having 3 carbons in parent chain. And here, what is the difference? Both are having same functional groups. Both are having same chain. Both are having same functional group. But this functional group is attached at carbon 1. This functional group is attached at carbon 2. That means position of functional group has been changed. Such structural isomers are known as position isomers. Here, have a look. 1, 2. Here, 1, 2. Both are having same chain. Both are having, same, what we call side chains or parent chain. Now, both are having same functional group as well. This is what we call dihalide. This is also dihalide. But what is the difference? Difference is here 2 chlorine atoms are present at 1 and 2 position. That means a vicinal position. Here 2 chlorine atoms are present at same carbon. That means to geminal. So these are having difference in position of substituents. Hence these are also position isomers. Have a look. If I write down, if I number this chain 1, 2, 3, 4, this is 1, 2, 3, 4. Both are having same number of carbons as their parent chain is concerned. That means there is no difference in parent chain. But what is their difference? Difference is double bond is present at second position. Here double bond is present at 1 position, or double bond is between 2 and 3. Double bond is between 1 and 2. That means position of double bond. There is difference in position of double bond. Similarly here, difference is in position of triple bond. So whenever you are having structural isomers which differ in either the position of triple bond, in position of double bond, in position of substituents, or in position of what we call functional groups, but their functional group is same and their chain is same, then we call simply such structural isomers as position isomers. And in position isomer, have a look, they belong to same homologous series. This is alcohol, this is alcohol. This is, say dihalide, this is dihalide. This is alkene, this is alkene. This is alkyne, this is alkyne. Same homologous series. After that, we have another rule, but before that rule, you must remember these things, that if alkane is there, alkene is there, alkyne is there, and alcohols are there. Remember, if alkane is there, we must remember this, that minimum number of carbons required to show what we call chain isomer is 4, but to show position isomerism, it is, I mean to say, at least 6. After that, my dear lovely students, for alkenes, we need 4 carbons at least to show chain isomerism, and 4 at least to show position isomerism. Similarly, for alkynes, we need 5 carbons to show chain isomer and 4 carbons to show position isomerism. For alcohols, we need 4 for chain isomerism and 3 for position isomerism. But minimum number of carbons required to show position isomerism is only 2. For alcohols, it is 3. But overall, it's 2. Have a look. Overall, it is 2. Because only 2 carbons can show position isomerism as well. I hope this is clear till now. After that, we will be having a rule known as CS rule. Sometimes you can call this rule as XY rule as well. But for the sake of simplicity, I have written over here CS rule. C means number of carbon atoms present in a chain. So C for carbon. S means substituents. That's why I have written over here CS rule. Now, if CS value for 2 isomers or for isomers is same, then we call simply such isomer, such structural isomer as what we call position isomer. And if CS value is different, we call that as chain isomer. Now have a look. If we compare these two, what is the CS value over here? 1, 2, 3, 4. So value of C is 4. What about S? There is no substituent, so value is 0. So can I say CS is equal to 40? The value of CS for this is 40. What about this? 1, 2, and 3. So number of carbons in a chain is 3. And there is one substituent, so substituent is 1. So total CS value is 3, 1. Now you can compare this value and this value. Both are isomers, but their CS value is different. Hence, these two are simply known as chain isomers. These are simply known as chain isomers. Have a look. This is 1, 2, 3, and 4. So number of carbons present in a chain is 4. Substituent is 0 because this is the functional group. This is not the substituent. So CS value is simply 40. Now here it's 1, 2, 3, 4. Both are, structural isomers. Both are isomers. Now the value of C is 4. There is no substituent, so CS value is also 40. Now compare this and this value. Both are isomers and having same CS value. Hence, these are what we call position isomers. So whenever CS value for isomers is same, they are position isomer. When CS value for isomers are different, they are known as chain isomers. I hope this is clear. But remember, these both belong to same homologous series, same functional group. Both belongs to same homologous series, same functional group. After this, we will be having third isomerism, that is known as metamerism. But before that, let me know in the chats if I am clear till now. Let me know in the chats if everything is clear till now. Let me know in the chats if I am clear till now. Let me know in the chats if I am clear till now. Am I clear till now? Let me know. Let me know quickly. Come on. Be very much sincere. Your exam is getting very closer. That's on 3rd May. So you have to be very much sincere. Okay. After this, we will be having metamerism. What is meant by metamerism? First of all, remember one thing. Compounds can show metamerism only and only if functional group present is polyvalent functional group. That means functional group, if compound is having univalent functional groups, say for example CHO, for example COOH, for example CN, for example OH, for example SH, etc. Such functional group containing compound can never show metamerism. Point number one. Point number two, which type of functional group should be present if compounds show metamerism? Polyvalent functional group, either bivalent or trivalent, like this. Either O I mean say ether, thioether, ketone, ester. It can be secondary amine, tertiary amine, secondary amide, tertiary amide, etc. So such type of polyvalent functional group should be present. After that, the groups attached to these polyvalent functional groups on either side in two compounds should be different. That means, have a look. So structural isomers which differ in arrangement of carbon atoms or arrangement of these groups on either side of a polyvalent functional group, they must be different. Hence, then they are known as metamers, and the phenomenon is known as metamerism. Have a look, my dear lovely students. Have a look. Have a look. This is the polyvalent functional group. Here, polyvalent functional group here. Can I say, in this case, it's one carbon over here and 3 carbons on this side of oxygen. Here, it's 2 carbon and 2 carbons attached to the same oxygen. That means here arrangement is different, here arrangement is different. Hence, they are having same molecular formula. Arrangement is different. Hence, they are known as metamers. What about this? What about this? Have a look. This is the functional group and a polyvalent functional group. First of all, you have to check whether this is a polyvalent functional group or not. Answer is yes. To polyvalent functional group, this was only having one atom. This is having 2 atoms in this functional group, but alkyl groups are attached to this carbon. Alkyl groups are attached to this carbon. Have a look. Alkyl groups are attached to, or groups are attached to only one atom. To this atom, on one side it is 1 carbon, on another side it is 3 carbon. To the same carbon atom of the functional group, 2 carbon, 2 carbon arrangement is there. So 1, 3 and 2, 2, they are different arrangements. Hence, they show metamerism, hence they are metamers. After that. But remember, they are also position isomers. So metamerism is basically a special type of position isomerism as well. Have a look. Here, what is the functional group? Functional group is of ester. Functional group is of ester. And ester, we know, ester is a polyvalent functional group in which there are 2 atoms actually to which groups are attached. One is carbon, another is oxygen. Have a look. One is carbon, another is having oxygen. Have a look. Here, it is 1 carbon attached but to oxygen and 3 carbons attached to carbon. 3 carbons are attached to carbon, but 1 carbon is attached to oxygen. Here, 1 carbon is attached to carbon. Here, 1 carbon is attached to oxygen. That means they are different. Similarly, 3 carbons are attached to oxygen. 3 carbons are attached to carbon. So, oxygen and carbon, they are different. Hence, they are metamers. But if you are having 1 carbon and 3 carbon in this case, and if you write down like this, 3 carbons on this side, 1 carbon on this side. For example, if you write this one, CH3, CH2, CH2, C double bond O, CH3. This cannot be metamer of this. Why? Because it is the same carbon to which 1 carbon alkyl and 3 carbon alkyl is attached. It is the same carbon to which 1 carbon and 3 carbon alkyl groups are attached. But here, 3 carbon alkyl group is attached to carbon. Here, 3 carbon alkyl group is attached to oxygen. That means there is difference between this and this. This is the only one atom to which these alkyl groups are attached. Here, 2 atoms of functional group are there to which alkyl groups are attached. Hence, these are what we call metamers, but these are not. So, let me erase this one. They are not metamers. Okay. So, remember, metamerism, whenever compound shows metamerism or metamers, they are having same what we call functional group, and they also belong to the same homologous series. Now, have a look. If I write down like this, CH3, C double bond O, and then CH2, CH2, CH3. And I will write down CH3, CH2, CH2, C double bond O, CH3. They are not metamers. Why is it so? Have a look. Here, it is the carbon atom of the functional group to which 1 carbon alkyl and 3 carbon alkyl is attached, and here it is the same carbon atom of functional group to which 1 carbon and 3 carbon alkyl groups are directly attached. As here, this is attached to 1 carbon alkyl group. This is also attached to 1 carbon alkyl group. This is attached to 3 carbon alkyl group. This is also attached to 3 carbon alkyl group. They are not metamers, they are homomers. They are same species basically. But why Why these two are what we call metamers? Because here 3 carbon part is attached to carbon, but 3 carbon part in this is attached to oxygen. So if we talk about this carbon, here it is 3 carbon, here it's 1 carbon. So carbon, alkyl part attached to this carbon in these two species are different. Similarly, alkyl part attached to oxygen in these two are different, hence they are metamers. But here they are not metamers, as similar parts are attached in this as well as this. I hope this point is very much clear, because this is sometimes confusing. Sometimes student got confused with this one. I hope this is clear to each and every one. Let me know quickly in the chats if this is clear till now. Let me know in the chats if this is clear till now. Quickly. Okay, this is clear. After that, we will be having another structural isomerism, that is known as functional isomerism. Till now, each and every one, whether it is chain isomer, whether it is position isomer, whether it's metamer, all are having same functional groups. But when functional group is different between two, say structural isomers, we simply call such structural isomers as functional isomers. There are a few examples you have to remember. Such examples: whenever you are having saturated alcohol and saturated ether having general formula CnH2n plus 2O, at that time these are known as functional isomers, because one is having alcohol, another is having ether. Both are having same formula, but they are having different functional groups. Similarly, saturated thiols, saturated thioethers, different formula is, different functional group is there, hence they are known as functional isomers. Similarly, aldehydes, ketones, unsaturated alcohol, unsaturated ether, cyclic alcohol, cyclic ether having this formula CnH2nO, that means formula is same everywhere, but they are having different functional group, hence they are known as functional isomers. Remember these. Similarly, carboxylic acid can be a functional isomer of what? Ester or hydroxyaldehyde or hydroxyketone. Remember. We are having few more examples: cyanides and isocyanides. We are having nitroalkanes and alkyl nitrites, alkynes, dienes, cycloalkanes. Similarly, alkenes and cycloalkanes. Similarly, aromatic alcohols, phenols, aromatic ethers having same molecular formula. Similarly, different degrees of amines. That means if we are having amine, 1 degree amine, 2 degree amine, 3 degree amine, that means primary amine, secondary amine, tertiary amine. If they are having same molecular formula, they will be called as functional isomers, because they are functional, their functional groups is different. 1 degree amine, secondary amine and tertiary amine have different functional groups. Similarly, a different degree of amides, primary, secondary and tertiary amide or oxime, if they are present, they are known as functional isomers. So after this, we will be having ring chain isomerism. Remember, structural isomers in which one structure is open structure, another structure is closed or ring structure having same molecular formula, they are known as ring chain isomers. Have a look. Alkynes and cycloalkenes. Similarly, alkenes and cycloalkanes. Have a look. Say for example, if I write down like this, this is what we call cycloalkane. This is having C4H8 formula, and if I write down like this, this is also having C4H8 formula. Both are having same molecular formula, but remember, one is having open structure, another is having ring structure. Such compounds are known as what we call ring chain isomers. They are also having different functional group. This is having double bond, this is having alkane, this is alkene. They are having different functional groups. They can also be called as functional isomers. But when you are having say such type of compounds and you have to choose whether they are ring chain isomer or functional isomer, for that you have to remember this preference order: RTF MCP. First, ring chain isomerism got preference, then tautomerism, then functional isomerism, then metamerism, chain isomerism and positional isomerism. But remember, all metamers or having same molecular formula as well as same functional group. Similarly, chain isomers have same molecular formula, same functional group. Position isomer have same molecular formula, same functional group. But ring chain isomers have different functional groups. Functional tautomerism have different functional groups, and functional isomers have also different functional groups. Now, among ring chain and functional groups, they are ring chain isomers as well as functional isomers. But which is having more preference? It is ring chain. Hence, if you have to choose only one option, at that time we will say ring chain isomer. But if option is that they are ring chain as well as functional isomerism, they show ring chain isomerism as well as functional isomerism, then you will tick or you can encircle ring chain as well as functional isomerism. I hope this is clear till now. After that, we will be having few questions over here. Let's try few questions, but before that, let me know, is everything clear? Let me know quickly, is everything clear? Is everything clear? Let me know quickly. Let me know quickly. Let me know quickly. Is everything clear till now? Is everything clear till now? Let me know. Let me know quickly. Okay, everything is clear. It's very, 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 very easy. Very easy. Have a look. Have a look. Have a look. Have a look. Now, these two structures, you have to find out whether they are chain isomers, whether they are position isomers, whether they are metamers, whether they are functional isomers, whether they are ring chain isomers. How to find out that? Have a look. First of all, what will be their functional group? Is their functional group same or different? Same. If functional group is same, remember functional group. If functional group is same, they can be either M, either C or P. If functional group is different, remember, if functional group is different, they can be either R, either T, or say what we call functional isomers. But we have not studied tautomerism yet, so we will be simply searching out whether this is a ring chain isomer or a functional isomer. If functional group is different at that time, they can be RTF. Have a look how to solve such type of questions. As functional group is same, so they can be either metamer or chain isomer or position isomer. Now, in this case, there is no, to check whether it is showing metamerism or not, as there is no polyvalent functional group, hence this can never be metamers. They can never be metamers. So, there is chain and position. For chain and position, use CS rule. Here, number of carbons present in a chain, so C is equal to 6 and S substituents are 3, so CS value is 63. Here, C is 6, S is 3, hence CS value is 63. Now, CS value of these two compounds are having same CS value, hence such compounds are simply known as position isomers. Such compounds are known as position isomers. After that, have a look. This is chain terminating functional group. So you can write down like this. So carbon present in a chain is 5, and this is the substituent. So substituent is 1. So CS value is simply 51. CS value here is 51. What about this? 1, 2, 3, 4, 5, 6. That means they are having different chain. Whenever they are having different chain, they are chain isomers, or simply you can write down C is 6 and there is no substituent, hence CS value is 60. So different CS value, hence they are simply chain isomers. Simple, they are chain isomers. Okay, once again, they are having different functional group. If they are having different functional group, it is either R or F. Now, this is not having that one is having open structure, another is having what we call a ring structure. So this is not ring chain isomer, hence we will simply say these two are functional isomers. After that, have a look. Both are having same functional group. That means they are either M, either C or P, but this is what we call a polyvalent functional group. So first of all, we will check whether they are metamers or not. How to check? Here, to this carbon benzene ring is attached and to this carbon cyclohexane ring is attached. That means they are different. Similarly, to this oxygen cyclohexane ring is attached and to this oxygen benzene ring or phenyl ring is attached. Hence, they are metamers. What about these two? They are having different functional group. That means either ring chain or functional isomer. But one is cyclic, another is ring. Another is what we call open chain. One is cyclic, another is open chain. Hence, they are ring chain isomers. Of each other. Now, after that, what is the name of this compound? Have a look. It is 2-bromo 3-chloro-benzene. This is also, have a look, Not 2 bromo, it's 1 bromo. 1 bromo, 1 bromo, 3 chloro. This is also 1 bromo, 3 chloro benzene. Both are having same molecular formula. Both are having same name. And we know same name means same compounds. So they are not different compounds. As they are same compounds, so they are not isomers. If they are not isomers, they can never be chain isomer, position isomer, ring chain isomer, functional isomer, metamer. So they are basically homomers. They are actually homomers of each other. Now let me know if I am clear till now. Let me know in the chats quickly. Am I clear till now? Am I clear till now? Let me know in the chats quickly. Let me know quickly in the chats. Am I clear till now? Clear. Okay, that's great. That is great. After that, you have to remember these so that we can calculate number of structural isomers in few questions. You have to remember for alkane, if alkane is given, you have to remember this. You can directly write down number of structural isomers possible. So for methane and ethane and propane, only one structure is possible. But for butane, it's 2. For pentane, it's 3. For hexane, it's 5. For heptane, it's 9. For octane, it's 18. For nonane, it's, what we call 35. And for decane, it's 75. Remember this forever. And for alkyl groups, methyl, ethyl, possible structure is 1. But for this and this, you have to double. That means double of 1 is 2, then double of 2 is 4, and double of 4 is 8. After that, you have to write down 17. So you can remember this as well. When you remember these, you can solve alkane question directly, or you can solve those questions in which alkyl groups are present. Have a look. Question is, find total structural isomers for C4H9Cl. C4H9Cl. First of all, make it a habit, calculate du first. And remember, this is C4H9Cl. What we have to do is remove Cl and add H. It becomes C4H10. When it becomes C4H10, compare it with saturated hydrocarbon, that means alkane containing 4 carbons. That is also having C4H10 formula. That means there is no hydrogen deficiency at all. That means it is having, degree of unsaturation is 0. But as we don't have to draw the structure, we have to simply calculate. So we don't need du, but make it a habit. First of all, you have to, calculate du. First of all, it is C4H9Cl. So can I write down it is Cl? Then to this Cl, C4H9 is there. And we know C4H9 can be possible. That means its possible structures can be 4. That is written over here. C4H9. It's 4. So as C4H9 is having 4 possible structures, so therefore question is find total structural isomers for C4H9Cl. We will simply say total structural isomers for C4H9Cl will be 4 in number. That's it. Question done and dusted. After that, we will be having another question. Find total number of structural isomers for C4H10O. But first of all, what is C4H10O? Its degree of unsaturation is 0 and its general formula is CnH2n plus 2 and O. That means it can be either an alcohol or ether, that too saturated one, because degree of unsaturation is 0. For alcohols, have a look. Very simple. Have a look. If you have to find out alcohol, we know formula is OH. And among C4H10O, I have written OH. Can I say the remaining part will be C4? And among H10, I have written one H over here. So H9 is there. And this part can show 4 possible structures. So formula C4H10O have 4 alcohols. And for ether, trick is like this. Have a look. For ethers, write down like this. O and write down CH3 on one side. Or you can write down like this after that. If I write 1 carbon from this, remaining carbons will be 3. And hydrogen 3 is here. Among 10, 3 is here. So there will be 7 hydrogens. Which one among these is, I mean to say, large alkyl group? It is this one. So this large alkyl group can form 2 structural isomers, or two possible structures are there. Have a look where it's written there. C3H7 can have 2 structures. So first what you have to do is write O and CH3 on right side, and remaining carbons and hydrogens you have to write down that on left side, and you have to remember whether it is methyl, ethyl, then 1 it's propyl, then 2, it is butyl, then 4, it is pentyl, then 8, it is hexyl, then 17. After that, what you have to do is add CH2 from this side. From lower side you have to add CH2. C and C becomes C2. H3 and H2 becomes H5. Then it is O. Then from this side you subtract CH2. Here you add, and from this side subtract CH2. It becomes C minus C. C3 minus C. That means it becomes C2. H7 minus H2. It becomes H5. So C2H5, C2H5, both are similar. So you can take any one, say for example this one. If both are not similar, you have to take larger one. So both are similar, take any one. So it can form 1 structural isomer. After that, add CH2 once again from this side, from that side which you have already added CH2. Okay, it becomes C3. C2 and C becomes C3. H5 and H2 becomes H7. Then it is O. Then it becomes, have a look here, you have to subtract this, it becomes CH3. But this is oxygen attached to propyl and methyl. This is also oxygen attached to propyl and methyl. That means this have been repeated. This structure has been repeated, so we don't need this, we don't count over here. That means total number of isomers possible as alcohols will be 4 and total ethers 2 plus 1 will be 3. So total isomers will be 7. 4 will be alcohols, 3 will be ethers. I hope this is clear. Let me know in the chats if this is clear to each and every one. Let me know quickly. Let me know quickly if this is clear to each and every one. Let me know quickly. Okay, that is great. After that, we will be having find 1 degree, 2 degree and 3 degree alcohols. If it is not total number of alcohols, then you cannot use this trick. Then here it is 1 degree, 2 degree and 3 degree alcohols. For that, you must know if your carbons are 4 in number, how many chain isomers will be possible for that. One will be this one, 4 carbons in one chain, and second one will be 3 carbons in one chain, and one will be the side chain. Only 2 possible structures will be possible as per chain isomerism is concerned. Now, have a look. This carbon and this carbon, they are both same carbons. This is same carbon. These two are same carbon. Here, this and this, they are having similar, groups on 4 sides. That means they are having same similarity, and this will be different carbon. Now have a look. If I attach OH to this, remember, if I attach OH to this and this, both will give same alcohol. So I will attach OH to this, then at that time will not attach to this. Similarly, if I attach OH to this and this, both will give same, alcohol, so attach to this, not with this. That means here 2 types of alcohols will be formed. This will be a primary alcohol, this will be a secondary alcohol. Here, if you attach OH to this, that will be a primary alcohol. If you attach OH to this, both, these all will be similar type of alcohol. So never attach to this, attach to only one. After that, here, this is a different carbon, attach OH to this. Have a look. As this is a primary carbon, this is a secondary carbon. So OH attached to this will give primary alcohol. OH attached to this gives secondary alcohol. As this is the primary carbon, OH attached to this will give primary alcohol. Similarly, this is a tertiary carbon, and OH attached to this will give a tertiary alcohol. So primary alcohols formed will be how many? This is primary, so 1. This is primary, so 1. That means primary alcohols will be 2. Secondary alcohols secondary alcohols will be this one. There is no secondary carbon. So 1. Tertiary alcohols. Tertiary alcohols, there is no tertiary carbon. This is the tertiary carbon. So tertiary carbon is 1. In total, there will be 4 alcohols. 2 will be primary, 1 will be secondary, 1 will be tertiary. Have a look. C4H10O is having 4 alcohols. With the help of this trick, you can write down any trick. Okay. Am I clear till now? Am I clear till now? Let me know quickly. Let me know quickly. Am I clear till now? Am I clear till now? Let me know quickly. Let me know quickly. Okay. Okay. That is great. That is great. Have a look. First of all, it's a given C4H10H8O. That means if you find out, if you calculate DU, it will result in the formation of DU1. That means this DU1 is either in the form of a double bond or in the form of a ring. But it is clear from there. That means we have to find out aldehyde or ketone. We know in case of aldehyde, it's already a pi bond. So no need to find out the ring. In ketone, it's already a double bond there. So we have to concentrate, ourselves to double bond, not to ring. So we will not find ring. We will talk about double bond only. Now, this is aldehyde. This is aldehyde. So number of aldehydes and number of ketones. How to calculate? Have a look. These are ketones. What is the formula? C4H8O. So 1C is written there. So in C4, 1 is written here. That means there will be C3H7 remaining part. C3H7 means there will be 2 structurally possible isomers for aldehydes. Here, first write down CH3 over here. After that, 2 carbons are already there. And here formula is C4. So 2 is here. So I will write down C2H5. And in these 2, this is the larger one, and we know it will form 1 isomer. After that, let me add CH2 from this side, and let me subtract CH2 from this side. C and C becomes C2, H3 and H2 becomes H5, then it is C double bond O, then it is CH3. But it is this C which is attached to ethyl and methyl. This is also attached to ethyl and methyl. That means they are amine to same. So that's why I will take only 1. So there is 2 aldehydes possible, 1 ketone possible if you are having this structure. So in total, we are having 2 plus 1, 3 aldehydes and ketones in total. 2 aldehydes and 1 ketone. So total aldehydes and ketones will be 3 in number. After that, total carboxylic acids and esters. Total carboxylic acids and esters. If you check DU, DU is 1. So carboxylic acid is C double bond O, OH. DU1 means 1 pi bond is there. And in ester, there is 1 pi bond also. So this is carboxylic acid. And this is ester. Have a look. What you have to do is, it's very simple. 1C is here and remaining carbons will be 3 and hydrogen 7. So once again, it will form 2 carboxylic acids. How many esters? Write first of all CH3 from this side, and then 2 carbons are there, so 2 are remaining, so write down C2H5. So among these 2, this is the larger one, so it will form 1 isomer. After that, add CH2. Add CH2. It becomes C2H5. It becomes like this. You have to subtract CH2 from this side, it becomes CH3. But they are not same. Why? Because here O is attached to CH3, here O is attached to C2H5. Here C is attached to C2H5, here C is attached to CH3. That means they are different. If they are different, among these 2, this is the larger one. So this will form 1 isomer as well. After that, add CH2. It becomes C3H7, and then it becomes H. And we know this can be H as per ester is concerned, because this carbon can be attached to H because formic ester is this. Now after that, among these two, this is the alkyl part, and we know this shows 2 isomers. But you cannot, say go beyond this, because you cannot subtract CH2 from H. So we will stop over here. So how many isomers? 1, 2, 4. So there are 4 esters and 2 carboxylic acids. In nutshell, we will be having 6 carboxylic acid and esters for C4H8O2. After that, how many amines, total possible amines? C4H9N. This is having degree of unsaturation equal to 0. That means they are saturated amines. And we know amines are having primary amines, we will be having secondary amine and tertiary amine. Primary amine, secondary amines and tertiary amines. We will be having 3 types of amines. Have a look. If we talk about primary amine, formula is NH2. If we talk about secondary amine, its formula is NH. And if we talk about tertiary amine, its formula is N. Now, have a look. Now, here it is C4H9 remaining part. So it will form 4 primary amines. And here I will write down first CH3, then remaining part will be C3H7. So this is the larger part, so it will form 2 isomers. After that, I will add CH2 from this side. Then it will become C2H5. Here NH. Here I will subtract CH2. It will become C2H5. This is different from this. So any one you can count. So let us suppose this one. After that, if you add CH2, it becomes C3H7, and it becomes, if you subtract CH2 from this side, it becomes CH3. Now, N is attached to methyl and propyl. N is attached to methyl and propyl. That means this has been repeated, so we don't need this one. So 4 primary amines, 3 what we call secondary amines. Now we will talk about tertiary amine. Let us write down CH3 and CH3 from this side. Then you will write down C2H5 from this side. So they will it will form 1 isomer. After that, if you add CH2 from this side, it will become C2H5. Have a look. If you add from this side, it will become C2H5. This becomes CH3. This becomes CH3. But this has been repeated because N is attached to 2 methyl and 1 ethyl. It is repeated. But if you add CH2 to this, then what will happen? It can be C2H5. Then it is CH3. Then it is CH3. Once again, this is one and the same thing. This is one and the same thing. Now, if you add to this and subtract to this, but it becomes secondary amine. That means these are repeated. So I will remove these. So there will be simply 4, primary amines, 3 will be secondary amines, 3 in total will be secondary amines, and 1 will be tertiary amine. In total there will be 8 amines, 4, 3 and 1. I hope this is clear till now. After that, we will be having the total number of structural isomers for C4H8. C4H8 is having Du equals to 1. Du equals to 1. 1 means 1 double bond. That means alkene, and 1 ring. Now, have a look. We know C4H8 means carbon 4. Can be like this as per alkenes are concerned. It can be like this. First of all, I will show alkene. And as we know, this is type A, this is type B and type B. Similarly, this is A and A, this is type B. Now, where we can form a double bond? We can form double bond between, say AB from this side, then not from this side, because both will give same product. So I will simply put a tick over here and cross over here, because among these two only one AB will form a double bond. Similarly, BB double bond can be possible. So here AB double bond can be possible, either this one or this one or this one. That means we will be having 1, 2 and 3 alkenes. What are the structure? Have a look. So it can be like CCC, or it can be C double bond C like this, or we can be having an alkene like this. And after that, you will satisfy valencies by putting hydrogen. So these are, acyclic 3 alkenes, and we will be having ring structure. Ring structure having carbon 4 is one is this, another is having 3 carbon and 1 CH3 group like this. That means cyclic structures will be 2, acyclic structures will be 3. If I put hydrogens over here, we can have a structure like this. We can have a structure like this. Have a look. We can have a structure like this. So this is C3H8, this is C4H8, this is 1, 2, 3, 4, 3, 4, 5 and 8, C4H8, C4H8, this is C4H8, this is C4H8. So in total we are having 5 structures, 3 acyclic open structures and 2 cyclic structures. I hope this is clear till now. After that we will be having another that is known as tautomerism. But before that, let me know in the chats if I am clear till now. Let me know in the chats if I am clear till now. Let me know in the chats quickly. Let me know in the chats quickly if I am clear till now. Come on, my dear lovely students. Let me know in the chats. Class duration will be obviously 10 to 12 hours, as this is a mega marathon going on. It will be up to 10 or 9:30, 10:30. I mean, say it will be around 9:30 to 10:30 anytime. Okay. After that, we will be having tautomerism. There are a few names, other names of tautomerism like desmotropism, cryptomerism, allotropism, merotropy, prototropy, reversible isomerism, dynamic isomerism. You can have different names of these tautomerism. But what is tautomerism actually? Tautomerism is that type of structural isomerism which basically, tautomers are those structural isomers which arises due to migration of hydrogen or migration of proton or oscillation of proton between 2 polyvalent atoms within the same molecule. But remember, have a look. Structural isomers which are interconvertible, they are always interconvertible into one another, and they are interconvertible due to hydrogen migration between 2 polyvalent atoms within the same molecule and are called tautomers, and phenomenon is known as tautomerism. Tautomers, as they are interconvertible into one another, they are always in dynamic equilibrium with respect to each other. There are few different types of tautomerism. Remember, open system, ring system and valence tautomerism, but these are not in our syllabus. We have to check open system only. But remember, open system is having 2 types, cationiotropy or prototropy. That means proton migration or cation migration will take place here. So we will take this one. Another is anianotropy, means anion migration takes place, but this is generally studied. This is generally studied under the heading allylic rearrangement. So we will not go with this as this is not in the syllabus. Now only this type of tautomerism is in our syllabus. So we have to migrate proton or cation. This is of 2 types. One is dyad system, another is triad system, or it can be a space tautomerism as well. Now what is meant by that? Have a look. Here carbon withdraws electron from hydrogen, so hydrogen becomes H positive. That H positive is attracted by electron. So hydrogen migrates from carbon to nitrogen, and carbon nitrogen are adjacent to each other. So if this is 1, this is 2. That means 1-2 proton migration takes place, or similarly this nitrogen withdraws electrons from hydrogen, hydrogen becomes H positive, this negative charge will accept H positive. That means it will be, migrated, proton migration takes place between 2 adjacent species. We call this as 1-2 proton migration, hence dyad system. But if hydrogen migration takes place in such a way that carbon-hydrogen bond is broken, have a look, both forms a double bond over here, then oxygen becomes negative charge, then oxygen takes this hydrogen. So if this is 1, this is 2, this is 3, that means 1-3 proton migration takes place between carbon and oxygen. Carbon is polyvalent, oxygen is polyvalent. So 1-3 proton migration, whenever 1-3 proton migration takes place, it's triad system. If 1-2 migration, proton migration takes place, it is dyad system. Now here H will withdraw, this oxygen will withdraw electrons from H. H is lost as H positive. It will form a double bond over here. It becomes negative charge. Negative charge will accept this H positive. So H from this carbon to oxygen or oxygen to carbon will migrate between 1 and 3 atoms. So 1-3 proton migration, triad system, and 1-2 proton migration is diad system. But in our syllabus, we are having triad system of, prototropy or triad system of tautomerism. That's why we will focus over here. Here, one of the compounds is having C double bond O group. This is known as keto. This is known as keto form. So whenever you are having C double bond O of aldehyde, ketone or ester, this is known as keto form, and this is known as ene, and to this ene, OH group is attached, so this is enol form. So when proton migration takes place in such a way that keto form gets converted to enol or vice versa, we call that tautomerism as keto-enol tautomerism. Generally, keto-enol tautomerism is 1-3 proton migration, but it can be 1-5, 1-7, 1-9. But 1-5, 1-7, 1-9 or more than that are known as space tautomerism. This is known as triad system of tautomerism. Actually, triad system of tautomerism is basically of 12 types further. But you don't worry, you have to focus on only one type, and that is keto-enol tautomerism. That's why we have to remember conditions for keto-enol tautomerism. First condition, remember, if you are having a keto form, and in this keto form, you have to check whether there is sp3 hybridized carbon to which hydrogen is attached. If you are having sp3 hybridized carbon to which hydrogen is attached, you have to think, if hydrogen is removed as proton, it will form a carbanion over there. And is that carbanion in conjugation with C double bond O? If it is, then this keto can be converted to enol and vice versa. That means this type of keto can show keto-enol tautomerism. Similarly, if enol is given, then OH should be attached to that carbon which is of carbon-carbon double bond. If it is like that, then this can show keto-enol tautomerism, provided in addition to these conditions, there will be no, stability. There will be no decrease in stability or drastic decrease in stability. What is meant by that? Have a look. This is the compound. This is not having any sp3 hybridized carbon, so it can never show keto-enol tautomerism. This is having sp3 hybridized carbon. This is sp3, this is sp3, this is sp3, this is sp3, this is sp3. But we have to check that sp3 if hydrogen is removed from that. If hydrogen is removed from that, say for example this hydrogen. For example, this hydrogen. If hydrogen is removed from this, so carbanion will be in conjugation with, oxygen. So this will form. Okay, so this is one, sorry, this is two. This will not show because there is no such type of hydrogen attached which can show tautomerism. Now the question is, this is having sp3 hybridized carbon, but there is no hydrogen. This is having sp3 hybridized carbon. But if hydrogen is removed, this carbanion is not in conjugation with C double bond O. That's why it will not show. Now have a look. Here are hydrogens. We generally remember alpha hydrogens. Don't remember alpha hydrogens only. Because if we remember alpha hydrogens, then this is C double bond O, this is alpha carbon. And here hydrogen is not attached to sp3 hybridized carbon. So alpha hydrogen here are not enolizable hydrogen. Hydrogens present at alpha carbon here do not take part in keto-enol tautomerism. But this is the sp3 hybridized carbon. If this hydrogen is removed as proton, negative charge is in conjugation with oxygen. You know conjugation, hence it can show tautomerism. After that, this one. From this position, if you remove hydrogen, negative charge is in conjugation with oxygen, so this can show tautomerism. Similarly, these types of hydrogens can show tautomerism. After that, here, yes, these types of hydrogens can show tautomerism. So conditions are there. Here, condition is there, but if we remove this hydrogen and form, say negative charge, removing hydrogen, negative charge forms a double bond. It becomes O minus finally accepts H. Have a look what it results. It results in the formation of this structure, and this structure is anti-aromatic. That means highly unstable. Even though condition is suitable for keto-enol tautomerism, but it will not show keto-enol tautomerism. Because it results in the formation of highly unstable, say this enol form. So if keto gets converted to enol and enol is highly unstable, or enol gets converted to keto and keto is highly unstable, at that time keto-enol tautomerism does not take place. That's why I have written over here, these are the conditions, but these conditions are valid only and only if stability is not affected drastically. Here, stability is affected drastically, that's why it cannot show keto-enol tautomerism. After that, this will show keto-enol tautomerism. It will simply do like this. H positive will, be attached to this. So its keto form will be like this. Here, it will not show keto-enol tautomerism because this is aromatic compound. If it undergoes, it does not prefer keto-enol tautomerism. Reason, it prefers to stay in this stage. It's approximately 100%. It prefers approximately 100% in this. It will not prefer to go here because it is approximately 0%. Reason, because this is aromatic, very stable. That's not aromatic. So as this is very stable, it prefers to stay in this. And if it prefers to stay in this, it will not prefer keto-enol tautomerism. Have a look. This hydrogen is present at bridgehead position. So it cannot form a double bond over here because bridgehead position can never be sp2 hybridized up to 8-membered ring. So it will not take part in, keto-enol tautomerism. But these hydrogens will take part, hence this will take part. So if I write another example like this, 13th example like this, if I write like this, this hydrogen is present, but it will not take part. Why? Because if it takes part in resonance, keto-enol tautomerism, then what will happen? Have a look. What will happen? Here it becomes a double bond and then it is OH. Have a look. It is not, possible. It's not possible. Reason, because here bridgehead position becomes sp2 hybridized, and which is not possible according to Bred's rule. So that's why it's not formed. If it is not formed, this hydrogen will not take part in keto-enol tautomerism. Now, let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Let me know quickly. Let me know in the chats quickly. Am I clear till now? Thank you, thanks for responding. God bless you all, God bless you all. That's great. After that, we will be having some comparison between enol content, but both are keto. That means we have to form enol first of all. Let us form an enol over here. This is the enol of this. Then enol of this is like this. This is the enol. Now have a look. Can I say in this resonance is more, so more stable. Resonance is more stable. Hence, we will simply say answer will be 2 greater than 1. So more stable enol, so more will be the enol content. Okay. After this, what will be the enol of this? Enol will be like this. Enol will be like this. Here, enol will be like this. Now, which enol is more stable? This is more stable because of resonance, because of aromatic character. So we will simply say 2 will undergo much more faster enolization. That means enol content of second will be more as compared to enol content of first. Here, what will be the enol over here? Enol will be like this. Here, enol will be like this. Listen carefully. This is stabilized by chelation or intramolecular hydrogen, same as this. This is having C double bond O, this is having C double bond O. Both are having, similar stabilities, but here resonance is like this. It is linear conjugation, but here this is having resonance like this, but at the very same time, here resonance is like this as well. That means here is cross conjugation as well. So in this case, resonance will be less Here resonance will be more. So this is more stable than that. That means one will form more enol content as compared to second. In case of second, enol content will be decreased due to decrease in resonance energy or decrease in stability because of cross conjugation. Here, it will form an enol like this. It will form an enol like this. It will form an enol like this. Have a look, my dear lovely student. This is aromatic. This ring is aromatic in nature. This is non-aromatic. And this is anti-aromatic. Highly stable, stable, and this is least stable. So, can I say 3 will form more enol content, after that 2, and lastly it will be 3. It will be 1, sorry. So, this is the, I mean to say, answer of this question. I hope this is clear. I hope this is clear. 1 greater than 2 will be the answer of this. So, enol content. That means enol content depends on what? Stability of enol. And stability of enol can be, I mean, so you can check whether the compound is stable because of aromaticity, because of resonance, because of hyperconjugation, many factors, intramolecular hydrogen bonding, so on and so forth. After that, you have to compare stability. One is keto, another is enol. Remember, in general, keto form is more stable than enol. Let me write down over here. In general, keto form of simple aldehydes, simple ketones, remember, is more stable than enol form due to bond dissociation energy, or you can say bond energy calculations. Remember, this keto is having 361 kilocalories per mole energy, which has been lost when C double bond O is formed. Similarly, this enol, instead of keto, when enol is formed, remember 343 kilocalories per mole energy will be lost. So which one is more stable as per bond energy calculation is concerned? So it is 1 which is more stable than 2. Remember. After that, we will be having second one. C double bond O, C double bond O, C double bond O is in common. But this C double bond O is having what we call 361 kilocalories per mole energy, which has been lost. This is having, remember forever, this is having what we call 343, I will write down over here, 343 kilocalories per mole energy, but according to bond energy. We will compare each and everything. But do you know this is also having chelation? So because of chelation, remember, because of chelation, it's having further 7 kilocalories per mole energy which has been lost. So what you have to remember is, listen carefully first. After that, this is having this type of resonance as well. And this type of resonance, that means the energy which has been decreased is approximately 15 kilocalories per mole. So here it's only bond dissociation energy or bond energy which is 361 kilocalories per mole. There is no chelation, there is no resonance energy. Here it is bond energy is what we call only 343 kilocalories per mole. Now this is not in what we call resonance with this one, so there is no resonance energy. This shows resonance with this, but we have, we don't, use that resonance value because we use bond energy there. And after that, there is chelation, so you can use chelation value as well. Chelation value is 7 kilocalories per mole. So in total, this is 350 kilocalories per mole energy which is lost. This is 365 which has been lost. This is 361. So 365 means much more energy is lost. This is less energetic, hence more stable. After that this, after that this. In nutshell, whenever you are having diketone, remember that enol is more stable than diketone, which is like this, in which resonance as well as chelation is present. This is more stable. You have to remember this. You don't have to remember values. You have to remember this. This is more stable as compared to this. But another enol in which there is only chelation, there is no further resonance with C double bond O, that is less stable. So let me erase this all. You have to remember this one now. You have to remember this one now. What you have to remember is, have a look. First of all, here resonance energy as well as chelation. Because of that, it becomes more stable than keto. And after that, it will be that enol, which is only stabilized because of chelation. So this will be the answer of this question. After that, this keto, this is enol, this is anti-aromatic. Have a look. Anti-aromatic means this is less stable, so it is 1 greater than 2. After that, this was having beta, this is beta diketone. This is beta diketone, but this is beta keto ester. One is ester, another is keto. This is beta keto ester. Remember, in this case, as you know, this one shows what we call, cross conjugation as well. So its enol percentage is less. So this is less stable as compared to this. So keto is more stable than enol. But why here enol, this enol is more stable than this? Because of one, chelation, another is resonance. But here resonance is less than 11 kilocalories per mole because of cross conjugation. Here resonance was approximately 15 kilocalories. So it becomes 365. But here it is 343 enol, then 7 chelation, then less than 11, that means less than 361. But this shows 361. That's why 1 greater than 2. After that. This is enol, so this is more stable as compared to this, so it will prefer to be present in enol. After that, this is normal ketone, and this is enol. Remember, in normal aldehyde, normal ketone, we know that this bond energy is more as compared to this, so we will simply say first keto form is more stable. After that, here it's having 3 and 3, 6 alpha hydrogens. This is having 2 alpha hydrogens. So this is more stable. So 2, after that it is 3. So this will be the answer 1, 2, 3. Normal aldehyde or ketone, first keto, then enol. But among enols, here hyperconjugation will decide the stability. But in beta diketone, remember this type of, enol, in which this functional group OH is in conjugation with this C double bond O, and also shows what we call chelation, is more stable than keto form. Another will be less stable than keto form. I hope this is clear to each and everyone. After that, we will be having stereoisomerism. What are stereoisomers? These are the compounds having same molecular formula, same structural formula as well. That means their connectivity is also, same molecular formula, same structural formula, but different relative arrangement of atoms or groups in three-dimensional space are called stereoisomers, and the phenomenon is known as stereoisomerism. Remember, the stereoisomerism is of two types. One is conformational, another configurational. Those stereoisomers which can be interconverted into one another by simple rotation about sigma bond are known as conformational isomers, and those stereoisomers which cannot be interconverted into one another by simple rotation about sigma bonds are known as configurational isomers. Generally, we cannot say these are, a type of stereoisomer, because stereoisomers basically are the real isomers, and these are not the real isomers, because these conformational isomers cannot be, separated from each other. They are always interconvertible into one another. They cannot be separated, but you can remember that this is one type and this is another type. So let me complete first conformational isomer, and after that configurational isomerism. So first of all, conformational isomers. What are conformational isomers? These are basically the isomers which are obtained because of rotation. Or these are the isomers which can be interconverted into one another by simple rotation about sigma bond. That's why they are also known as rotamers, conformers, conformational isomers, conformations, and the phenomenon is known as conformational isomerism. Basically, they need very small amount of energy, and that energy is already available at room temperature. So remember 2 points regarding this. They cannot be isolated at room temperature, because at room temperature they are interconvertible into one another. Second point, remember, during rotation, when different conformers are obtained, bond length and bond angle remain same, but their dihedral angle is changed, but their bond length and what we call bond angle remains always same. Have a look. Now we are having in syllabus conformational analysis of ethane. We know ethane is having formula CH3CH3. Say for example C2H6. Now, when you rotate this carbon-carbon single bond, so because of rotation of carbon-carbon single bond or sigma bond, there are infinite number of forms which are possible. That means ethane is having infinite number of conformations. But the two extreme conformations are very important for us. One is eclipsed, another is staggered. One is eclipsed, another is staggered. Now, what is eclipsed and what is staggered? Have a look. If I write down this carbon with the help of this dot and this carbon with the help of this circle. So this is front carbon, that is back carbon, Newman projection is this. So to this carbon, 3 hydrogens are attached, and to that back carbon, 3 hydrogens are attached. What is the angle? If I say, what is the angle between this carbon hydrogen and carbon hydrogen or back bond? I mean, say, hydrogen atom attached to front carbon and hydrogen atom attached to back carbon. What is the angle? That angle is known as dihedral angle. So here dihedral angle is 0 degree. Whenever angle is 0 degree, we call that form of ethane as eclipsed form. And if we rotate, say for example, we rotate back carbon, not front carbon. Front carbon remain as such, but we rotate back carbon, say for example 60 degree towards clockwise direction. Then what will happen? This will come to this place, this will come to this place, because 120 is the angle and half of that is 60. So this will come to this place. I hope this is clear. Now, what is the angle between this and this? Minimum angle between, I mean say, hydrogens present at two different carbons, front carbon and back carbon, is 60 degree now, and that angle is known as dihedral angle. So if dihedral angle of any conformation of ethane is 60 degree, we call that as staggered form. We call that as staggered form. Have a look. Can I say this electron and this electron, I mean say bond, this bond and this bond, they are separated from each other by means of 60 degree. So the electronic repulsion, the electron repulsion between these bonds of two different carbons, this repulsion is known as torsional repulsion. This is known as torsional repulsion. And the groups present at front carbon and back carbon, if their electron clouds repel, we call that as steric repulsion, or we call that as van der Waals repulsion. So repulsion because of size is known as van der Waals repulsion or steric repulsion, and repulsion due to electron repulsion is known as what we call torsional strain or torsional what we call repulsion. So because of torsional repulsion, molecule may appear torsional strain, and because of steric repulsion or van der Waals repulsion, there may be steric strain or van der Waals strain in the molecule. Have a look and tell me, can I say this bond and this bond, they are very closer to each other. Hence, there will be electron repulsion more. That means here torsional strain, torsional repulsion will be more. This is free from torsional strain because they are at an angle of 60 degree. So staggered is considered as free from torsional strain. Similarly, if we talk about this hydrogen and hydrogen, this hydrogen attached to front carbon and hydrogen attached to back carbon, and they are very close. Hence, there may be some what we call steric strain or van der Waals strain, but here hydrogens are far apart from each other. There will be no van der Waals strain or steric strain. So can I say strain will be more, repulsion will be more in eclipse form. So this will be more energetic, less stable. This is free from torsional strain, or there will be less repulsion as compared to this, less strain as compared to this. So this is what we call less energetic or more stable. And molecule prefers to be present in this at any instant of time, but they are interconvertible into one another. They cannot be separated at room temperature. But let's suppose this is having 0 kilocalories per mole energy. Then this is having more than 0 kilocalories per mole. Why? Because this is more energetic. This is more energetic, and the energy difference between these two is approximately 3.3 kilocalories per mole or 12.5 kilojoules per mole approximately. So remember, whenever theta is 0, it's eclipsed. Whenever theta is 60, it is staggered. And eclipse is having more repulsion, less stable. This is having less repulsion, more stable. So stability order will be staggered, greater than eclipse. Energy order will be eclipse, greater than staggered. I hope this is clear. But There are many forms, infinite number of conformations are possible for ethane, but other forms, their angle, dihedral angle will be either more than 0, that can be 1, 2, 2.5, 4, 7, 9, anything between 0 to 60. That means it can be greater than 0 or it can be less than 60. Such forms are known as skew forms. So stability of skew forms will be always between staggered and eclipse, staggered, skew and eclipse. Similarly, energy of skew forms will be between eclipse and staggered. That means first eclipse, then skew, then staggered. I hope this is clear. This was all about ethane. After that, if we are having propane, similarly, propane is having same type of, repulsions. So we can simply say if theta is 0, it's eclipse. If theta is 60, it's staggered. Staggered is more stable as compared to eclipse, because here it is free from torsional strain or lesser repulsions or lesser strain. Here its strain will be more. So staggered greater than eclipse, stability, and eclipse greater than staggered. But the difference is only that here will be more repulsion compared to this eclipse form. Here it is CH3. Because of that, group size has been increased. So this will be approximately 3.5 or 3.6 kilocalories per mole energy difference. So if this is having 0 kilocalories per mole, then this is 6 kilocalories per mole energy, or 3.3 kilocalories per mole here and 3 over here. Or you can say this is 3.3, then this will be 3.5, or you can say if this is 3, then this is 3.3. I mean to say this will be slightly in having higher energy, this eclipse form, as compared to ethane. Now after that, all other forms will be in between. That means skew forms will be in between. So if question is like how many conformations are possible for ethane, infinite, how many conformations are possible for propane, infinite. Remember, but two extremes are very important. One is eclipse, another is staggered. After that, we will be having N-butane. So if we form conformations between 2 and 3 carbon, that means let us suppose this is carbon number 2 and let us suppose this back carbon is carbon number 3. Then we will be having 4 important conformations over here. 2 are having theta equal to 0. When theta equals to 0, it is eclipse form. Theta equals to 0, it's eclipse form. And another theta equals to 60, it is staggered form. Theta equals to 60, it is staggered form. And we know staggered form is more stable than eclipse always. But here, bulky groups, CH3 and CH3, bulky groups, they are having, say theta equal to 0. This is known as fully eclipse. When bulky groups are having theta equal to 0, this is known as fully eclipse. When bulky groups are theta equal to 180, we call this as partially eclipse. And if bulky groups are having theta equal to 60, we call that as gauche or gauche. And if CH3, that means bulky groups are, having 180 dihedral angle, we call that as NT form. That means we are having basically 2 forms. One is staggered, another is eclipse, and staggered is more stable than eclipse. But after that, staggered is having 2 forms, NT and gauche, and similarly eclipse are having 2 forms, partially eclipse and fully eclipse. So what will be the stability order? First it will be NT, then it will be gauche or gauche, then partial eclipse, and after that it will be having fully eclipse. So fully eclipse will be having higher energy, 5 kilocalories per mole, then 3.6 kilocalories per mole, 0.90. But this is the only, basically, the difference. If this is 0, then this is 0.9. If it is 1, this is 1.9. Say this is the difference between these two. Similarly, difference between this and this is 3.6. Difference between NT and this is 5 kilocalories per mole. Why is it so? Have a look. This is having more strain as compared to this one, because this is also having torsional strain, electron cloud repulsion. Here it's neither electron cloud repulsion nor what we call bulky group repulsion. But as compared to this, here bulky groups are closer as compared to this. That's why we can simply say here repulsions will be more as compared to this. But here torsional strain, these are free from torsional strain because these are staggered forms. So free from torsional strain, here torsional strain is more, so these are less stable, these are more stable. But among these two, here will be CH3 repulsion, van der Waals strain or steric strain more as compared to this. That's why this is less stable as compared to this. Similarly, among these torsional, this van der Waals strain will be more as compared to this. That's why first of all you have to write down NT. Then you have to write down gauche. After that, you have to write down partially eclipse and finally fully eclipse. I hope this is clear to everyone. But we have few groups you have to remember. If we have a compound like this, CH2, CH2, then here it is OH, another it is Z. Z can be OH, F, Cl, Br, OH, F, Cl, NH2, NHR, NR2, NO2, CHO, COH, etc. That means those species which are here can, these species can form simply, have a look. Just give me a second. Now, these species which are formed over here, when we form gauche of that, have a look. This is the gauche. If this is having OH and this is having OH, there will be intramolecular hydrogen bonding. That means it becomes more stable because of intramolecular hydrogen bonding as compared to this one. So that's why if such group is present at that time, we know staggered is more stable than eclipse. But among staggered, gauche becomes more stable due to what we call electrostatic force of attraction, or we can simply say intramolecular hydrogen bonding. That's why gauche becomes more stable than NT. So you have to remember this. Partially eclipse, fully eclipse remain as such. Similarly, if this is having an ion, cation, and this is having, Z is having either OCH3, OH, FCl, Br or this one, then this becomes more electronegative as this. So this will be partial negative, partial positive. So this becomes a dipole. So dipole, ion dipole interactions will be more in gauche. So gauche becomes more stable. In nutshell, you have to remember, if this is the structure, in these cases, gauche will be more. Similarly, if this is the structure, in acidic medium, it remains as it's. As such, gauche will be more stable than NT, but in basic medium, base will abstract H positive, it will result in the formation of this. At that time, it will be normal, NT, gauche, then partially eclipse and fully eclipse. That means you have to remember three things only where gauche can be more stable as compared to NT. There are many more, but you have to remember these three for NEET or for JEE. Now have a look. One is this, two is this, and third one is this one. In these three, gauche will be more stable than NT. Otherwise, NT is always more stable than gauche. I hope this is clear. After that, for cyclohexane, this is generally not, asked, but let me tell you that you have to remember this one, that here four forms are very important: chair, half chair, twist boat, and boat. And among these, what will be the stability order? First, chair is most stable. After that, it is twist boat, then it is boat, then it is half chair. This is the stability order, and reverse of this is obviously energy order. And you have to remember one more point, that is twist boat is the only conformation of cyclohexane which is chiral because of absence of plane of symmetry or center of symmetry. Now, what is plane of symmetry? What is center of symmetry? We will discuss that in optical isomerism. But now you have to remember that chair is more stable than twist boat, then half chair, because chair form is basically the staggered form of this, and its boat form is actually what we call its eclipse form. And in this half chair, there is what we call very strain. Because of that, it becomes least stable. Now you have to remember these things as per cyclohexane is concerned. After that, whenever cyclohexane is having bulky groups, say for example methyl groups attached to cyclohexane, then which type of cyclohexane is more stable? Which type of chair form is more stable? Remember, that type of chair form is more stable in which bulky groups are present at equatorial bonds. These are the equatorial bonds. This is equatorial, but this is axial. This is axial. This is axial. So remember, stability order will be 3. After that, let me write down this with another pen. So 3, then it will be 2, then it will be 1. Why? Because more bulky groups at equatorial position. Remember, more bulky groups at equatorial position increases stability. Remember this, increases stability. Similarly, if you are having, say for example this one. If you are having, suppose this one. Suppose you are having this one. It is CME3. C having 3 methyl and a tertiary butyl. And this is CH3. Both are present at what we call axial positions. After that, one is present at axial, another at equatorial. Third, now CH3 will be present at equatorial and this will be present at axial. And number 4, both are present at equatorial positions. Remember, If both are present at equatorial position, that will be more stable. That will be more stable structure. So I will write down 4. After that, among CH3 and CME3, which one is more bulky? Obviously, CME3 is more bulky. So more bulky present at equatorial is more stable. So it is 2. After that, it is 3. And lastly, it is 1 because both are present on axial position. So what you have to remember is, if cyclohexane ring contains bulky group like methyl or any other group, so in general, we will simply say if bulky group is present at equatorial position, that conformation of cyclohexane will become more stable. That is it. That is it. So this was all about what we call conformational isomerism. But here is the question, that which of the following can show conformational isomerism? Let me check. Let me check. Can you know the answer of this question? Let me know. Let me know. Do you know what will be the answer? What will be the answer? Which of the following can show conformational isomerism? Or which among these can show what we call conformational isomerism? If you have your basics clear, then this session is more than sufficient. This session is more than sufficient because I am trying to teach you each and everything. I will not even skip one concept. I try my level best. I will try my level best. But only thing is that if time permits. Okay. Now, do you know how to find out which can show conformational isomerism? Let me know. Yes or no? Do you know how can we check whether the compound shows conformational isomerism or not? Let me know, yes or no. Let me know in the chats quickly. Do you know that? How to check conformational isomerism? Let me know quickly. Thank you, beta. Thank you at the rate of Ria. Thank you. Okay, let me know. I'm waiting for your response. Do you know how to check? How to check which among these can show conformational isomerism or not? Okay, that is great. That is great. Now, remember. For conformational isomerism, we have to check. For conformational isomerism, we have to check 3 continuous sigma bonds should be present. 3 continuous sigma bonds should be present. 3 continuous sigma bonds should be present in the molecule, should be present in the species. If it is present, then we can say conformational isomerism is possible. Have a look. This is HCH4. This is basically HHH. This is CH4. But here, we don't have 3 continuous sigma bonds, so it will not show. Here, we don't have 3 continuous sigma bond because it's having a pi bond over here. We need only sigma bonds. We need only 1. This is not that 1, 2, 3. No, this is having also pi bond. There should no pi bond at all. So this is not showing, I mean to say, isomerism, conformational isomerism. But what about this? HCHH. Then H. Have a look. It will show. 1, 2, 3. Either from this side or from this side. That means it will show. What about this? HCH, H, O and H. What about this? Yes, it can show 1, 2, 3. That means it will show. Okay. What about this? What about this? Can I write down this in this fashion? It is CHH, H, then it is C, then it is H, then it is double bond, then it is C, then it is H, then it is H. Have a look. This is 1, this is 2, this is 3. So continuously they are having 3 sigma bonds, so it will show. What about this? What about this? What about this? So HCH, double bond C, single bond H, single bond C, single bond H, double bond CH2. Have a look. It is this one, then this one, then this one. Yes, they are having 3 sigma bonds continuously, so it can show. What about this? What about this? N, H, H, O and H. 1, oh, it's 1, then 2 and then 3. So it will show. What about this one? N, H, H, N, H, H. So it will also show. It will also show 1, 2 and 3. 3 continuous bonds. That means it can show conformational isomerism. This is in general. This is in general. Now, after that, we will be having few questions. Minimum number of carbons required to show conformational isomerism for alkanes. For alkanes, minimum number of carbons required to show conformational isomerism is 2. And for any compound, minimum number of carbons required is 0. Sir, how 0? Have a look. There is no carbon. There is no carbon, but it can show conformational isomerism. There is no carbon, but it can show conformational isomerism. I hope this is clear to each and every one. After that, we will be having types of configurational isomerism. First, geometrical and then optical isomerism. Have a look, my dear students. This is geometrical isomerism. Remember, geometrical isomerism is that stereoisomerism which arises because of restricted rotation or hindered rotation. And restricted rotation is either in the double bond or in triple bond or in what we call single bond of a ring. You know that. So, whenever there are few conditions, I hope you know these conditions. Condition number 1. Condition number 1 is there must be at least 2 centers about which hindrance or restricted rotation is present. After that, each center must contain 2 groups. That means if one center contains 2 groups, second center contains 2 groups, but both the groups attached to same center should be different, but all these 4 groups should be present within the same plane. And after that, third one is very important, that their areal distance, that means distance between identical groups in all geometrical isomers should be different. Have a look. First is there must be at least 2 centers about which rotation is restricted. Say for example, if I talk about this and this, here rotation should be restricted. Similarly, rotation should be restricted. First of all, 2 centers should be present. After that, the groups attached to this center should be different. Similarly, groups attached to this center should be different. Say for example, if one is A, another must be B. If this is A, another should be B, because both must be different. Here it may be different. With respect to each other, they may be either different or same, but to one center, 2 groups should be different. Similarly, after that, all these 4 groups should be present within the same plane and areal distance should be different. Have a look. If this distance between A and A is L1, here distance between A and A is L2. L1 should never be equal to L2. These are the conditions for geometrical isomerism. So, if we talk about geometrical isomerism in alkenes, first of all, we know alkenes are having 2 centers which are having restricted rotation, and after that, you must know that these groups attached to alkene should be different and these groups should be different. You have to check only different groups attached to, say this carbon and this carbon, because all these groups are always present within the same plane because this alkene structure is planar in nature. Now, after that, so can we say this shows, say isomerism? Answer is yes, it can show geometrical isomerism. If you are having like this is having A, this is having A, this is having B, this is having B, it will not show geometrical isomerism. Similarly, if you are having C double bond C, this is having A, this is having A, this is having B, this is having D, this will also not show geometrical isomerism because these are different but these are same. So, if you are having C double bond C, here it is A, here it is B, here it is D, here it is E. So, these 2 groups are different, these 2 groups are different. It can also show geometrical isomerism. Now, in case of alkenes, geometrical isomerism is basically of 2 types. One is cis trans, another is EZ. But first of all, we will discuss cis trans And later, after a few minutes, we will discuss EZ isomerism. Now, let me show you that if you are having an alkene like this, if you are having an alkene like this, in which across this carbon-carbon double bond, if you check, because double bond is in this fashion, if you check this A and A, identical groups, similar groups are on same side of this carbon-carbon double bond, and similar types of B are present on same side of this double bond. We call this isomer as simply cis isomer, you know that. Similarly, if we are having C double bond C, then we will be having A and B in this fashion, then B and A in this fashion. Then across carbon-carbon double bond, have a look, across carbon-carbon double bond, A and A, they are on opposite side, and B and B, they are on opposite side. We call this as trans isomer. So that geometrical isomer in which identical groups are present on same side of carbon-carbon double bond is cis, and in which similar or identical groups are present on opposite side of carbon-carbon double bond is known as trans. Similarly, if you are having carbon-carbon double bond like this, then you are having A and B, different groups. You are having A and B like this. Have a look. Across carbon-carbon double bond, I will form a line over here, imaginary line. Now AA and BB, that means identical groups are present on the same side. So this is cis. Similarly, if I write C double bond C over here like this, this is A, this is B, then this is A and this is B. What is this? This will be simply a trans isomer. So this is very, very, very easy. Cis and trans is very easy. So I hope you can find out which one is cis and which one is trans. Let me know in the chats, can you find out cis and trans easily? Can you find out cis and trans easily? Let me know clearly. Let me know quickly in the chats. So that if you know cis and trans, so we will not waste much time on cis and trans then. Can you find out cis and trans easily in case of alkenes? In case of alkenes. Okay, that is clear. Thank you very much. After that, we will be having GI in azo compounds. What are azo compounds? Azo compounds is this, N double bond N. Now, say for example, we have, say for example, PH and PH. Phenyl groups are attached to this, and another is the lone pair. So here, lone pair will act as a group. Remember, so these are two different groups. These are two different groups. When lone pair acts as a group, we use syn and anti instead of cis and trans. Have a look. So lone pair on the same side of this, say restricted rotation, where restricted rotation is there, that means N double bond N. Similar groups are on the same side. So we call this as syn, because we use syn instead of cis if lone pair acts as a what we call group. Similarly, N double bond N, this is like this. This is the lone pair and this is the lone pair. Not necessary that lone pair is shown, but it is simply this identical groups are on opposite side across this nitrogen, double bond nitrogen. So we will call this as NT. So instead of cis and trans, we use syn and NT if lone pair acts as a group. So this is what we call GO in azo compounds. After that, GI in oximes. Have a look. Oximes are of two types. One oxime is this one, in which this carbon is having one hydrogen. This is known as aldoxime, in which this carbon attached to double bond nitrogen is having one hydrogen, is known as aldoxime. And another type is in which there is no hydrogen attached to this carbon. No hydrogen is attached to this carbon. This is known as ketoxime. This is aldoxime. What you have to check, have a look. You have to check simply hydrogen and OH. Hydrogen of carbon attached to nitrogen with a double bond, and OH attached to nitrogen which forms a double bond with carbon. If they are on the same side, of carbon double bond nitrogen, then we call that aldoxime as syn aldoxime, syn side. Why syn? Once again syn, because lone pair acts as a group. Similarly, if you are having C double bond N, lone pair acts as a group, you have to use syn or NT, syn NT. Now, have a look. Across carbon nitrogen double bond, check where is OH and where is H. They are on opposite side. Hence, this aldoxyme is known as NT. So, in case of aldoxymes, you have to find out the position of H and OH. If they are on the same side, this is syn. If they are on opposite side, then NT. But in case of ketoxymes, you have to remember, if you write the name like this is methyl, this is phenyl. If you write down methyl first and then phenyl and then ketoxyme, remember. Similarly, if you write phenyl first, then methyl, and after that ketoxyme. Have a look, my dear lovely students. In case of ketoxyme, the group written first, the group which is written first, you have to check position of that. That means if this is the name of this compound, you have to check methyl and you have to check OH. That means position of methyl and OH, you have to check. Methyl and OH, they are opposite. So this is NT. So this is NT, methyl phenyl ketoxyme, or same compound is like this. You have to check the group written first is phenyl. Now you have to check position of phenyl with ketoxyme. Have a look. Listen carefully. So for this, you have to check OH and CH3. So you will write down this. Let me change the color. Let me change the color of this. You have to check now OH and pH. Here, as they are on the same side, so this is syn. So now, is this syn or NT? That depends on which group is written first. If methyl is written first, you have to check position of methyl and OH, that is NT. If phenyl is written first, you have to check position of phenyl and OH, and that is syn. I hope this is clear. This is for aldoxyme, this is for ketoxyme. After that, in case of cycloalkane, remember my dear lovely students, have a look. Whenever you are having cycloalkane, whether it is 3-membered ring, whether it is 4-membered ring, whether it is 5-membered ring, whether it is 6-membered ring, whether it is 7, 8, 9, 10, I mean say you can use any ring. But what you have to remember is there must be 2 sp3 hybridized carbons. Remember, I will write down over here. There must be at least 2 sp3 hybridized carbon. 2 sp3 hybridized carbons should be present. And on these two different groups should be present. 2 groups, or I will write down 2 different groups should be present. 2 different groups should be present. On each sp3 carbon. So first of all, there must be at least 2 sp3 carbon. Here 3 sp3 carbons are there. But what is the group attached to this? Hydrogen. So here hydrogen, similar groups. Here hydrogen, similar groups. Hydrogen, similar groups. So there will be no what we call GI. But if it is like this, it is A, this is B. One sp3 is having 2 different groups. But this is having HH. No, this will not show what we call GI. So at least there must be 2 groups. Whether those groups are adjacent, whether those groups are, say far away from each other, hardly matters. But there must be 2 sp3 groups. This is one sp3 group. This is another sp3 carbon, say. And to this sp3 there must be 2 groups different. And to this there must be 2 groups different. Now, these groups are both above the plane and these groups are both below the plane. As both are above groups are similar, below groups are similar. So we can call this as cis, not syn, because here no lone pair will act as a group. Now, what will be the trans form of this will be simply like this. Its transform will be, this is A, this is B, then this is B, this is A. Above and below, identical, below and above, identical. So this is trans. In nutshell, cis and trans is possible only, this will not show cis and trans, this will not show cis and trans, this will not show cis and trans until and unless two groups, two sp3 carbons are there, and each sp3 carbon must have two different groups. I hope this is clear to each and every one. This is very, very, very important point. This is very, very important point. You have to remember this. You have to remember this. You have to remember this. This is very, very, very important. So let me erase this. Let me erase this. Let me write down over here, for example, this one. This is A, this is B. It will not show. It will not show. Say, for example, I will write down this is A, this is B, then this is A, this is A. It will not show because this is sp3 attached to two groups, sp3 attached to two groups, but these are different, these are same. They will not show. Similarly, this is A, this is A, this is B, this is B. It will not show. Or if I write like this, this is A, this is B, this is D, this is E. So it can show, but it will not show cis trans. Then which type of, say isomerism can it show? That is secondary. But first of all, we have to think about cis and trans. So for cis and trans, it must have at least two sp3 carbons, and to each sp3 carbon, two groups should be present and both should be different from each other. So these are two different groups, these are two different groups. I hope this is clear. Let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Let me know, my dear lovely students. Let me know quickly, am I clear till now? Sharon, yes sir. Envy, yes sir, yes sir. Clear sir, yes sir. Okay, that's great, clear sir, yes sir. Okay, nice. After that, we will be having GI in endocyclic double bonds in cycloalkenes. What is meant by that? Listen carefully. First of all, you must know that GI is absent in endocyclic double bonds in cycloalkenes up to 7-membered ring. Point number 1. Point number 2. GI is present in 8-membered in endocyclic double bond of cycloalkene from 8-membered and onwards. And remember, from 8 to 11-membered rings, it is cis form which is more stable than trans, and from 12-membered and onwards, stability order will be trans greater than cis. This is the stability order. Now, have a look. Actually, if you form a 3-membered ring like this, this is the endocyclic double bond. this endocyclic double bond is having, say for example, hydrogen and hydrogen. Both these hydrogens are present on the same side. So this can form cis, but it cannot form trans. So cis trans, that means geometrical isomerism, is not possible, as trans form is not possible. Similarly, this is having hydrogen, say for example, and hydrogen on the same side. So cis is present, not trans. Similarly, 5, 6, 7, it's not possible. But for 8-membered ring, you can form a double bond over here like this. It is actually possible. It is actually possible. Now, if this is 1, 2, 3, 4, 5, 6, 7, and 8, this is possible. Here, hydrogen and hydrogen can be, possible. Opposite, that means trans is possible. So this is trans form. And similarly, we can have a cis form as well like this. You can have a cis form, say for example like this. You can have a cis form like this. So this is hydrogen and this is hydrogen. So this is cis alkene. So 8-membered can form cis as well as trans up to 11. But remember, in trans there will be strain as compared to cis. That's why from 8 to 11 cis is more stable than trans. But from 12-membered rings or onwards, that means if size of ring is increased, so there will be no strain after that. That's why 12 is always, from 12 and onwards, trans is always more stable than cis. Now, the question is, when you are having double bond as well as you are having a cyclic ring, you have to look towards double bond, whether this double bond shows this what we call GI or not, and you have to check, is there any carbon which is sp3, and if you are having two sp3 hybridized carbon, and to these sp3 hybridized carbon, each sp3 hybridized carbon has two different groups, then it can show what we call GI at double bond as well as ring. So you have to check that. So let me show that with the help of, that type of, question later on. But first of all, you have to check GI in cumulines. What are cumulines? Cumulines are those compounds in which pi bonds are present at adjacent position. For example, you are having a pi bond like this. This is having cumuline containing even number of pi bonds. But remember, my dear lovely students, cumuline having even number of pi bond always contains these two groups. Say for example, this is A and B different groups, this is A and B different group, whether they are same, whether they are different, but they are always present in different plane. That means they are perpendicular with respect to each other. That means these all groups are not present within the same plane. Hence, remember, GI in cumulines with even number of pi bonds, is always absent. Even number of pi bonds is always absent. Remember this, is always absent. Why? Because we know one of the conditions for GI is that these two groups and these two groups all should be present within the same plane, but they are in different plane. That means these two are in one plane and these two are in another plane. So let us suppose these two are present on the board, but this is above the plane, perpendicular to the board, and that is below the plane, that means perpendicular to the board. These are on the board, these two are perpendicular, present in perpendicular plane, that means they are at 90 degree with respect to each other. But if you are having a cumuline with odd number, with odd number of pi bonds, then remember, this is point number 1, you have to remember this, and point number 2 you have to remember is GI in cumulines with odd number of pi bond, is present. But for that we have condition, is present if each end center has two different groups. If each end center has two different groups. Have a look. If this is A, this is B, this is the end center, this is the end center, these are the two end centers, this is A, this is B, all are present in the same plane. Remember, they are in same plane. If they are present in same plane, restricted rotation is there. That means all conditions are there. Only you have to check whether this end position, or I mean say terminal position, is this end center having two different groups, end center having different groups. So you can simply say GI is present. But what about this? This is odd number of pi bonds are there. So this is A, this is B, this is B, this is B. It will not show GI because they are different, but here they are same. So here it must be different, as well as the groups present at this should also be different. That's why it will show, it will not show. Similarly, if I write down like this, A and A, here it is, say for example, B and B, it will not show. Why? Because groups present at this center are different, similarly, Similarly, groups present at this end center is similar. But we must have groups present at this end center different, groups present at this end center different. I hope this is clear till now. After that, similar, even, odd story can be used in spirons. But what are spirons? Spirons are basically series of spiro compounds. And what are spiro compounds? Spiro compounds are those bicyclic compounds which contain at least one atom common between two rings. Have a look. Have a look. This is the simplest spiron. This is having two rings. In between, this is the atom which is common. Now, what is the end center? End center is this one. This carbon is the end center, because from this position ring starts and ring ends at this position. If this is having similar or different centers, hardly matters. What matters is you have to remember these are perpendicular with respect to each other. So you have to simply remember this point, that GI in spiro compounds or spirons, in spirons with even number of rings, with even number of rings, with even number of rings is always absent, because it's not fulfilling all the conditions of GI. So it's always absent. Remember this. Like that of I mean say cumulains. But if you are having a spiro compound in which number of rings is odd, at that time you have to check only end center. That means this center and this center, end center. If each end center has different groups, remember these, I mean say spirons have basically all four groups in same plane. So what you have to remember is that it shows. So what you have to remember is this, that GI in spirons with, I mean say odd number, with odd number of rings can show GI if there is condition. What is that condition? If each end center has two different groups. If each end center has two different groups. That means if this is having different groups, this is having different group, yes, this can show. If these are having similar, or from this side or from both sides, that will not show. That will not show. Say for example, this one. This one will not show, I mean to say GI. So it will not show GI. Why? Why it will not show GI? Because this end center is having same groups, hence it will not show GI. I hope this is clear. After that, it is GI in substituted biphenyls. Have a look. Have a look. This is phenyl. This is phenyl. But if you are having a substituted biphenyl like this, say for example, this is G, this is G prime, this is G double prime, let us suppose, and this is G triple prime. Suppose these are the groups which are bulky. If bulky groups are there, there will be repulsion. So when groups are present within the same plane and they are closer to each other, there will be repulsion. And because of that, to minimize repulsion, they will rotate about sigma bond to minimize repulsion. That's why they will rotate about this bond, this sigma bond, they will rotate. Now, after rotation, these groups are present in one plane, these groups are present in second plane, so there will be less repulsion, hence they are present basically in different plane. If they are present in different plane, so can I say substituted biphenyls can never show, say GI, because group attached to this is one group and this is second group. Similarly, this is third group and this is fourth group. So 4 groups at 2 end centers are not present within the same plane, hence GI is absent. So we can simply say GI is absent because all these 4 groups are not present within the same plane. After that, my dear lovely students, GI in terphenyls, but ter means 3 phenyl rings are there, but substituted terphenyls. Let us suppose like this. Let us have a group like this. Have a look, my dear lovely students. If this is a bulky group, say for example A, this is bulky group, for example B, this is bulky group, say for example A, this is bulky group, for example B, this is say for example having A, this is having B, this is having A, this is having B. So what will happen? These bulky groups will repel with each other, and to minimize repulsion, these 2 groups will, these 2 rings will be now perpendicular to each other. Similarly, these 2 will be perpendicular to each other, but these 2 will be in same plane. That means first and third ring will be present in the same plane. First and second will be in different plane. Second and third will be in different plane. What about this? What about this? Can you say this end center is having 2 different groups? This end center is having 2 different groups. Similarly, this end center is having 2 different groups. As first of all, these all 4 groups are present in within the same plane, because rings are present in the same plane, so groups are present within the same plane. But this is having different group, this is having different group. Hence, GI is present. Here, GI is present. I hope this is clear. So, can I say here isomerism occurs because of restricted rotation as a result of steric repulsion. Here isomerism occurs, but due to what we call restricted rotation between them, because they show GI, and GI is possible only if there is restricted rotation between this and this. So there is restricted rotation. So isomerism arises here due to restricted rotation, but this restricted rotation takes place only because of steric repulsion. Why? Have a look. When these 2 repel each other, they will migrate, they will rotate. Once they will rotate, they will be present in now different plane. They will never come to the same plane, because they know if they come to the same plane, there will be repulsion. So rotation is restricted. They will be always there in different plane. So rotation is restricted. So can I say isomerism occurs due to restricted rotation as a result of steric repulsion, and this type of isomerism is known as atrop isomerism. Remember, atrop isomerism. So what is atrop isomerism actually? Atrop isomerism actually means isomerism which arises due to restricted rotation as a result of steric repulsion. So here basically rotation becomes restricted. Now rotation, they will not rotate, this single bond the rings will not rotate about single bond because of steric repulsion. So rotation becomes restricted, and after that, if isomerism arises due to restricted rotation, this is known as atrop isomerism. So this will show GI, and here atrop isomerism is present. Now after that, which can show GI? Have a look. This is having similar groups, so it will not show GI. Here, these are having 2 different groups, so this will show GI. What about this, my dear lovely students? Have a look. These groups are different, but what about this? So you can draw an imaginary line across carbon-carbon double bond. Have a look. These 2 are different, but these 2 are similar, so there will be no GI. Now, Here, across carbon-carbon double bond, there will be GI because these two are different and this part is different, so GI is present. Across this carbon-carbon double bond, you know H and H, so I will simply say across this carbon-carbon double bond, there will be no GI. But have a look, there is a ring also, and this carbon is sp3, this carbon is sp3. To this Cl, obviously hidden hydrogen is also there. That means two different groups are present. Similarly, two different groups are present. So I can simply say around this carbon-carbon single bond, there will be what we call GI, hence this molecule shows GI. Because whenever you are having a ring as well as double bond, you have to check double bond, you have to check a ring as well. And at double bond, it is like this. But at a ring, you have to check two sp3 carbon atoms. And if each sp3 carbon atom is having two different groups, then it will show GI at that time. Have a look, have a look. What about this? This is 1, 2, 3. This is odd number of pi bond cumulene. But end centers are having same groups, hence it will not show GI. It will not show GI. What about this? 6-membered ring, endocyclic double bond, never shows GI. This ring never shows GI. This ring never shows GI because we need at least two sp3 carbon to which two different groups are attached. But what about this double bond? What about this double bond? Have a look. This is having double bonded side, this is having single bonded side, different groups across this. Similarly, this having side in which Cl is attached, side in which no Cl is attached. Hence, this will show GI. What about this? This is 10-membered ring. 10-membered ring, double bond can show GI. This is cis, we can form its trans as well. So that means this can show cis and trans, GI. Now have a look. Across this double bond, we cannot say that GI is present. Why? Because this and this is similar. Similarly, this and this is similar. So there is no GI. But if you look towards this carbon and this carbon, both are sp3, and to this H and Br is present. Here H and Br is present. That means these are two different groups. These are two different groups. Hence, across this carbon-carbon single bond, GI is present. Hence, we will say molecule can show GI. I hope this is clear. Now, this is spiro compounds with even number of ring. So, in this spiro compound with even number of ring, GI is absent. But, with respect to this and this carbon, with respect to this and this carbon, this is having I and H, this is having I and H. So, not as per spiro compound is concerned, but as per this carbon-carbon single bond is concerned, here restricted rotation is there, two groups, four groups are present, all are present within the same plane. In nutshell, two sp3 carbons are there, and to these sp3 carbons, different groups are present, hence GI is present, hence GI is present, hence GI is present. Now, minimum number of carbons required to show GI. I am waiting for the reply. What will be the answer? Let me know. Let me know quickly. Let me know in the chats. I am waiting for the answer of this question. Till that, I will take some sip of water. Minimum number of carbons to show GI. For GI, how many carbons are required? How many carbons are required? Someone is saying 4, someone is saying 2. Now, have a look, have a look. Can I say this can show GI? Can I say this can show GI? Can I say this can show GI? Have a look and tell me the answer. Can this compound show GI? Yes, answer is yes. Why? Because this is syn. I can form this like this. This is NT. So one is syn, another is NT. That means the GI. But in this compound, there is no carbon, there is no carbon. So what will be the answer? Answer is 0. So no need of carbon to show GI. But minimum number of carbons required to show GI in alkenes. If it is alkene, then it can be 4, because whenever we talk about alkene, that means we must have carbon and hydrogens only. We must have carbon and hydrogens only. So this is cis form. For GI, we must have at least 4 carbons. But in alkenes, so remember, answer is 4. We must have 4 carbons for GI, but in alkenes. What about number of GI in alkanes? Minimum number of in cycloalkanes. This is cycloalkane. Simplest cycloalkane is this. But we need, I mean to say, that cycloalkane which is made up of only carbon and hydrogen. So have a look. This is cis form. This is trans form. This is cis form and this is trans form. So minimum number of carbons required. 3, 4 and 5. So we need minimum number of carbons required will be 5 if we talk about GI in cycloalkanes. After that, we talk about cycloalkenes. How many? Because cycloalkene, this is the cycloalkene, but this double bond will not show what we call GI. Let me form this ring in this fashion. Now, but if I write down like this, but we have to write only carbon and hydrogen, not chlorine, not any other group, only carbon and hydrogen. That how many carbons minimum? So this is cis with respect to this and this, not with respect to this, with respect to this. Similarly, we will be having trans, not with respect to double bond, but with respect to this one. This is H, this is CH3, this is CH3, this is H. So CH3 and CH3 here, H and H here, they are trans. So we need at least 6 carbons. We need at least 6 carbons as per cycloalkenes are concerned. After that, we will be having EZ isomerism. Have a look. E basically comes from a German word, means that German word is Engagement, and it means across or opposite. It means across, or we can say opposite. But what should be opposite? Similarly, Z comes from a word zusammen. These are the German words basically. Means same side, which means opposite side, and which means together are same side. What? Identical priorities. Identical priorities across 2 GI centers. So for example, if we talk about alkenes, say for example 2 GI centers are like this. If we are having priority groups like this, this is having priority 1 group, this is having another group having priority 2. This is having highest priority. 1 means highest priority and 2 means lowest priority. Similarly 1 and 2. So can I say across carbon-carbon double bond, or we can simply say across, say 2 GI centers, 1, 1. Identical priorities are on the same side, and 2, 2. That means identical priorities are on the same side. So this is what we call Z isomer. Similarly, if we have first priority and second priority in this fashion, that second and second are opposite, first and first are opposite across, say for example 2 GI centers, not necessary carbon-carbon double bond, then we call this as E isomer. So one is E, that means opposite, and another is Z, that means on the same side, but opposite identical priorities. Opposite identical priorities, then E. Identical priorities on the same side, then we call this as Z. Now, for that purpose, we must know to, for priorities, we must know CIP rules. C means can, I means INROLL, and pre means prelog. That means can, INROLL, and prelog. These were these 3 scientists who gave basically sequence rules with the help of which we can find out priority. So Khan, INROLL and Prelog. With the help of these, we find out, I mean to say, priority. But after that, who told that when 1, 1 or 2, 2, I mean say highest priority and lowest priority are on the same side, it is Z, and if it is on opposite side, it's E. It was not Khan, INROLL and Prelog who gave E and Z name. E and Z name was given by Blackwood. But with the help of Khan, INROLL, Prelog, I mean say CIP rules. Now, rule number 1 is, if you are having GI center like this, if you are having two, I mean say centers at which GI is possible, suppose GI centers are these two, and the groups attached to them is like I, this is BR. Now tell me, the group attached to this is I and BR, that means they are different. That means they are having different atomic number. The group which is having highest atomic number is given first priority, and group which is having lowest atomic number is given lowest priority. That means it is directly proportional to atomic number. Similarly, if you are having like this, F and this is having Cl. Cl is having priority 1, fluorine is having priority 2 because it's having highest atomic number as compared to this. So first you have to check 2 groups on one center, then you have to check 2 groups on another center. Now, have a look. 1 and 1, they are opposite, 2 and 2, they are opposite, that means identical groups are on opposite sides, so this is simply E. Similarly, you can write down. You can write down like this. Say for example, this is I, this is Br. This is what we call Cl and this is F. So this is 1, priority number 1, atomic number highest means highest priority. So among these 1, 2, and among these, this is 1, this is 2. After that, my dear student, have a look. 1, 1 is on the same side, 2, 2 is on the same side. So this is what we call Z. So can we say this is easy isomerism? Yes? Yes, this is easy because this is E and this is Z. And as this is really very easy, so easy is not a difficult one. Now, after that, we will be having second rule. And what is second rule? Have a look. Second rule is like this. Second rule is like this. Very, very simple. Very, very, very simple. Now, first of all, these are the 2 GI centers. Now tell me, to these GI centers, what is attached over here? It is carbon. It's carbon. Groups are different, but similar atoms are attached. If groups are different, similar atoms are attached, then what to do? Then we know atomic number will be same. Then what to do? We have to, go to second atom then. Now, what are the other atoms attached to this? This is H, H and H. Form a set over here. Now, after that, what are the atoms over here? H, H and C. Because to this, 3 atoms attached are H, H and C. But among these, which is having highest atomic number? First it is C, then it is H, then it is H. Now compare. This is H, this is C. First point of difference is there. So whose atomic number is highest? Carbon or hydrogen? Carbon. Carbon is part of this. That means this will become 1, this will become 2. After this, have a look. This is carbon, this is carbon. Similar atoms of different groups are attached. Then, atom next to these atoms is considered. Here, which are the atoms? Fluorine, fluorine and chlorine. But chlorine is having highest atomic number. So write chlorine first and then fluorine. Here, chlorine first and then fluorine. Compare these. Now, can I say this chlorine and this chlorine, they are same. Chlorine and chlorine are same. Chlorine and chlorine are same. So there will be no point of difference at all. But this fluorine and this chlorine, they are different. Chlorine is having higher atomic number as compared to fluorine. Chlorine is part of this. So this will become 1. This will become 2. So can I say? Have a look. 1 and 1, they are on the same side. 2, 2 on the same side. Hence, this is what we call Z. This is Z. Now, let me know in the chats if I am clear till now. Let me know in the chats if I am clear till now. Exactly, it is Z. At the rate of Sharon, exactly. You are very, very, very correct. Let me know quickly. Am I clear till now? At the rate of Shafkat. Thank you. Thanks for replying at the rate of universe, at the rate of Supriya. Thank you. Thank you all. Thank you all. Thank you all. Thank you all. Yeah, there will be break after this chapter. After this chapter, there will be break. After completing geometrical isomerism, there will be break because your optical isomerism is not the part of 11, that is part of 12th chemistry, and that will be discussed in 12th chemistry. I mean to say day after tomorrow, that means on Saturday, most probably, or yes, or day after tomorrow, that means Saturday. We will be completing optical isomerism, alcohol, phenol, ether, haloalkane, haloarine, aldehyde, ketone, carboxylic acids, amines, diazonium salts, biomolecules, each and everything. Now, okay, that is clear, that is clear. Now, what about this? What about this? This is C double bond C. For example, this is having CCl3, this is having CCl2 and F. Then this is having C, say for example, CH3, this is having CH2, and then it is having Cl. Now, have a look, have a look, have a look. This is the similar atom attached to this center. After that, Cl, Cl and Cl, different atoms. Then, I mean say, next atom will be Cl. Here, next atom will be Cl, after that Cl, after that F. Have a look, Cl and Cl, they are same. There will be no point of difference, no point of difference. Now, Cl and F, there is point of difference. Cl is having highest atomic number as compared to F. So, this is 1, this is 2. What about this? This is carbon, this is carbon. After that, it is having H, H and H. This is having Cl, H and H. So there will be first point of difference will be this. Cl is having highest atomic number. So this is 1, this is 2. And if you look towards this carbon-carbon double bond, now 1, 1, 2, 2, they are on opposite side, hence this is E. So this is E isomer. I hope this is clear. I hope this is clear. After that, another is that if isotopes are attached to GI center, at that time priority is directly proportional to mass number. This is very, very simple. Say if you are having C double bond C, here it is H and D. Now, both are having similar atomic number, so you cannot differentiate these two by atomic number, so that's why mass number. Deuterium is having higher mass number, so it's 1, it is having 2. Similarly, if you are having this I and Br over here, I is having higher atomic number, this is having lower atomic number. So highest priority, lowest priority. So this is on the base of atomic number, this is on the base of mass number. So 2, 2, 1, 1 opposites, hence this is E. Similarly, if you are having C double bond C, it's having D and this is having H, this is having I and this is having Br. We know we can differentiate this on the base of rule number 1, atomic number, but we cannot differentiate this on rule number 1 or 2. So that's why I will write down mass number according to mass number, rule number 3, 1 and 2. 1, 1, 2, 2 on the same side. So this is Z. So one is E, another is Z. This is very, very easy. After that, if you are having like this, if your GI center is such that groups attached to GI center contains what we call a double bond or a triple bond already, then what will happen? You have to duplicate each atom which forms double bond and you have to triplicate each atom which forms triple bond. How to duplicate or triplicate? Have a look. Have a look. First of all, I will not change this one. I will write down this as such. This is I and here it is Br because it is not forming double bond or a triple bond. After that, this is the GI center. At this center, I will write down CH and double bond will be converted to single bond. Have a look. And I will mark that carbon and oxygen which forms double bond. But first they were formed 2 bonds. Now they were formed 1 bond only. That means 1 bond of carbon has been decreased. 1 bond of oxygen has been decreased. So form 1 bond of carbon, form 1 bond of oxygen. But here carbon forms 2 bonds with oxygen. Here carbon forms 2 bonds, one with 1 oxygen and another with another oxygen. This oxygen, this atom is basically that atom which we have added after duplication. This is known as phantom atom. Try to satisfy the valency of phantom atom by hydrogen. So we know oxygen forms 2 bonds. That's why I will give 1 more hydrogen to this. This is actual atom which was present. This is phantom atom which we have added. Oxygen forms two bonds with this carbon. So this is one bond with carbon, this is another bond with carbon. But this is actual carbon, this is phantom carbon. Now, we know carbon forms 4 bonds. Here it is only 1. Give 3 hydrogen to this because we have to satisfy valency of phantom atom. Okay, so this is phantom atom. Similarly, right over here, it is C single bond N and mark actual atoms. We know carbon forms 3 bonds with nitrogen, form 3 single bonds over here and give 3 nitrogens to this. These two are phantom nitrogens or phantom atoms. Try to satisfy the valency. This is the actual nitrogen. It forms 3 bonds with carbon. Now you have to form 3 sigma bonds. Now instead of double bond you have to form 2 bonds. Instead of triple bond you have to form 3 bonds. So nitrogen forms 3 bonds with carbon. Now in this, nitrogen forms only 1 bond with this carbon. So this can form 2 more bonds with carbon, but these are phantom carbons. You have to satisfy the valency. Now have a look. This is the carbon attached to, this GI center. This is the carbon attached to GI center. After that, this is oxygen, oxygen and hydrogen which are attached basically. So can I say any atom attached to this atom is oxygen? When it is duplicated, you have to write down it twice. So OO and then this one, H. So this is basically the atoms attached to this carbon. What about this carbon? Carbon is attached to 3 other nitrogens. That means, as we know, it forms a triple bond with this nitrogen. So remember, this will be nitrogen, nitrogen and nitrogen in nutshell. So carbon, carbon, they were same. Have a look. Carbon, carbon were same. But after that, it's oxygen. After that, it's nitrogen. Oxygen and nitrogen, which will be having more atomic number. Oxygen, so this will become 1, this will become 2. After that, this is 1, this is 2. It's very clear. 1, 1, 2, 2 on the same side, so it is Z. Very, very, very simple. In general, you can say, whenever you are having a triple bond, say for example between A and B, you are having a double bond between A and B, and if you are having single bond between A and B, give priority to triple bond, then double bond, then single bond. But if you are having a triple bond between carbon, carbon, and you are having double bond between carbon, nitrogen, give priority to carbon double bond nitrogen. Similarly, if you are having carbon, carbon triple bond, you are having carbon, carbon, carbon double bond oxygen, give priority to oxygen. Because this carbon is attached to 3 carbons, this carbon is attached to 2 oxygens. So oxygen and carbon, this will get preference. So this is in general, or this is what we call a trick. After that, we will be having few compounds and we have to identify E and Z isomers. Have a look, my dear lovely students, have a look. First of all, to this carbon, can I say chlorine and fluorine is attached? So this is 1, this is 2. Bromine and hydrogen is attached. So this is 1, this is 2. After that, have a look. After that, I will draw a line over here, an imaginary line. Have a look. So this line, from left side of this line, 1, 1, 2, 2, they are on same side. So this is simply a Z isomer. Now, this is second, have a look. This is H and this is H. Across carbon, carbon double bond. This is having lone pair of electron, this is having lone pair of electron. Identical groups are on the same side. So this is simply Z. What about this? This is having a lone pair of electron. Now, this is having lone pair of electron. Now, how this is Z, sir? Because remember, lone pair always gets lowest number as compared to any atom. So this is 1, this is 2. Similarly, this is 1, this is 2. As lone pair does not have any proton, so its atomic number will be always lowest. Now, this is having, this is 1, this is 2. But this is carbon and hydrogen. So this is 1, this is 2. So across carbon, carbon, double bond nitrogen, what will happen over here? Have a look. What will happen over here? Here, 1, 2. That means 1, 1 on opposite side, 2, 2 on opposite side. So this is E. This is simply E. What about this? What about this, my dear lovely students? You can use cis trans over here, but you can use EZ everywhere. Whether it is cis trans, whether it is syn NT, you can use EZ everywhere. But you cannot use cis trans or syn NT everywhere. Have a look, have a look. If we talk about this carbon-carbon double bond, once it's carbon, this is hydrogen, hydrogen and carbon, 1 and this is 2. Carbon and hydrogen. Carbon is having atomic number, higher atomic number as compared to hydrogen. So 1, 1 on the same side, 2, 2 on the same side. So we will call this as Z, or we can simply say this is cis isomer. After that, have a look. If we talk about this, one is chlorine, another is hydrogen. Among chlorine and hydrogen, chlorine gets number 1 and hydrogen will get number 2. So chlorine number 1, hydrogen number 2. So on, I mean say this line, I mean say geometrical isomer center. You have to check across GI center. 2, 2 on the same side, 1, 1 on the same side. So this is simply Z. This is simply Z. This will not show GI, this will not show GI. So we have to check GI over here. This is carbon-carbon triple bond. So this will get number 1, this is carbon-carbon double bond. This will get number 2. Triple bond will get number 1, triple bond as compared to double bond if triple bond and double bond is present between similar elements. Now this is 1, this is 2. So 1, 1, 2, 2 on opposite side. So this is E. Now have a look. Here it is hydrogen. Here it is hydrogen. So this carbon will get 1 and this hydrogen will get 2. This hydrogen will get 2. This carbon will get 1. So 1, 1 opposite, 2, 2 opposite. So this is E. Similarly, what about this one? This is hydrogen. This will get 1. Hydrogen will get 2. Similarly, this is hydrogen. So this will get 1. This will get 2. So 2, 2 on the same side. 1, 1 on the same side. So this is Z. So one is E, another is Z. What about this? What about this? Have a look. This is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen. Now, across this carbon-carbon double bond, this is 1, this is 2. Across this carbon-carbon double bond, this one is 1, this is 2. So 1, 1 on the same side, 2, 2 on the same side, so this is Z. What about this carbon-carbon double bond? This is 2 and this side is 1. This is 2 and this side is 1. 2, 2 on the same side, 1, 1 is on the same side, so this is Z. Very, very simple. Similarly, you can write this is E, this is Z. This is E and this is E. This is E and this is E. Similarly, this is C double bond O. That means O will be duplicated, O and H. This is N and N. So O and N. O will get number 1, N will get number 2. Similarly, this is C and C because triplicate. You have to triplicate this carbon and you have to triplicate nitrogen. So which one will get number 1? It will get number 1, it will get number 2. So 1, 1 opposite, 2, 2 opposite. So this is E. Now let me know in the chats if I am clear till now. Let me know quickly. Is this clear till now? Let me know in the chats quickly. Let me know in the chats quickly. Am I clear till now? Am I clear till now? Let me know. Let me know. Let me know quickly. Let me know quickly, my dear lovely students. Let me know quickly. Let me know quickly. Yes. Okay. At the rate of Kingi, at the rate of Shafkat, at the rate of Supriya. That's great. That's great. At the rate of Grumpy. Thank you. Thanks for responding. Thank you, everyone. Thank you. Thank you. Thank you. After that, calculation of GI. Remember. You have to remember in case of unsymmetrical species, remember number of GI will be simply 2 raised to the power n. What is n? N means number of GI areas. I mean say number of restricted areas, those areas due to which GI takes place. This is number 1. In case of symmetrical species, number of GI is equal to 2 raised to the power n minus 1 plus 2 raised to the power p minus 1. Now, if n is even, if number of geometrical areas are even, at that time p is equal to n by 2, and if n is odd, then p is equal to n plus 1 divided by 2. So these are the two formulas which you have to remember, Number 1 is this one. You have to remember this. And another is this one. But for this, you have to remember this one as well. If n is even, then p is equal, because you have to substitute the value of p over here. Now, have a look and tell me what will be the answer. First of all, here will be no GI. So if GI is absent, so no need to calculate total number of geometrical isomers. This is what we call cumulene with odd number, and in odd number you have to check, say this position and this position. Say end centers. That means that center, that atom from which double bond starts and that atom to which double bond ends. So cumulene, odd number. This is having H and CH3. This is having H and CH3. That means from this position to this position, as GI is present, so N is 1. Whenever N is 1, total GI, so GI, number of GI will be simply 2. No need to write down the formula. No need to write down formula if n is 1. But if n is more than 1, you have to at that time check whether the molecule is symmetrical, unsymmetrical. If it is symmetrical, is n having even number or odd number, you have to use formula accordingly. Have a look. Here GI is possible, here GI is possible, here GI is possible. But we can have a look. This molecule can be divided into 2 equal halves. That means this is symmetrical. So I will simply say n here is equal to 1, 2 and 3, and molecule is symmetrical. And molecule is symmetrical. So n3 means n is basically odd. So calculate first p. P is equal to n plus 1 divided by 2. That means 3 plus 1 divided by 2. So value of P is 2. Now use number of geometrical isomer will be, use formula, use this formula, use this formula. It is 2 raised power n minus 1. N was 3. So 3 minus 1 is 2. 2 raised power 2 is 4. P is 2. 2 minus 1 is 1. 2 raised power 1 is 2. That means 4 plus 2. Answer is 6. So simply it's having 6 answers. So number of geometrical isomers here will be 6. This is once again having 1, 2 and 3, but this is unsymmetrical. N is 3 but unsymmetrical. If n is 3 and unsymmetrical, you have to write down 2 raised power n. That means number of geometrical isomers will be simply 8. Here, there will be no GI at this double bond, but this double bond, this sp3 and sp3 is having two different groups. So GI center is only 1. When n is 1, no need to calculate formula. Number of GI will be simply what we call 2. Here, GI will be possible over here. GI is possible at this double bond, as well as at this odd cumulene. Similarly, GI is possible at this sp3 center, because this is having H and this group different. This is having H and this group different. That means GI is also possible at this center. So how many GI centers are there? GI areas are there. 1, 2, 3, 4, 5. That means n here is 5 and it is unsymmetrical. It is unsymmetrical. So we can simply say that number of GI will be simply 2 raised to the power 5. Answer is 32. Answer is 32. I hope this is clear till now. After that, there is differentiation between cis and trans on the basis of physical properties. Remember, cis in general, trans molecules are more symmetrical than cis. Hence, their packing will be more closer. That means their melting point will be more. So trans in general is having more melting point as compared to cis, because there is more force of attraction because of more close packing. Obviously, if they are closely packed, that means their volume will be less. Volume will be less, that means density will be more, because density is inversely proportional to volume. So it is trans greater than cis. Next is lattice energy. What is lattice energy? Amount of energy required to, break a crystal lattice into its constituent particles. So if we want to break crystal lattice of trans, we need much more energy. That means simply it is trans which is having lattice energy more as compared to cis. Now, dipole moment, it gives basically information about polarity of the molecule. In general, few trans molecules are more, having more dipole moment as compared to cis, but in general, it is cis whose dipole moment is more as compared to trans. So we will write down cis as compared to trans, because in trans dipole moment will be subtracted, because groups are opposite with respect to each other in general, but there are few molecules as well in which trans shows much more dipole moment as compared to cis. So more dipole moment means cis molecules are more polar, and they are more polar and having less force of attraction with respect to each other. Their solubility will be obviously more. So cis are more soluble as compared to trans. And as we know, cis molecules are more polar, so their boiling point will be more. So more polar, more boiling point. So cis greater than trans. So this was all about geometrical isomerism. Now, after half an hour, we will try to discuss hydrocarbons now. So let's have a break of half an hour at least. Let's meet at 6, so that we will discuss, or we will try to complete hydrocarbon, and then after that we will be having last part of this previous year questions, and if time permits, after that we will discuss qualitative as well as quantitative analysis. Now have a look. So this was all about GI. But remember, optical isomerism is part of 12th chemistry. I hope we will go according to NCERT textbook, because NCERT textbook is very, very important for us. Go according to NCERT textbook. My dear students, NCERT is very, very, very important for you. You have to check each and every example of NCERT as well. So let us start hydrocarbons, but at 6. So now we will be having a break till 6 p.m. So at that time, we will be discussing hydrocarbons. So till then, take care and bye-bye. But I would want you all guys to be back at 6 p.m. because most of the questions will be asked from hydrocarbons. Hello and welcome back again. Am I audible and visible? Let me know in the chats. Am I audible and visible? Let me know in the chats. Let me know in the chats quickly. Am I audible and visible? Hello, hello, beta. Okay. Am I audible and visible? Let me know quickly in the chats. Let me know quickly. Let me know quickly. Okay. So, we will be discussing another chapter. We have already completed IUPAC nomenclature. We have completed GOC and isomerism. Now, we will be discussing hydrocarbons. First, you have methods of preparation of alkanes, and in this, first reaction is like this. First reaction is from unsaturated hydrocarbons. This is unsaturated hydrocarbon. This is unsaturated hydrocarbon. This is not unsaturation hydrocarbon. This is unsaturated hydrocarbon. Give me a second. From unsaturated hydrocarbon, that means you have to form saturated hydrocarbon alkane from either alkene or alkyne. How to form? Have a look. How to form this? From unsaturated hydrocarbons. Have a look. You want to form an alkane from this. You want to form an alkane from this. What you have to do is you simply break one pi bond and add hydrogen. Break this bond and add hydrogens to this. That means hydrogen is added, but remember, this is addition of hydrogen means reduction or what we call hydrogenation taking place in presence of catalyst. Say this is platinum or palladium or Raney nickel. You can use platinum, palladium or Raney nickel. Or you can use nickel but at high temperature. When alkene or alkyne are converted to, say alkane, by using ordinary nickel at high temperature, reaction is known as Sabatier-Senderon's reaction. Sabatier-Senderon's reaction. In alkyne, what you have to do is you have to break two pi bonds and you have to add two hydrogens to this carbon, two hydrogens to this carbon. In nutshell, you will get alkane. So from alkyne, we need two moles of hydrogen to form alkane, and from alkene you need 1 mole of hydrogen to form alkane. So hydrogenation, remember this, hydrogenation by using nickel at high temperature, approximately 573 to 623 Kelvin at high temperature is called Sabatier-Senderon's reaction. It's called Sabatier-Senderon's reaction. And this reaction can be used to synthesize vanaspati ghee from edible vegetable oils. Very, very simple reaction. You have to add H by breaking pi bond. So this is very, very simple reaction, and addition of hydrogen takes place from the same side. This is syn addition reaction. After that, we will be having another reaction from alkyl halides. We will be having another reaction that is from alkyl halides. First, by reducing alkyl halide to alkane. That means if you are having an alkyl halide, when you are having CX bond, what you have to do is you have to replace X by H. You have to replace X by H. Now, what are the reagents with the help of which CX bond is converted to CH bond? That means with the help of which X can be replaced by hydrogen. What are the reducing agents? Remember, number one is zinc in presence of acid, say for example HCl, or it's not necessarily zinc, it can be active metal. Example is zinc. Similarly, zinc in acetic acid, say for example. Similarly, you can use zinc copper couple in alcohol. Similarly, you can use zinc in NaOH, or you can use Hi in red phosphorus as well. So there are many reducing agents, but you just remember these reducing agents with the help of which we can convert alkyl halide to alkane. Just replace X by means of H. After that, my dear lovely students, there is another reaction, that is a reaction of alkyl halide with metals, and first metal is magnesium. What will magnesium do over here? Whenever you are having magnesium and CX bond is there, magnesium always gets incorporated between C and X bond, and it will result in the formation of RMgX, known as alkyl magnesium halide, which is a Grignard's reagent. This is an organometallic compound because carbon and metal bond is there. So in this Grignard's reagent, this is having partial negative charge, this is having partial positive charge. Whenever this Grignard reagent is treated with any acidic hydrogen containing compound, it can be water, it can be alcohol, it can be phenol, it can be HCl, it can be terminal alkyne, it can be carboxylic acid, any. But say for example, I am giving only one example over here. So whenever Grignard's reagent is treated with any acidic hydrogen containing compound, this Grignard reagent will accept hydrogen from this, and it will result in the formation of an alkane, plus it is Mg, which is having X, and OH will be attached to this. So this reaction, from which Grignard's reagent on treatment with any acidic hydrogen containing compound resulting in the formation of alkane, is known as Zary-Vatanov's reaction. So this reaction is Zary-Vatanov's reaction. It's not necessary that you use water, you can use alcohol, you can use phenol, you can use HCl, you can use carboxylic acid, you can use ammonia, you can use any acid which can donate H positive. So it will act here as a base, it will act here as an acid. So this is an acid-base reaction, so it will act as acid-base reaction. Okay, now after that, reaction with sodium. Whenever alkyl halide is treated with sodium, reaction is known as Wurtz reaction. Reaction is known as Wurtz reaction. Now, what will happen during Wurtz reaction? Have a look. If you are having an alkyl halide and it is treated with sodium, that means only one type of alkyl halide is there. If it is treated with sodium, reaction takes place generally in dry ether. What will happen? What you have to do is just break CX bond, form a radical over here, and couple this radical with similar type of radical. That means dimerization will take place, and it will result in the formation of an alkane plus NaX. Similar type of reaction you can write down like this. It is Rx plus sodium. If you want to balance the reaction, then you can write down like this. Whenever sodium and CX bond is there, remember forever, you have to break CX bond. So after breaking CX bond, it will result in the formation of a radical. It will result in the formation of a radical. Radical will combine, it will form an alkane. And then twice NaX will be formed. So this type of Wurtz reaction taking place between two similar type of molecules is known as simple or self-intermolecular, what we call Wurtz reaction. Then this is one example. Another example can be like this. If you are having an alkyl halide and it is treated with different alkyl halide, say two different alkyl halides, let us suppose R is not equal to R prime. That means two different alkyl halides are treated with sodium in presence of dry ether. What will happen at this time? Remember, this will form a radical, that means R prime radical. This will form a radical, that means R radical. That means two different type of radicals are formed. Hence, three different combinations will be possible for coupling. So, one will be RR, another will be R prime, and another will be R prime. And side product will be obviously NaX. So, RR is formed from similar type of radical, combination of similar type of radical. This is formed by similar type of combination of similar type of radical. This is formed by combination of different type of radical. This is always a minor product during what we call Wurtz reaction. And this type of product can never be obtained alone. Whenever this product is formed, it will be formed with other alkanes as well. That means this is formed only during, in what we call Wurtz reaction in mixture form. That means in impure form. Now have a look. Different type of radical, different alkyl halides undergo Wurtz reaction. So this is intermolecular, but different type of molecules undergo Wurtz reaction. This is known as what we call mixed or crossed intermolecular Wurtz reaction. You can take an example of CH3Cl, CH3Br, CH3CH2Br. You can take different examples over here and you can form the product. Similarly, if you are having, my dear lovely students, an example like this, if you are having example like this, that means you are having a dihalide and then it is treated with sodium in presence of dry ether. What will happen? This will form a radical, this will form a radical, this radical and radical will combine together. So here intramolecular Wurtz reaction will take place. But you have to note down few things. Number one, during Wurtz reaction, methane cannot be obtained. Methane cannot be obtained during normal Wurtz reaction. Cannot be obtained during normal Wurtz reaction. This is point number one. Point number second, tertiary alkyl halides do not show this reaction. Number third point, this reaction is considered as best method to prepare symmetrical alkane because whenever unsymmetrical alkane generally, or you can simply remember those alkanes which are formed by combination of two similar type of radicals, this is considered as better method to prepare that. For example, if you are having say for example CH3Br, this upon Wurtz reaction results in the formation of what? This will result in the formation of a methyl radical, so it will result in the formation of ethane. So that means dimerization of this radical takes place. Similarly, if you are having CH3Br and CH3CH2Br, that means different type of radicals when combined together, different type of alkyl halides when combined together and during Wurtz reaction, what will happen? It will result in the formation of methyl radical and this will result in the formation of ethyl radical. Both these radicals can combine in three different ways. So we can get ethane, we can get N-butane over here, and we can get propane. But we can form this with the help of this reaction. We can form N-butane if we treat ethyl bromide with sodium. That means this and this can be formed separately, but this can never be formed separately because this has been formed by combining different radicals. So this is formed only and only in impure form. So this will be the minor product of this reaction. After that, if you are having 1,3-dibromocyclobutane, for example, and it undergoes Wurtz reaction, what will happen over here? This bond will be broken, radical will be formed, such type of radicals, they will combine together and they will form this bicyclic compound. So this was all about what we call Wurtz reaction. After that, we will be having another reaction, reaction with zinc. Basically, whenever alkyl halide reacts with zinc, it first results in the formation of, whenever alkyl halide reacts with zinc, basically they result in the formation of Frankland's reagent. I mean to say, it results in the formation of Zn, R and R. R2Zn. This is known as Frankland's reagent. After that, this Frankland's reagent, on treatment with alkyl halide once again, what will happen? This R will attack, or this R and this X will be lost. That means this will be simply an SN2 reaction and we will get RR, that means a symmetrical alkane. And this reaction is known as Frankland's reaction. This is known as Frankland's reaction. So you can use simply a trick like this whenever you are having alkyl halide and it is treated with zinc. So this is the trick. Just break this bond, form a radical and combine this radical with similar type of radical. That means RR will be the product. But this is not basically the correct way, but this is the trick with the help of which you can solve the question easily. For example, if you are having CH3Br and it is treated with zinc. So what will happen? What will be the product? Product will be CH3, simply. But this alkyl halide can never be a tertiary alkyl halide because this is an SN2 reaction with the help of which finally alkane is obtained. After that, we will be having a reaction of alkyl halide with Gilman's reagent. What is Gilman's reagent? Gilman's reagent means this one. Lithium dialkyl cuprate or lithium dialkyl copper. When this is treated with alkyl halide, this alkyl halide can be similar, value of R can be similar or it can be different depending upon the value of this R prime. Now this will attack over this R and X minus will be lost. That means it is simply an SN2 reaction where R and R prime will be formed. That means R prime will be formed. That means an alkane will be formed. After that, it is RCU and LIX side products. But this alkane can be symmetrical. It can be unsymmetrical as well. But we know during Wurtz's reaction or Frankland's reaction, generally symmetrical alkanes are obtained. Here, symmetrical as well as unsymmetrical can be obtained. So, to prepare unsymmetrical alkane, Wurtz's reaction is not the good method. Frankland's reaction is not good method. This is the best method among these three. So, can I say to prepare unsymmetrical alkane, unsymmetrical alkane. This reaction is known as Corey-Haas reaction. So Corey-Haas reaction is preferred over Wurtz and what we call Frankland's reaction. So this is known as Corey-Haas reaction. For example, if this is having CH3Cu CH3, this is having CH3X, then CH3CH3 will be the product. If this is having CH3Cu CH3 Li, then this is having CH3CH2X, then CH3CH2 CH3 will be the product. Very, very easy reaction. So reaction of Gilman's reagent, that means lithium dialkyl cuprate with alkyl halide, is known as Corey-Haas reaction. After that, a reaction of alkyl halide with metal hydrides. Have a look. If you are having an alkyl halide and this alkyl halide is treated with, either lithium aluminium hydride or sodium borohydride or triphenyl tin hydride, remember it results in the formation of alkane, but you have to remember few points. Number one, if alkyl halide is 1 degree alkyl halide, if alkyl halide is 1 degree alkyl halide, then it is basically sodium borohydride. There will be no alkane formation. That means sodium borohydride cannot reduce 1 degree alkyl halide. Similarly, if it is 3 degree alkyl halide, remember lithium aluminium hydride cannot form alkane, but instead of that, no alkane is obtained. Instead of that, alkene is formed. That means triphenyl tin hydride can convert primary, secondary, tertiary to alkane, but sodium borohydride can convert secondary and tertiary to alkane by replacing X, but lithium aluminium hydride can convert primary and secondary alkyl halide to alkane by replacing H. After that, we will be having another reaction that is from aldehydes and ketones. How can we convert aldehydes and ketones? Remember, how can we convert aldehydes and ketones to CH2? Either by reduction by using HI in red phosphorus, or, my dear lovely students, you can use zinc amalgam in acidic medium, say for example HCl, And this reaction is known as Clemmensen reduction. Clemmensen's reduction. So aldehyde or ketone C double bond O is converted to CH2. Similarly, C double bond O is converted to CH2. Just remember, you have to convert C double bond O to CH2 by using N2H4, that means NH2NH2, hydrazine in basic medium and at high temperature, plus N2. This is known as Wolff-Kishner reduction. Wolff-Kishner reduction. That means Wolff-Kishner reduction is conversion of C double bond O of aldehyde or ketone to CH2 in basic medium, and this is in acidic medium. But sometimes other part of this aldehyde and ketone is acid sensitive. If it is acid sensitive, that means if that can react with acid, then it is preferable at that time. Basic, Wolff-Kishner reduction is preferable at that time. So if it is acid sensitive, do reduction in basic medium. If it is basic sensitive, do reduction in acidic medium. Okay. After that, we will be having another reaction that is from carboxylic acids. We will be having another reaction that is from carboxylic acids, that means by decarboxylation, and simple decarboxylation is by using soda lime. What we have to do is have a look. If we are having carboxylic acid, first of all, acid is treated with base, say for example NaOH. What will happen? OH will abstract this H and it will result in the formation of sodium salt, RCOONA, sodium salt of carboxylic acid. This upon treatment with soda lime means NaOH and CaO in the ratio of 3:1. Now what will happen? Have a look. Just remove this in this fashion. Just remove carbon dioxide in the form of Na2CO3. That means you have to remove carbon dioxide in the form of Na2CO3, and you will result in the formation of RH. And during this, basically carbanion will be formed in rate determining step of the reaction. That means our rate of decarboxylation is actually dependent on the carbanion formed when CONA or COH is removed from this. For example, if you are having CH3COOH and this is treated with soda lime, NaOH, CaO, heat, what you have to do is just remove this, form a carbanion and give H to this. That means it will result in the formation of CH4. Similarly, if you are having CH3CH2COH, what you have to do is remove this, form a carbanion. This is the carbanion. Now, after that, add H to this. It will result in the formation of CH3CH3. But suppose this reaction is having rate R1, this is having a rate R2. I mean, say whether ethanoic acid or propanoic acid, which one will decarboxylate very fast? That depends on the stability of carbanion formed in RDS. Have a look. That depends on this carbanion. This forms methyl carbanion, this forms ethyl carbanion. We know this is more stable as compared to this. So remember, if this is its rate is R1, its rate is R2, we will simply say R1 will be faster as compared to R2. Because here carbanion is more stable as compared to this one. I hope this is clear to each and every one there. After that, we will be having another reaction, and that reaction is Kolb's electrolysis. What you have to do is simply either you take sodium salt or a potassium salt of carboxylic acid and then treat it with water and then electrolysis, then electrolyze it. So during electrolysis, what will happen over here? Have a look. Whether it is carboxylic acid, whether it is sodium salt, whether it is potassium salt, remove this one and form a radical over here. Combine this radical with another radical, that means alkane will be formed at anode. Similarly, carbon dioxide will be removed as a gas. This will be formed once again at anode. Hydrogen gas will be evolved but at cathode. You have to remember these. And in our solution, there will be NaOH. If it is RCONA, if it is K, then KOH. So I will write down twice NaOH. So this is the balancing of the reaction. So solution will be basic. That means solution will be having pH greater than 7. But here you have to remember, if this R is HCOONA, that means if it is sodium salt of formic acid, sodium formate, then what will happen over here? Then during this reaction, there will be no alkane formation at anode. There will be hydrogen gas which will be evolved at anode as well as cathode. Carbon dioxide will be evolved at anode, but hydrogen here will be evolved at anode as well as cathode. At anode as well as cathode. And obviously pH of solution will be greater than 7 because of formation of NaOH in the solution. But if you write CH3CONA, what will be the product? CH3 radical will combine and that will form ethane. Methane is once again not formed during this reaction. Very, very, very easy reaction. After that, we will be having chemical, reactions of haloalkane. But before that, let me know in the chats if I am clear till now. If I am clear till now, let me know in the chat so that we will start halogenation, chemical reactions of alkanes. Let me know in the chats if I am clear till now. Because this is the session which will help in your revision, which will help in your basics as well. And this is the, as your time is very less, this is the way you have to revise your organic chemistry. Okay, everything is clear. Everything is clear. Now, after this, have a look. Halogenation. What is meant by halogenation? It is simply reaction of alkane with halogen taking place in presence of light or heat. Taking place in presence of light or heat. What will happen over here? H will be replaced by X. That means this will be simply a free radical substitution reaction. So this reaction is simply free radical substitution reaction. Free radical substitution reaction. So intermediate of this reaction is free radical. So this is a free radical substitution reaction. Point number one. Point number second is among halogens, reactivity order will be simply fluorine, which is very, very reactive than chlorine. Chlorine is more reactive than bromine, and bromine is very reactive than iodine. And among halogens, you have to remember reactivity order will be obviously in every free radical reaction. It will be 3 degree hydrogen, greater than 2 degree hydrogen, greater than 1 degree hydrogen. Now after this, if X is Cl, then it is simply known as what we call chlorination. So if you are having chlorination of alkane, now what will happen? Suppose you are having CH4 and then it is treated with Cl2. What will happen? H will be replaced by Cl. H will be replaced by Cl simply. So the product will be CH3Cl plus HCl. But once CH3Cl is formed, if Cl2 is taken in excess, it will further react. And it will result in the formation of CH2Cl2 plus HCl. After that, this CH2Cl2 will further react with Cl2 and it will result in the formation of CHCl3 and HCl. Then this CHCl3 will further react with Cl2 and it will result in the formation of CCl4. Then reaction will stop. In nutshell, we can say simply like this. If methane is taken in is treated with Cl2, and suppose this chlorine is taken in excess, then what will be the major product? What will be the major product? Major product will be CCl4. First CH3Cl is formed, then CH2Cl2 is formed, then CHCl3 is formed. Finally, CCl4 is formed and it will be the major product. But if methane is taken in excess, at that time, remember, if methane is taken in excess, at that time methyl chloride will be the major product. And how many monochlorone products will be formed from an alkane? That depends on how many different types of hydrogens are present in alkane. Methane is having only one different type of hydrogen. That's why only one type of alkane is formed. Suppose you are having a reaction like this. Suppose you are having a reaction like this. This is CH3, this is CH3, and this is CH3. 1, 2, 3, 4. That means 2-methyl butane is there. And if it is treated with Cl2 in presence of what we call light, or it is treated in presence of heat, what we have to do is, first of all, we have to find out different types of carbons. So these are similar type of carbons. This is different, this is different, this is different. So we have 4 different types of carbons, hence we have 4 different types of hydrogens. How to check whether the carbon is same or different? You have to check 4 different groups attached to this carbon. Similarly, 4 different groups attached to this carbon, 4 different groups attached to this carbon. So this is very, very simple. So remove 1 hydrogen of a carbon, say type A hydrogen, replace 1 hydrogen by Cl. So product will be like this. It will be Cl, CH2, and then it will be like this. Similarly, second product will be like this. Second product will be like this. It is CH3, this is CH3, this is CH3, and here it will be Cl. So this is type A product, this is type B product. After that, type C product will be like this. Type C product will be like this. This is CH3, here it will be Cl, it is CH3, it will be CH3. So this is type C. Type D product will be like this. CH3, CH3. I mean to say this is, say type D product. Now, how many products are formed excluding stereoisomers over here? Have a look. Excluding stereoisomers, 4 products are formed. 4 products are formed. 4 monochloro products are formed. But including stereoisomers, 6 products will be formed. How? Have a look. As this carbon is a chiral carbon, similarly, we will be having this as a chiral center or a chiral carbon. Now, this chiral center is having one product this, another its image, that means enantiomer. Similarly, this is having one product this, another its image, that means 2 and 2, 4, 5 and 6. In total, we will be having 6 products. Okay. If we will talk about bromination, bromination takes place in similar manner as that of chlorination. Only 2 things will be different. Say takes place in similar manner. Takes place in similar manner as that of chlorination. But only one thing you have to remember is it's more selective than chlorination. What is meant by that? That means whenever bromination of alkane takes place, major product will be always formed from more stable carbon-free radical. That means tertiary carbon-free radical will form more stable product. But in chlorination, sometimes more stable carbon-free radical form major product, sometimes lesser than that can form major product. So here it will be always from more stable carbon-free radical. Next is 3-degree hydrogen is more reactive than 2-degree hydrogen, is more reactive than 1-degree hydrogen. But as per chlorination is concerned, ratio will be 5.35 is to 3.8 is to 1. This is with respect to chlorine. But with respect to bromine, it's 1600 is to 82 is to 1. That means if similar reaction takes place, but here instead of chlorine, we use bromine, then this B will be the major product. So during bromination, B will be major product, but during this chlorination, B is not the major product. You can check, most probably, yes, it is C which acts as a major product. So B is not the major product, C is major product here in chlorination, but in bromination, as this is the selective reaction, in bromination, previous example gives B as the major product, because that is formed from more stable carbon free radical. Have a look. If you remove Cl, this is tertiary carbon free radical, this is secondary carbon free radical. Tertiary is more stable, so product formed from this during bromination will be major product. After that, you have to remember one more thing, that is fluorination. Direct fluorination of alkane is not possible. Remember this. Direct fluorination is not possible. Direct fluorination is not possible because reaction is not possible, because reaction is too violent to be controlled. It's too violent to be controlled. Similarly, after that, if we talk about iodination, direct iodination of alkane is not possible. Direct iodination of alkane is not possible because reaction is reversible. Because reaction is reversible due to formation of HI, which acts as a reducing agent, and converts alkyl iodide back to corresponding alkane. So have a look. That means if you take methane and treat methane with iodine, reaction is reversible because first it results in the formation of methyl iodide and HI. HI will act as a reducing agent. It will convert this alkyl iodide back to alkane. So if you want to perform iodination of alkane, then reaction should be irreversible, and reaction should be irreversible only if HI formed is removed, and that is possible in presence of strong oxidizing agents like HNO3, HiO3 or HiO4. Similarly, you can use HGO. So this is all about halogenation of alkane. After that, we will be having another reaction, that is combustion, and combustion is of two types. One is complete combustion and another is what we call incomplete combustion. During complete combustion, what will happen? Hydrocarbon on treatment with oxygen results in the formation of carbon dioxide, and water. It's a large amount of heat is evolved as well. For example, if you use, say X as 1 and Y as 4, that means it is CH4, which results with CH4 upon treatment with say twice O2 gives what we call carbon dioxide, 1 times carbon dioxide and twice water, and tremendous amount of heat. So remember, as tremendous amount of heat is evolved, so no need to write down value of this. So tremendous amount, or due to due to evolution of large amount of heat during combustion, hydrocarbons can act as fuel. Hydrocarbons can be used as fuel. After that, we will be having an incomplete combustion like this. Say, for example, you are having methane. Obviously, this is a gas, and oxygen gas in limited supply of air. What will happen? It will result in the formation of carbon black, that means solid, plus, say, for example, water, and that too to ice, that means liquid state. This carbon black is used in the manufacture of, ink. We can say printer ink. We can say filters. We can say black pigments, etc. So it can be used in the manufacture of these. After that, after combustion, we will be having another, that is controlled oxidation. What will happen during controlled oxidation? Have a look. If you are having an alkane, suppose you are having an alkane like this, and this upon oxidation in presence of copper at a temperature of 573 Kelvin, 100 atmospheric pressure, upon oxidation in presence of this, you have to replace one H by one OH. That means your product will be an alcohol. Replace one H by one OH, product will be alcohol. If similar type of alkane, say for example like this, is treated with molybdenum oxide, say for example MO2O3, and it's heated, then replace two hydrogens from same carbon by two OH groups. But we know two OH groups to the same carbon they are not stable. They will lose water and result in the formation of aldehyde. If alkane is treated with manganese acetate, CH3COO2 Mn, then replace three hydrogens by three OH groups, but from the same carbon. Then if three OH groups are attached to the same carbon, two OH groups will lose water because they are unstable. Then it will result in the formation of carboxylic acid. And remember, KMNO4 does not oxidize alkane until and unless alkane contains a tertiary hydrogen. So whenever alkane is having tertiary hydrogen, then KMNO4 will oxidize that. So KMNO4 oxidizes only that alkane which contains a tertiary hydrogen, and it will convert that into an alcohol directly. So it will replace H by OH, but only tertiary hydrogen is oxidized. That means tertiary hydrogen is replaced by OH. After that, we will be having another reaction, that is nitration. Remember, normally alkanes do not undergo nitration, but if alkane and HNO3, fuming HNO3, if I mean to say alkane and nitric acid, fumes are passed together at high temperature, approximately up to 673 Kelvin, 423 to 673 Kelvin, high temperature. Here, vapor phase nitration will take place, and what will happen? CH bond is cleaved as well as CC bond will be cleaved, and this will be a free radical substitution reaction. And if CC bond is cleaved, C radical, CH3 radical will be formed, to that NO2 will be attached, and if CH bond is broken, then it will result in the formation of CH3 CH2 radical, and NO2 will be attached to this. That means mixture of nitroalkanes will be obtained. After that, it's a free radical reaction. Once again, 3 degree hydrogen will be more reactive than 2 degree, will be reactive than 1 degree hydrogen. After that, we will be having sulfonation. This reaction is shown by that normal alkane which contains at least 6 carbons, or our alkane must contain at least one tertiary hydrogen. After that, when this is treated with when this is treated with sulfuric acid at high temperature, sulfuric acid at high temperature, say for example 773 Kelvin, once again a free radical substitution will be taking place. H will be replaced by SO3H. That means introduction of SO3H, I mean say sulfonic acid group, is taking place. That's why this is known as sulfonation. This is once again a free radical reaction. After that, isomerization. Isomerization means that phenomenon during which isomers will be obtained. Say for example, if you are having butane without any, I mean to say, branch. So butane upon treatment with AlCl3 and HCl at high temperature, what will happen? It will result in the formation of, I mean say, 2-methyl propane. So N-butane will give 2-methyl propane. Both are having, I mean to say, similar molecular formula but different structure, and its structure differ in chain. Hence chain isomers basically will be obtained during this reaction. Okay, after that we will be having aromatization. And just remember forever, if you are having N-hexane, 1, 2, 3, 4, 5 and 6, 1, 2, 3, 4, 5, 6, N-hexane, because this reaction is shown by those alkanes which contain at least 6 carbons. N-hexane on treatment with Cr2O3, I mean say an oxidizing agent, or V2O5 means oxidizing agent, or MO2O3, that means an oxidizing agent, any oxidizing agent supported over by alumina at 773 Kelvin, I mean say high temperature and 10 to 20 atmospheric pressure. What will happen over here? It will result in the formation of benzene. N-hexane gives benzene. Remember this one. And 4 hydrogen moles will be, I mean say, lost. So this is dehydrogenation, cyclization, that means oxidation as well. So N-hexane will give benzene. Remember N-heptane or 2-methyl hexane or 2-methyl hexane, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. These, upon similar conditions, will form toluene. And if we are having N-octane, under similar conditions can form ethyl benzene and its isomers like 1,2-dimethyl benzene known as orthoxylene, 1,3-dimethyl benzene known as metaxylene, and 1,4-dimethyl benzene known as paraxylene. Obviously with 4 times H2 molecule. So this is aromatization, as aromatic compounds are obtained. After that, we will be having a reaction of alkane with steam. That means when you treat alkane, for example, CH4 with steam, that means water, at high temperature, in presence of a catalyst, say for example nickel, at a temperature of approximately 1273 Kelvin, what will happen? Carbon monoxide will be obtained and hydrogen will be also formed over here. After that, pyrolysis. What is meant by pyrolysis? Pyrolysis is basically thermal decomposition, breakdown of higher alkane to lower alkanes with the help of heat. So pyrolysis, what will happen during pyrolysis? If you are having an alkane like this, propane, suppose, then this upon treatment at high temperature, let us suppose 773 Kelvin, what will happen? It can form an alkene and hydrogen gas, I mean say hydrogen, or it can also form methane plus ethene. That means, can I say higher alkane is converted to lower alkane and alkenes So during what we call pyrolysis, higher alkanes can be converted to lower alkane and alkene. So this is all about what we call alkane. Now, after this, we will be discussing, we will be completing, I mean to say, methods of preparation of alkene. But before that, let me know in the chats if I am clear till now. Is everything clear till now? Because these are the reactions which you have to remember only. There will be no question which will be difficult from these reactions. There will be simple and to the point question asked from such types of questions like combustion, controlled oxidation, aromatization and all that. Now, let me know quickly, am I clear till now? Let me know quickly, am I clear till now? Asat, thank you, clear sir. What about others? Come on, let me know quickly, am I clear till now? Am I clear till now? Let me know in the chats quickly. Okay, thank you. Thank you. Thanks for responding. Thanks for responding. Thanks for responding. Okay. After this, we will be having methods of preparation of alkene. That means formation of alkene from alkynes, but by partial, what we call hydrogenation. Have a look. If you are having an alkyne like this, and you want to convert this into alkene, that means you have to perform partial reduction or partial hydrogenation. There are two types of, reagents. If you are performing hydrogenation in presence of, if you are performing hydrogenation, that means reduction in presence of palladium carbon or palladium calcium carbonate with small amounts of sulfur or quinoline, this is known as Lindlar's catalyst. You can also use H2 in presence of palladium barium sulfate with small amounts of sulfur or quinoline, but this is known as Rosenmund's catalyst. You can use Rosenmund's catalyst over here as well, or you can use P2 catalyst. P2 catalyst means nickel boride, Ni2B, whether it is Ni2B, whether it is what we call nickel boride. Function of all these is that they will simply break pi bond and add hydrogens, but those hydrogens will be added from the same side. That means here alkene will be formed, but that alkene which is cis alkene. So with the help of this reaction, cis alkene will be obtained and reaction will be stopped. But if you use sodium in ammonia or lithium in ammonia, reaction is known as Birch reduction. Here, hydrogen will be added across this triple bond after breaking one pi bond, but these hydrogens will be added from opposite side. Will be added from opposite side. That means we will get a trans alkene during this reaction. Remember this as well. This is very, very, very simple. After that, we will be having a reaction with the help of which we will be obtaining alkene but from alkyl halides by dehydrohalogenation. Say for example, you are having an alkyl halide like this. Then if it is treated with alcoholic potassium hydroxide and heat. Remember, whenever alcoholic potassium hydroxide and alkyl halide is there, this is a reaction which is known as E2 reaction. What we have to do during E2 reaction, find alpha and beta. Remove halogen from alpha and remove hydrogen from beta. That means dehydrohalogenation, removal of hydrogen and halogen. Then after that, form a double bond between alpha and beta. So this will be the product. Only one product will be formed. But if you are having a reaction like this, have a look. What will be the product over here? This is alpha, this is beta, this is beta. If it is Cl, Bri, what you have to do is, you have to find out how many betas are there. This beta is having 3 hydrogen, this beta is having 2 hydrogen. So with respect to hydrogen, this is poor. With respect to hydrogen, this is rich. Remove hydrogen from this position and form a double bond over here. That means product formed from rich beta position is like this. Product formed from rich beta position is known as Hoffman product, and product formed from poor beta position is known as SADZF product. So this is SADZF. But remember here, major product is SADZF. Until and unless, in case of alkyl halide, you are having F. I mean, say if it is Cl, Bri, form Hoffman and SADZF, SADZF will be major. But if it is F, then you have to find out whether Hoffman is major or SADZF is major. So in case of F, you have to check. Otherwise, if it is Cl, Bri, it will be, I mean, say major product will be what we call always SADZF. But if base is not bulky, this base is not bulky, so major product is this. So how many products are formed? 2 products are formed because 2 different types of hydrogens were present. Suppose if you are having like this, CH3, CH, then F, then CH2, then CH3. What we have to do here is, have a look. If similar type of base is used, what we have to do is, this is alpha, this is beta. Form a carbanion at beta position, suppose at this position and this position, and check which carbanion is more stable. This is primary carbanion, this is secondary carbanion. Generally, primary carbanion is more stable as compared to secondary carbanion until and unless secondary carbanion is stabilized by some other effects like resonance. So, this is more stable. So, product formed from more stable carbanion will be major product. That means here, Hoffman, in this example, Hoffman product will be the major product. So, Hoffman product here will be the major product. So here Hoffman product will be the major product as compared to SADZF, and SADZF will be the minor product. Stable will be always SADZF, but major in this case will be Hoffman and SADZF will be minor product. But if similar, I mean say example is there but little difference is there, instead of CH3 benzene ring is there. And then we will be having, I mean say CH2, then CHF, and then it is CH3. So instead of this CH3, I have written benzene ring over here. Have a look. This is alpha, this is beta, this is beta. What we have to do when it is F as a leaving group, then we have to simply think of carbanion at this and this position. This is primary carbanion, this is secondary carbanion. Generally, primary carbanion is more stable, but here this carbanion is stabilized due to resonance. So this will form a product which is more stable because this carbanion is more stable. So carbanion is more stable, that means product is more stable, because here transition state is basically carbanion-like, but you don't have to think about transition state. You just solve the question like this. So it will result in the formation of CH, CH3. As this product is formed from this is rich, this is rich, this is poor. So product formed from poor is SADZF product. This was rich with respect to hydrogens, and this is poor with respect to hydrogen. So poor will form SADZF, rich will form Hoffman. So this is SADZF, and rich will form this product. Remove hydrogen from this, form a double bond. So it will be resulting in the formation of CH2, CH double bond CH2. So this is Hoffman. But major will be this one, because this carbanion here is more stable as compared to this. And one more thing you have to remember is, among alkyl halides, if halogen is same, at that time it is tertiary, greater than secondary, greater than primary. Among Ri, RBr, RCl and RF, it is Ri, then RBr, then RCl and then RF. Because in this case, leaving group is better. More better the leaving group, more, I mean say faster will be this reaction known as E2 reaction. I hope this is clear till now. After that, we will be having another reaction, that is dehalogenation reaction, but from vicinal dihalides. What is meant by vicinal dihalide? Have a look. This is vicinal dihalide. Simply this is vicinal dihalide. We have to remove this X and X. Now we have to use dehalogenating agent. Simple dehalogenating agent is zinc. So zinc will remove this X and X, and it will result in the formation of an alkene. So remove X and X from both carbons and form a double bond over here. This is also a reaction of This is also an E2 reaction, but you have to simply remember, remove X, form a double bond. That's it. After that, from alcohols by acidic, by acidic dehydration. Have a look. From alcohols by acidic dehydration. If this is an alcohol, suppose, what you have to do is, you have to treat this with acid. Say for example, H positive. Now what will happen? First of all, whether this is H2SO4, whether this is H3PO4, what will happen? This will react with this. It will react with this. Then what will happen? Have a look. It will react with this and it will result, first of all, it will undergo protonation, results in the formation of protonated alcohol. Now, this is a very good living group now. This is the good living group. This was not a good living group. This was a poor living group. Now, it becomes a good living group. After that, this will be lost and it will result in the formation of a carbocation. So, it will be lost in the form of water, and this step is slowest step, hence rate determining step, and it will result in the formation of a carbocation first. Once carbocation is formed, intermediate is carbocation, we have to think of rearrangement. If after rearrangement carbocation becomes more stable, we have to rearrange it. Otherwise, we do not have to rearrange it. We know this is the stable carbocation. It cannot be, after rearrangement, it cannot form more stable carbocation than this. Hence, there will be no rearrangement. Finally, what will happen over here? Have a look. Carbon adjacent to the carbocation. Carbon adjacent to the carbocation will lose H positive. Carbon adjacent to the carbocation will lose H positive and it will form a double bond with carbocation. So H positive will be lost. That means this H positive will act as a catalyst. So what will happen? It will result in the formation of an alkene like this. Now the question is, which alcohol can undergo dehydration much more readily? Remember, rate of dehydration, which alcohol will undergo dehydration much faster? Rate of dehydration is directly proportional to stability of carbocation formed from an alcohol, during RDS. So if alcohol forms more stable, much more stable carbocation, that alcohol will be undergoing dehydration much faster. So among tertiary, secondary and primary alcohol, we can simply say tertiary alcohol undergoes dehydration faster as compared to secondary alcohol, as compared to primary alcohol. This is rate of dehydration among alcohols. Why? Because tertiary alcohol forms much more stable carbocation as compared to secondary, as compared to primary. So rate of dehydration among alcohols will be 3 degree, 2 degree and 1 degree. I hope this is clear. After that, my dear lovely students, we are having chemical reactions of alkenes. Have a look. Alkenes in general show, first of all, electrophilic addition reactions, because these are the characteristic reactions of alkenes and alkynes. So how will they show electrophilic addition reactions? They can show either take place via classical carbocation, or they will take place via non-classical carbocation. Here, rearrangement takes place because classical carbocation means carbocation is having complete positive charge. There, positive charge is not fully developed. So rearrangement can take place. Here. Rearrangement can take place here. So this is point number 1. Here, no rearrangement takes place. No rearrangement takes place. No rearrangement takes place. Now, Which reactions can undergo, I mean to say, classical carbocation mechanism as per your syllabus is concerned. If addition of HX, H2SO4, water to alkene takes place, then you have to form carbocation and you have to check whether, I mean say, rearrangement takes place or not. Now, in this case, simply you have to remember halogenation. That means addition of halogen. Whether it takes place in non-polar solvent or in water. Number second is, I mean say, oxymercuration demercuration reaction. These two reactions are basically taking place via non-classical carbocation. There will be no rearrangement at all. Okay. Let's have one by one these reactions. Let's have a reaction of HX one by one. I mean say addition of HX first. Now, if you are having an alkene like this and you want to add HX, whether it is HCl, HBr, HI, HF, whatever is the, I mean say HX, then what will happen? Mechanism will take place like this, and first of all X minus will be lost, and this will be the rate determining step. Formation of carbocation will take place. Once carbocation takes place, then you have to check whether this carbocation rearranges or not. If after rearrangement it forms more stable carbocation, we have to rearrange it. So rearrange if possible. After that, next step is attack of nucleophile. You have to attack with the help of nucleophile. This is the fast step. Nucleophile will attack carbocation and it will result in the formation of this. And remember, this is an unsymmetrical reagent. When unsymmetrical reagent is added to unsymmetrical substrate, addition takes place according to Markovnikov's rule. So, point number one is, among HX, what will be the reactivity order? First of all, you write down this one. Remember this one: HI, HBr, HCl and HF. First point is this one that you have to remember. This is electrophilic addition reaction. Intermediate is carbocation, so rearrangement can take place. Point number second, when HX is added to unsymmetrical alkene, addition should be according to Markovnikov's rule. So addition should be according to Markovnikov's rule. So what is Markovnikov's rule? Negative part of addendum. That means negative part of addendum means molecule to be added. Here molecule to be added is HX. The negative part of HX means X minus. Negative part of HX means X minus is added to that carbon of carbon-carbon double bond which is having lesser number of hydrogens. But remember, this Markovnikov's addition, I mean say Markovnikov's rule, is not applicable or is not valid if you are having this alkene attached to, I mean say, electron withdrawing group, or alkene is such that it undergoes rearrangement. At that time, Markovnikov's rule is not valid. For example, if you are having an alkene like this, CH3CH double bond CH2, we know, because you must have hold on its mechanism, that's why it's possible. Otherwise, it's not possible that you will write directly. Now remember, here we will use Markovnikov's addition. That means we will form this as the major product. This will be the major product. according to Markovnikov's rule, and this will be the minor product, because this is also possible, but this will be the minor product. This will be the minor product. But major product will be according to Markovnikov's rule. But if you are having an alkene like this, in this alkene, once carbocation is formed, that carbocation can undergo rearrangement. That can undergo rearrangement. That means here HX is added, but not according to Markovnikov's rule. So here major product will be like this. It will be CH3C, then it will be CH3. Here X will be added, and then it will be CH3, and then CH3. This is not the Markovnikov's product. This is the Markovnikov's product, which is major. This is major product, but this is not Markovnikov's product. This is rearranged product. This is rearranged product. This is not the product which is formed according to the definition or statement of Markovnikov's rule. Similarly, if you are having an electron withdrawing group attached to carbon-carbon double bond, and you want to add HX, here negative part should go to this, positive part to this, according to Markovnikov's rule. But here product will be like this. Product will be like this. So remember, in these two cases, Markovnikov's rule is not valid. Markovnikov's rule is not valid. Is not valid. Because Markovnikov's rule is not valid if alkene can undergo rearrangement, or we will having an alkene, we will be having an alkene into which electron withdrawing group is attached. At that time, there will be no Markovnikov's addition. And the question is, which type of alkene can show, say this reaction faster? So remember, among alkenes, rate of this reaction is basically rate of this reaction or any electrophilic addition reaction is directly proportional to stability of carbocation. Remember this point as well, but not after rearrangement, but formed in RDS. Any alkene which can form more stable carbocation during RDS can show electrophilic addition much more faster. Okay. After that, we will be having another reaction, that is addition of H2SO4. Once again, a very simple reaction. What will happen over here? It is an alkene, unsymmetrical alkene. You have to add H2SO4 over here. So I will write down HOSO3H like this, because this is H2SO4. After that, my dear lovely students, add H to this. So first of all, OSO3H minus will be lost. So this is the rate determining step. Formation of carbocation will take place. Rearrange this if possible. After that, first step will be that nucleophile OSO3H minus will attack on this carbocation, and we will get ROSO3H. So on treatment with cold concentrated sulfuric acid, alkyl hydrogen sulfate will be obtained. But if this is further treated with water, if not treated with water, this will be the product. But if it is further treated with water and we boil it, or with boiling water, what will happen? OSO3H will be replaced by OH, and the final product is alcohol. But this is alcohol will be formed only and only if this is treated with water. But if it is not treated with boiling water, product will be alkyl hydrogen sulfate. After that, another reaction is acidic hydration of alkenes. Acidic hydration of alkenes. What will happen over here? Have a look. This is an alkene. This, on treatment with water in presence of acid, whenever water is there, acid is there, both will combine together and they will result in the formation of hydronium ion. So hydronium ion is there from water and H positive. So first of all, H positive will be added to this, water will be lost, and it will result in the formation of a carbocation first. Now rearrange this if possible. After that, this is the rate determining step or slowest step of the reaction. After that, rearrange carbocation if possible, and then finally you have to attack with the nucleophile. As water is in excess, it will act as a nucleophile and it will result in the formation of this one. Finally, my dear lovely students, finally it will lose H positive. It will lose H positive. When it loses H positive, it will result in the formation of alcohol like this. So this is once again an electrophilic addition reaction taking place via carbocation. So there are few alkenes where carbocation is formed. Once after that it undergoes rearrangement and then it will result in the formation of different products or rearranged products. But if there is no rearrangement, product will be according to Markovnikov's statement or Markovnikov's rule. Similarly, another reaction is addition of X2. This is simply taking place either in presence of, have a look, if you are having an alkene and reaction takes place with halogen in presence of CCl4 in non-polar solvents, what you have to do is replace, break pi bond and add halogens. But remember, this halogen addition takes place from opposite side. This is anti-addition reaction. And if this is Br2, if X is Br, that means you have to use at that time Br2. Its color is reddish brown. And the product formed will be then vicinal dibromide. That means that will be a colorless compound. So in nutshell, here we can simply say that decolorization of bromine has been taken place. Hence, this can be used as a test for unsaturation. Similarly, if you use halogenation, if you simply perform halogenation but in presence of water, for example, we can say HOX, then this HO minus, this is having X positive, negative part goes to that carbon-carbon double bond, which is having lesser, hydrogen. So it will result in the formation of halohydrin. Once again, this is an anti-addition reaction, but if X2 and H2 is taken and X2 is equal to bromine, then this is bromine water. Then once again, reddish color is decolorized. So this bromine water can be also used as a test for unsaturation. Whether bromine or bromine water, it can be used as a test for unsaturation. There will be no rearrangement at all. Reaction takes place via cyclic halonium ion. There will be no rearrangement at all. You simply have to break pi bond and add XX if a reaction takes place in non-polar solvent, and if takes place in presence of water, then you have to add OH to that carbon-carbon double bond, which can form more stable carbocation, but you don't have to form carbocation, but which can form more stable carbocation. That means this one, that means lesser, that carbon which is having lesser number of hydrogens, and give X to that carbon-carbon double bond which is having more number of hydrogens. After that, oxymercuration, demercuration. This is indirect hydration of alkene. Remember, this is indirect hydration of alkene. So if you are having like this, if you are having an alkene like this, and after that, my dear lovely students, you are having mercuric acetate, HgOAc whole 2, mercuric acetate and water. Similarly, you are having NaBH4 OH minus. Remember, whenever you saw these, reagents, you have to add water. Add water across carbon-carbon double bond according to Markovnikov's rule. What is Markovnikov's rule? Negative part of water goes to, that means OH goes to that carbon-carbon double bond which is having lesser number of hydrogens. So the product will be like this. Give OH to this and H to this. So this is the product according to Markovnikov's addition. So this is oxymercuration, demercuration, indirect hydration. Now then, another is hydroboration oxidation. Another is hydroboration oxidation of, this is not alkane, this is alkene. This is basically alkene, not alkane. Hydroboration oxidation of alkenes. Now what will happen? Whenever you are having an alkene, and you want to perform hydroboration oxidation, remember reagents only. B2H6 is there or BH3 is there, then THF or heat is there. Number one. Number second, H2O2 OH minus is there. Whenever you saw these types of reagents, you have to add water. Add water across either carbon-carbon double bond or carbon-carbon triple bond. Now it is carbon-carbon double bond over here. So add water according to across carbon-carbon double bond, but according to anti-Markovnikov's rule. According to anti-Markovnikov's rule. Now you have to add water according to anti-Markovnikov's rule. That means we will add negative part to that carbon-carbon double bond which is having more number of hydrogens. So to this. So this is what we call anti-Markovnikov's addition of water to alkene, known as indirect hydration of alkene, known as hydroboration, oxidation of alkene. But remember, here H and OH will be added across carbon-carbon double bond from the same side. If H is added above the plane, then OH will also be added above the plane. If H is added below the plane, OH will be also added below the plane across carbon-carbon double bond. After that, we will be having free radical. We will be having free radical reactions of alkenes. First one is what we call peroxide effect, also known as Kharash effect. This is also known as Kharash effect. This is also known as Kharash effect. And this reaction can be simply understood with the help of this. Say for example, you are having an alkene, unsymmetrical alkene. You want to add HBr to unsymmetrical alkene, but in presence of peroxide. In presence of peroxide. Say for example, you have benzoyl peroxide C6H5, C double bond O, then O, then O, then CO, then C6H5, any peroxide, for example, benzoyl peroxide. Now in absence of peroxide, this reaction is electrophilic addition reaction, and you have to add negative part according to what we call Markovnikov's addition, and intermediate is carbocation. But in presence of peroxide, addition should be anti-Markovnikov addition. Addition should be anti-Markovnikov addition. That means addition should be like this. Br should go to this and H to this one. So anti-Markovnikov's product will be formed. Anti-Markovnikov's product will be formed. And this addition is an example of free radical addition reaction. This is an example of free radical addition reaction. And intermediate of this reaction is free radical, not a carbocation. Intermediate of this reaction is free radical, but not a carbocation. Remember it forever. Remember this forever. Remember, this anti-Markovnikov's product is formed on the basis of more stable carbon free radical. And one more thing, if peroxide is present, HF, HCl, HI is present, there will be no peroxide effect. So peroxide effect or anti-Markovnikov product will be only and only if alkene is unsymmetrical, HBr is there and in presence of peroxide. Otherwise, there will be no anti-Markovnikov's product, or there will be no free radical addition reaction. Otherwise, it will be electrophilic addition reaction taking place. After that, we will be having another, that is allylic halogenation. Allylic halogenation. We will be having another reaction, that is allylic halogenation. Suppose you are having an alkene containing at least one hydrogen at allylic position. Containing at least one hydrogen at allylic position. This on treatment with chlorine in presence of light, or chlorine at high temperature, say for example 773 Kelvin. Then what will happen? Or NCS, I mean to say N-chlorosuccinimide. Then what will happen? Allylic chlorination will take place. That means it will simply cleave CH bond at allylic position, and it will result in the formation of a radical first. Now, once this radical is formed, you have to check its other resonating structures as well. And if I form another resonating structure that's also the similar type of radical, finally Cl will be attached to this, and it will be simply allylic halogenation. If Cl2 is there, in presence of light or heat, allylic halogenation, but in absence of, light or heat, that means in darkness, you have to break pi bond and add halogen to that. Okay. If similar type of reaction takes place, but reagents are slightly different. Say for example, reagents are, suppose instead of chlorine, bromine is there. In presence of light, or what we call in presence of high temperature, or NBS, N-bromosuccinimide, then it is allylic bromination which takes place instead of allylic chlorination. Here HCl will be the side product, here HBr will be the side product. But you cannot use fluorine because that is too violent to be controlled. You cannot use iodine because HI will be formed and that will convert a reaction back. That means that at that time reaction will be reversible. Similarly, instead of this, you can use sulfuryl chloride, SO2Cl2, in presence of light and heat. Then allylic chlorination can also take place. So this was all about halogenation or free radical reactions. By the way, this reaction is an example of free radical substitution reaction. This is an example of free radical substitution reaction. After that, we will be having ozonolysis. We will be having ozonolysis of alkene. First ozonolysis is reductive ozonolysis. Have a look. What you have to do is, if you are having an alkene, any alkene, whether it's having HH, whether it's having CH3, any group can be attached to this. If you are having an alkene, then what you have to do is simply you have to do reduction, first ozonolysis with the help of O3. Then if it is zinc H2O, then just cleave this, add double bond O over here. So products will be C double bond O and C double bond O. Sometimes product is given. If sometimes product is given, you have to find out reactant. You have to put these oxygens closer to each other, remove this oxygen and form a double bond. You will get this one. That means whether reaction is, say ozonolysis, whether reaction is retro-ozonolysis, you can form products easily. So in this reaction, reductive ozonolysis, we can get both aldehydes, both ketones, one aldehyde, one ketone. So this is very, very simple. Only you don't have to check what is this. You have to simply replace this, remove this double bond and add oxygen to this. That's it, reductive ozonolysis. After that, we will be having oxidative ozonolysis. During oxidative ozonolysis, what we have to do is, remember, if you are having double bond CH2, if you are having double bond to which double bonded carbon to which two H are there, remember you have to convert this into carbon dioxide and water. You have to convert that into carbon dioxide and water. If you are having double bond CH and then R is there, but R is not equal to H, at that time convert this double bond CH to COH and R is there, so it will result in the formation of RCOH. If you are having double bond C, then R and R, you have to convert this double bond C to double bond O like this, O double bond C, then R and R will be there. That means either we will get ketone, acid, we can get, carbon dioxide, water, anything can happen. Now, have a look. If you are having this one, alkene is this, and after that, it is written ozone, and then it's not zinc, it is H2O or it is H2O2. Then this is oxidative ozonolysis. If zinc is there, then reductive ozonolysis. Now, what we have to do is convert this CH2 into carbon dioxide and water, convert this into carbon dioxide and water. So we will break this and it will result in the formation of twice carbon dioxide and twice water. Similarly, my dear lovely students, if you are having like this CH3CH, double bond CH, single bond CH3, what will be the product over here? What will be the product over here during oxidative ozonolysis? Break this one, convert CH into COH and then R is there, so it will result in the formation of CH3COH. This is also CH3COH, so it is twice. Similarly, if you are having CH3CH, double bond C, CH3 and CH3, what will be the product? You just break this one and convert this CH double bond to COH, so it will become CH3COH. And as this carbon is having R groups, this is not having any, hydrogen, so you have to convert into ketone. So it will be O double bond C, then CH3 and CH3. So in this fashion, you can, say, convert alkenes to different products by using oxidative ozonolysis. Okay. Now, another is oxidation by using hot KMNO4, it's hot KMNO4 or you can say hot K2Cr2O7 or KMNO4H positive, K2Cr2O7H positive. You remember, this is similar reaction as that of oxidative ozonolysis. That means it takes place in similar manner as that of oxidative ozonolysis takes place. Okay, after that, this is oxidation by using Bayer's reagent. What you have to do in this reaction is, this is very, very simple. You have to simply break pi bond, say dilute KMNO4. What is Bayer's reagent? Bayer's reagent is cold dilute alkaline KMNO4 solution. So it is dilute KMNO4. This is Bayer's reagent. Now what you have to do is break CH bond and add OH. That's it. Add OH. But both OH should be added from the same side. Similarly, if you use osmium tetraoxide, product will be same. So by using Bayer's reagent or osmium tetraoxide, we can simply perform syn hydroxylation reaction. Hydroxylation means addition of hydroxyl group across carbon-carbon double bond, but from the same side, that means syn hydroxylation. This is point number 1 regarding this reaction. Point number 2 is, during this reaction, KMNO4, say pink color of KMNO4 is changed to brown precipitate. Brown precipitate of MNO2 is formed. So pink color is decolorized. So with the help of this, you can use it as the test for unsaturation under the name Bayer's test. Okay. After that, we will be having another reaction. Say for example, if you are having an alkene, and if this alkene is treated with per acid, RCOH is acid, so one O is say more in this, so per acid or per oxo acid, number 1, followed by hydrolysis. You have to break pi bond, you have to add OH group. That means once again hydroxylation reaction is this, but this is anti-hydroxylation reaction. Here syn hydroxylation, here anti-hydroxylation reaction takes place. After that, my dear lovely students, there are methods of preparation of alkynes, but before that, let me know in the chats if I am clear till now. Is everything revised till now? If everything is revised till now, let me know in the chats quickly. I will take sip of water. Let me know quickly. Let me know quickly. Is everything revised till now? Is everything clear till now? Show some Josh in the chats as well. If everything is clear, if everything is revised, show some Josh. Thank you, thanks for showing some Josh. That's great. That is great. I'm really very sorry. As you know, I'm not feeling good, but your time is very, very, very important for me. That's the reason I am in front of you taking this long marathon. Now let us start alkynes now. Have a look, have a look, have a look, my dear lovely students, have a look. Have a look. From calcium carbide, we know CaCO3, calcium carbonate, on treatment or on heating decomposes to CaO and carbon dioxide. Once CaO is treated with carbon, then it results in the formation of CaC2 plus, I mean to say, carbon monoxide. Now this CaC2 on treatment with water results in the formation of calcium carbide on treatment with water results in the formation of HC triple bond CH, that means an ethine, acetylene, and plus CaOH whole 2. So with the help of water you can form acetylene or ethine from calcium carbide. After that, another reaction is from vicinal and geminal dihalides. Have a look, my dear lovely students. From vicinal and geminal dihalides. Have a look. If I write vicinal dihalide like this, CH3, CHX and X, like this. This on treatment with alcoholic potassium hydroxide undergoes E2 reaction. It will result in the formation of an E2 reaction. Let me remove this one. Let me write down a simple alkyl halide. Let us suppose CH2X. Now, what will happen? X will be removed from this, hydrogen will be removed from this, so there will be double bond between them. So there will be a vinyl halide formation taking place. But remember, vinyl halide does not undergo another elimination rapidly, conveniently, as this is a very stable product. After that, what we have to do is we will use strong base, more stronger than alcoholic potassium hydroxide. We can also use alcoholic potassium hydroxide, let me tell you that, but reaction will be slower. So to perform another E2 reaction, two consecutive E2 reactions, now we have to remove H and X from this, then it will result in the formation of alkyne like this. So can we use NaNH2 in first step? Answer is no, because in NaNH2, NH2 minus is a strong nucleophile that will replace this X and NH2 will be there. So there will be nucleophilic substitution instead of elimination. So if we want to form alkyne, we have to perform elimination reactions. Similarly, this is first vicinal dihalides. Now if you are having geminal dihalide, like this, what will happen? Similar type of reagents, say first KOH alcoholic, heat, E2 reaction will take place. From alpha position, remove halogen, and from beta, hydrogen. So it will result in the formation of vinyl halide first. After that, this on treatment with NaNH2 and ammonia undergoes another E2 reaction, and it will result in the formation of an alkyne. But remember, my dear lovely students, if this is further treated with NaNH2, then that NaNH2 will act as base that will remove this hydrogen and will result in the formation of a carbanion over here. Remember that as well. So this is the preparation of what we call alkyne from vicinal and geminal dihalides. After that, from halo form, or what we call CHX3. From CHX3, have a look. From CHX3 by dehalogenation. This is CHX3, H, C, and this is X, X, and X. If this is treated with silver, remember this metal is simply a dehalogenating agent, what will happen over here? Simple reaction will take place. This H, this X and Ag, these halogens and Ag will form AgX, AgX, AgX. That means to balance the reaction, it's 6 times. AgX, 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 AgX. This carbon and carbon will form a triple bond over here. So, if sodium is there, it will break CX bond. If zinc is there, it will break CX bond. If Ag is there, it will form CX bond. It will break CX bond. So, it will result in the formation of AgX as well. So, dehalogenation takes place with the help of Ag. So, Ag here will act as a dehalogenating agent. After that, we will be having chemical reactions of alkynes. We will be having chemical reactions of alkynes. First, acidic nature of alkynes. Let me tell you that these reactions are shown by terminal alkynes. These reactions are shown by terminal alkynes. I mean to say those alkynes in which hydrogen is attached to sp hybridized carbon. These are basically acidic hydrogen. This is basically an acidic hydrogen because if it is removed, negative charge is present on most electronegative carbon. Now, if you are having a terminal alkyne like this, known as ethyne, and if you are having terminal alkyne like this, in which there is one acidic hydrogen here, two acidic hydrogens are there. If this is treated with sodium or this is treated with sodium, sodium will act as a base. Sodium will act as a base and it will replace hydrogen. So first it will result in the formation of this one. It will result in the formation of sodium ethanide and it will result in the formation of sodium alkinide. Formation of this sodium alkinide or sodium acetylide means that hydrogen has been replaced, hydrogen has been removed, but after that, hydrogen has been removed. That means one hydrogen has been removed. So I will simply say half of H2 will be removed. Hydrogen will be removed as gas. Half of H2. Okay. This will further react. This will further react with sodium. This will further react with sodium. And another half of H2 will be, lost. And instead of H, Na positive will be there. So it will result in the formation of disodium acetylide. It will result in the formation of disodium acetylide, but it will form monosodium alkinide because it's having only one acidic hydrogen. After that, if similar alkynes are treated with strong bases like NaNH2. What will happen over here? This is Na positive, NH2 minus. This will act as a base. It will abstract this hydrogen. Similarly, it will abstract here this hydrogen. Have a look. And it will result here in the formation of H, C, triple bond C having negative charge and Na positive. Now, this NH2 and H, that means ammonia will be lost. Similarly, NH2 and H, ammonia will be lost. And it will result in the formation of RC triple bond C, negative and Na positive. But as this is having one more acidic hydrogen, this strong base NaNH2 will once again react and it will abstract this hydrogen. But here no acidic hydrogen is there, reaction will stop. But in this case, it will result in the formation of this disodium acetylide and ammonia will be lost. So these products are formed only if hydrogen has been removed. If hydrogen has been removed from terminal alkynes. When terminal alkynes lost H positive, that means they are acidic in nature. That shows acidic character of terminal alkynes. After that, my dear lovely students, if you are having an alkyne like this, if this alkyne is treated with if this alkyne is treated with Toland's reagent, that means Ag, NH3, whole 2 and OH, formed by AgNO3 and NH4OH. That means ammonical silver nitrate solution. What will happen? What will happen? As this is having two hydrogens, acidic hydrogens, let me tell you that it will result in the formation of heavy metal acetylide like this, and its white precipitate will be obtained. So no need to write side products. Similarly, if this is treated with terminal alkyne is treated with Toland's reagent once again, so Toland's reagent can react with this. That means it can show Toland's test, but the only difference is aldehydes, whether aliphatic or aromatic aldehydes, they will show silver mirror test, but this will not show silver mirror test. This will simply show what we call like this. This will simply show a white precipitate over here. So white precipitate will be obtained. But if you use, instead of ammonical silver nitrate solution, if you use ammonical solution of cuprous chloride, then what will happen? Have a look. Have a look. If you use ammonical solution of cuprous chloride, that means if you use CuNH3 whole 2 OH minus, whether it's written like this or written like this, then what we have to do is replace hydrogens, acidic hydrogens, by copper. And copper is heavy metal, so heavy metal acetylide will be obtained over here. But instead of Ag, copper is there, so red precipitate will be obtained. Here we will get red precipitate. We will get red precipitate of this. We will get red precipitate over here. RC, triple bond C having negative charge, and then Cu having a positive charge. That means we will get a red precipitate of this. So this was all about acidic nature of terminal alkynes, because these all are formed when this hydrogen from alkyne has been removed, or if H is lost as H positive. So whenever H is lost as H positive, that clearly indicates terminal alkynes act as an acid. That means acidic nature of terminal alkynes. After that, we will be having addition reactions of alkynes. Have a look. If you are having an alkyne and you want to add, say for example, Hz to this, what will be the formation over here? Have a look. It will form a carbocation first when Z minus will be lost. This is a rate determining step. This will be the rate determining step. But look towards this carbocation. Look towards this carbocation. Look towards this carbocation. This is a vinyl carbocation, less stable carbocation as compared to when alkene forms carbocation. Have a look. Have a look. During alkene, Z minus was lost. Rate determining step forms a carbocation upon protonation, but carbocation was like this. This was alkyl carbocation. And this is vinyl carbocation. Here, positive charge is present on double bonded carbon. Positive charge is present on single bonded carbon. This is less stable. This is less stable compared to that of this, and this is more stable compared to that of vinyl carbocation. So, can we say rate of electrophilic addition reaction is directly proportional to carbocation? So, rate of electrophilic addition reaction among alkynes and alkenes will be always alkenes and then alkynes. Alkenes show much more faster electrophilic addition reactions as compared to alkynes. Now, first addition reaction of alkyne is addition of HX. Now, no need of rearrangement over here, as this will not undergo any rearrangement. So, what we have to do is how to, say, form product directly. Have a look. Have a look. Whenever you are having an unsymmetrical alkyne, first of all, add HX according to Markovnikov's rule. Add HX according to Markovnikov's rule. That means you have to break pi bond and then add negative part to that carbon-carbon triple bond which is having lesser number of hydrogens. That means first of all, you just form this one. It is like this. After that, as pi bond is there, we can add another molecule of HX. Then you can add this in this fashion, simple. Break pi bond and add X to that carbon to which already X is there. So it will result in the formation of geminal dihalide. That means that dihalide in which both the halogens are present to the similar carbon. So this is addition of HX. After that, we will be having another reaction, that is addition of water to alkyne. This reaction is known as Kocharov's reaction. This is known as Kocharov's reaction. Very, very, very simple reaction. Have a look. If you are having an unsymmetrical alkyne and you want to add water, add water according to Markovnikov's rule, but this reaction generally takes place in presence of HgSO4, H2SO4 dilute. Sometimes it's not HgSO4, it is written Hg dipositive. This is one and the same, and at high temperature around 333 Kelvin. Now, what will happen? First, you have to break one pi bond and then you have to add water according to Markovnikov's rule. That means negative part goes to that carbon-carbon triple bond which is having lesser number of hydrogen. This is enol. But we know this enol form is not that stable as compared to its keto form. So its keto form is more stable. So it will try to form a keto. So it will result in the formation of a keto form. That's why it tautomerizes to keto form. So this is the product of this reaction, or this is what we call addition of water to alkyne. After that, my dear lovely students, there is another reaction, that is addition of halogen. Very, very, very simple reaction. Whenever you are having an alkyne and you want to add halogen, suppose you want to add halogen in CCl4. Say in presence of CCl4. So in CCl4, non-polar solvent, what we have to do is break pi bond, first one pi bond, then add X and X from opposite sides, then finally add one more X2. But remember, if X2 is bromine, then this reaction can be used as a test for unsaturation. Then break pi bond. Once pi bond is broken, then you have to add X. So X, X, X and X. That means tetrahalide will be obtained. But if similar reaction takes place in polar solvent, for example in water, for example you are having X2 and water. This is also known as hypohalous acid, HOX. HO minus will be at that time negative part, X is positive part, and remember X is not equal to F. Okay. Now negative part goes to that carbon-carbon triple bond. That means it will be like this. Negative part goes to that carbon-carbon triple bond which is having lesser number of hydrogen, and X to this. First anti-addition. After that, break one more pi bond. When you add HOX further, this is negative part, this is positive part, or you add X2 water. Break pi bond and add X to that which is already having X, and add OH to that which is already having OH. But this is unstable. As two OH groups are not stable over here, it will lose water molecule. Once water molecule is lost, it will result in the formation of this is ketone, but at alpha position of this ketone, two halogen groups are here. So dihaloketone will be the product formed over here. After that, hydroboration oxidation. That means indirect hydration of alkynes. Have a look. you are having an alkyne like this and you are performing hydroboration oxidation. That means reagent should be B2H6 or BH3 followed by oxidation, that means H2O2 and OH minus. Whenever these reagents are there, we have to add water, but now across carbon-carbon triple bond, because substrate is triple bond now, so across carbon-carbon triple bond according to anti-Markovnikov's rule. That means you have to break pi bond first, one pi bond, break one pi bond, and then you have to add negative part to that carbon-carbon triple bond which is having more hydrogens. That means OH to this one and H to this one. After that, this is an enol. It will tautomerize to its keto form like this. So H is shifted from this to this, so it will result in the formation of RCH2, and then this is C having double bond O and NH. This is an aldehyde which is formed over here in this example. Now, if it is not terminal alkyne, if it is R, then it will be, say ketone which is formed. Okay. After that, another reaction will be oxymercuration, demercuration. Another reaction is oxymercuration, demercuration. If you are having an alkyne like this, and we want to perform oxymercuration, demercuration of this. That means mercuric acetate is there, followed by reduction NaBH4 OH minus. Whenever we are having such types of reagents, what we have to do is we have to add water. Add water across carbon-carbon triple bond according to Markovnikov's rule. Here, addition was according to anti-Markovnikov. Here, addition is according to Markovnikov. Now, if addition is according to Markovnikov, first of all, we will break triple bond to double bond, then we will add OH over here and H over here. So, enol is formed. This enol will undergo tautomerization, and it will result in the formation of more stable keto product. So it will result in the formation of this product. After that, my dear lovely students, there is ozonolysis. Ozonolysis is of two types, whether reductive or oxidative. What you have to do in reductive ozonolysis is, that's very, very simple. Ozonolysis by using zinc water, what you have to do is break two pi bonds and add oxygen and oxygen double bond to this. That means dicarbonyl compound will be obtained in this one. Very, very simple. After that, another ozonolysis is oxidative ozonolysis. For this, you have to remember this one. If you are having a triple bond, carbon to which hydrogen is attached, this upon oxidative ozonolysis gives carbon dioxide and water. And if you are having triple bond C and then R, convert this triple bond C into COH and then R is there, so it will result in the formation of RCOOH. I mean to say, if you are having an alkyne like this, what will be the product of this reaction if oxidative ozonolysis takes place? Now, triple bond CH, break this, convert this into carbon dioxide and water, convert this into carbon dioxide and water. That means it will result in the formation of carbon dioxide and water. But if you are having CH3, then C triple bond, then CH, what will happen over here? This triple bond C is converted to carboxylic acid and CH3 is there, so it will result in the formation of CH3COH plus this will result in the formation of carbon dioxide and water. But if you are having an alkyne like this, what will happen? Break this bond and convert This triple bond C to COH, CH3 is attached. Convert this to COH, CH3 is attached. That means it is twice CH3, COOH will be obtained. After that, my dear students, there will be another reaction, and reaction is oxidation by using KMnO4H positive. KMnO4H positive is this. It is KMnO4H positive. KMnO4H positive. Or K2Cr2O7 H positive, or hot KMnO4 or hot K2Cr2O7. At that time, reaction is similar as that of oxidative ozonolysis. So similar reaction as that of oxidative ozonolysis. It is similar reaction as that of oxidative ozonolysis, my dear lovely students. After that, this is oxidation by using Bayer's reagent. Now, what is Bayer's reagent? Cold dilute alkaline KMnO4 solution. What you have to do here is, whenever you are having CH, convert that into COH. And if you are having triple bond Cr, convert that into C double bond O and then R. And if you are having C double bond O and to that COH is attached, always you have to decarboxylate that. You have to lose water to this, and after that you have to form it into COH. That means if we are having an alkyne like this, on treatment with Bayer's reagent or dilute KMnO4 at a temperature of 273 Kelvin, that means cold condition, this COH is converted to COH. This is single bond COH. That means this is single bond COH, as triple bond is common in between them. Then COOH, single bond COH. That means single bond should be common in between them. That means acetylene or ethine will give oxalic acid. What will be the product over here? First, it will result in the formation of CH3, C double bond O. But triple bond is common, so single bond is common between them. Once C double bond O COH is there, it will further oxidize and carbon dioxide will be lost, and it will result in the formation of CH3, COOH. Now, what will be the product of this reaction? CH3, C triple bond, C, CH3. What will be the product of this reaction? Now, it will result in the formation of CH3, C double bond O, C double bond O, and then CH3. After that, my dear lovely students, there is polymerization reaction. There is polymerization reaction, very, very important reaction. Polymerization reaction of alkynes. Have a look. First is linear polymerization. Whenever you are having an alkyne like this, it upon linear polymerization by using CuCl, NH4Cl, what will happen over here? It will undergo, polymerization in such a way that hydrogen is replaced by vinyl group of another acetylene group. First it will result in the formation of CH2 double bond CH, single bond C, triple bond CH, then there is another H, so further reaction will take place, CuCl, NH4Cl, and this hydrogen will be replaced once again like this. So divinyl acetylene or acetylene will be obtained. What has happened actually? Instead of this, we have basically written over like this. Have a look. This has formed a bond with this. But when this forms a bond with this hydrogen has been replaced. That means this negative charge, it becomes negative charge. This negative charge will accept this H. That means it becomes CH2, double bond CH. then CH2 double bond CH, C triple bond H. So it becomes double bond CH2 and this is CH. So CH2 double bond CH will attach to this and it will form this. Similarly, after that, another molecule will form this one. So this is linear polymerization. After that, we will be having cyclic polymerization. We will be having cyclic polymerization. During this, what will happen? Acetylene trimerizes. That means 3 molecules of acetylene react together and trimerizes in the form of a ring in presence of red hot iron tube. Red hot iron tube. At a temperature of 873 Kelvin, it trimerizes to benzene. It forms benzene. But if it is propyne, then it trimerizes to mesitylene. It trimerizes to mesitylene or mesitylene. I mean to say 1,3,5 trimethyl benzene. I mean to say mesitylene. Mesitylene will be the product over here, and here benzene will be the product. So this is cyclic polymerization. So this was all about alkynes. Now we will be having another topic pending in this chapter, and this will be the last topic of this chapter, that is aromatic hydrocarbons. First we will do its methods of preparation. After that we will do its chemical reactions. But before that, let me know in the chats if I am clear till now, and let me take a rest of 1 minute so that I can take some water. Let me know quickly. Am I clear till now? Let me know quickly. Let me know quickly. Am I clear till now? Come on, come on. I'm waiting. Let me know quickly. Okay. Thank you everyone. Thank you for responding. Okay. That's great. Let me tell you once again that I'm not feeling good, but I'm here only and only for you people, because your examination is very near. So I need your concentration. I need your support right now. Okay, my dear lovely students. Now after this, have a look. First of all, from alkanes aromatization, this is already what we have already discussed this reaction today itself. So I can say this is done. This is done. Okay. Or we can say this is already done over here. Second is by cyclic polymerization. We have done this reaction just now. Have a look. This is what we call cyclic polymerization. So with the help of this, we can convert acetylene or trimerizes acetylene to benzene. So this is already done. This is done. After that, we will be having third preparation, that is from cyclohexane and cyclohexadiene. Have a look. This is cyclohexane. This is cyclohexene, sorry. And this is cyclohexadiene. Cyclohexadiene can be conjugated. It can be what we call a non-conjugated cyclohexadiene. What we have to do is, if this is treated with selenium, and we heat this with selenium. Selenium is a dehydrogenating agent. It will break CH bonds and remove H from there and will form C radicals, and those C radicals will result together in the form of what we call benzene. So all these structures can be converted to benzene. So whether it is cyclohexene, cyclohexadiene, whether conjugated, non-conjugated, all will be converted to, benzene if they are treated with selenium and heat. After that, fourth reaction is by Diels-Alder reaction. This reaction is simply 4 plus 2 cycloaddition reaction. This is 4 plus 2 cycloaddition reaction. That means this is the reaction during which 4 electron system is added to 2 electron system, and it will result in the formation of a cyclic 6-membered structure. Have a look. If you are having a diene, for example, buta-1,3-diene, it will act as a diene, and it's having 4 electrons, 2 pi, 4 pi electron system. If this is added to CH2, that means this is an ethene, and this ethene here will act as a dienophile. That means diene loving species. What will happen? It will simply attack this carbon. This carbon will form a carbanion over here, negative charge over here, and this negative charge will attack over here. Then this bond will be break. Now what will happen? What will happen? Let me show in this fashion. Now this bond is formed. This bond will be formed. This bond will be broken. This bond will be broken. This bond will be formed. This bond will be broken. This bond will be formed, and this bond will be broken. That means there will be a cyclic 6-membered transition state will be formed. So let me write down cyclic transition state will be formed. After that, finally, this bond will be broken, this bond will be formed, this bond will be broken, this bond will be formed, this bond will be broken, this bond will be formed. So it will result in the formation of a cyclohexene. But so this is known as Diels-Alder reaction. 4 plus 2 cycloaddition takes place and 6-membered ring has been formed. And this upon treatment with selenium and heat will result in the formation of benzene. So with the help of this Diels-Alder reaction, we can form, benzene after dehydrogenation. I hope this is clear. But remember, this reaction will be much more faster if this dienophile is having electron withdrawing groups. More electron withdrawing groups, then this will attack more faster. Faster attack will take place. After that, next reaction is from haloarenes. Another reaction is from haloarenes. Now, my dear lovely students, say for example, we are having chlorobenzene. If this chlorobenzene is treated with, magnesium in an ether, say for example, tetrahydrofuran, what will happen? Between C and Cl, this Mg will be incorporated, because the function of whenever you have CX bond and Mg will be always incorporated between C and X. Now, this is phenyl magnesium halide, that means a Grignard's reagent. This Grignard reagent is having negative part and a positive part. Now, this upon treatment with water, what will happen over here? Positive part of water will be accepted by this and negative part will be accepted by this. In this fashion, we will get a benzene over here, because this will attack this H positive. So normal acid-base reaction will take place. I have shown this H so that you will understand that this H goes to this place, otherwise not necessary, not needed. That means if I remove this H, it should be understood. Now, this will be the product. Similarly, if you are having chlorobenzene like this, and my dear lovely students, if it is treated with nickel aluminium alloy in presence of NaOH, this is a reducing agent, it simply replaces Cl by means of hydrogen. So it can be converted to benzene with the help of this as well. So you can form what we call aromatic hydrocarbons from haloarenes. After that, we will be having another reaction that is from phenol. That is from phenol. Have a look. Whenever you are having phenol, and you want to convert phenol into aromatic hydrocarbon, what you have to do is you have to remove this oxygen, and it is zinc which is used as here to remove this oxygen. So it will result in the formation of zinc oxide as well. So this is simply a removal of oxygen, that means reduction. After that, from benzaldehyde, have a look. From benzaldehyde, we want, benzene. That means we have to remove this carbon directly attached to benzene. It can never be removed until and unless, this C is converted to COOH. That means, first of all, whenever benzene is attached to carbon, and if you want to remove that carbon, first you have to convert that carbon to COOH. So you have to convert the CHO to COH. How? By simply oxidation. Say for example, by using strong oxidizing agents like KMnO4, K2Cr2O7, HNO3. You can use any strong oxidizing agent. So simply you have to oxidize this. So first it will be oxidized to COOH. Once it's oxidized, now treat it with first sodium hydroxide. OH will abstract this H, and it will result in the formation of sodium salt of acid. Now, when it forms sodium salt of acid, now treat it with soda lime. That means NaOH, CaO, and heat it. What will happen? Decarboxylation will take place, Na2CO3 will be lost, and to this H will be attached. So benzene is formed. So whenever you are having benzene and to that benzene carbon is attached, you want to remove carbon, first you have to convert into this, then these two steps, then benzene will be obtained. After that, next reaction is from benzoic acid. Can I say it's done right now? It is done right now. Have a look. From benzoic acid, it's already done. After that, from benzonitrile. What is meant by benzonitrile? Have a look. Benzonitrile means this one. Benzene, to that C triple bond N or CN is attached. But once again, we have to remove carbon, but it's not possible that we can remove carbon directly. That's why we have to convert this into first benzoic acid. We have to convert CN to COOH first. How to convert CN to COH? By hydrolysis, complete hydrolysis. So CN will be converted to COOH. After that, we know what we have to do. First, treat it with NaOH. It will result first in the formation of COONA. Now treat it with soda lime. That means NaOH and CaO at high temperature. So decarboxylation will take place and carbon dioxide will be lost in the form of CO3 minus ion, and it will result in the formation of benzene. This is very, very, very simple now. After that, my dear lovely students, from nitrobenzene, have a look. Here we have to remove now nitrogen attached to benzene. Now it is not possible to remove nitrogen unless and until this is converted to diazonium ion. Unless and until it is converted to diazonium ion or diazonium salt. Now, how to convert this into diazonium salt? First, we will reduce nitro compound. We can reduce nitro compound by many ways. This is the simple reduction by active metal in acid. Then NO2 is converted to NH2. I mean, say, primary aromatic amine. Now, this primary aromatic amine is treated with NaNO2 in excess of acid, say for example HCl, or HNO2, because both will form HNO2 and HCl is in excess. At 0 to 5 degrees Celsius, this reaction on treatment of primary aromatic amine with this results in the formation of benzene diazonium salt. Reaction is known as diazotization reaction. This is known as diazotization reaction. Now, first, this has been formed. Now, you can replace now this N2. You can replace now this N2. You will remove this with the help of phosphenic acid or ethanol. And it will result in the formation of what we call benzene, and N2 will be lost. So whenever you have to replace N by H, first you have to convert that N to N triple bond N or N2. That means diazonium ion. I hope this is clear till now. After that, my dear lovely students, from aniline, it's already done. From aniline, it is already done. It is done in this reaction. Have a look. This is aniline. This is aromatic amine known as aniline. Aromatic primary amine known as aniline. So from this you have to carry out this reaction. This one. Okay. After that, and another reaction is benzene sulfonic acid. From benzene sulfonic acid. That means from this one. This is benzene. We have to remove this SO3H. How? If we treat it with water, remember, it will result in the formation of benzene and H2SO4. But benzene on treatment with H2SO4 can form benzene sulfonic acid. That means this is basically a reversible reaction. This was all about methods of preparation. Now, we will be having chemical reactions of what we call aromatic hydrocarbons. Chemical reactions of aromatic hydrocarbons. And in this, we will be discussing first electrophilic substitution reactions. Let me write down over here. First of all, we will be discussing electrophilic substitution reactions. We will be discussing electrophilic substitution reactions of aromatic hydrocarbons. I mean, say, we will be discussing ESR. We will be discussing ESR. We will be discussing ESR, I mean, say, electrophilic substitution reactions. We will be discussing electrophilic substitution reactions. I mean to say we will be discussing ESR. Have a look. Have a look. We are having an aromatic hydrocarbon, say for example benzene. Now, every carbon of this benzene is having similar electron density. That means electrophile can attack to any carbon. Now, if we want to perform reaction like this, if we want to perform reactions like this, if we want to perform reactions like this, first, we want to perform halogenation reaction. Say for example, we want to perform chlorination or bromination. Reaction takes place in presence of Lewis acid. What will happen? Both these will form an electrophile, and that electrophile is Cl positive, and that electrophile will come and that will attack any site of benzene, because every carbon of benzene, every site of benzene is basically similar electron rich, or it's having similar electron density. So it will result in the formation of this one. But electrophilic substitution reaction can further take place in chlorobenzene if Cl2 is taken in excess. But now Cl2 and AlCl3 will form Cl positive. Now in this case, Cl positive will go to that electron, that site which is having more electron density. Because electrophilic substitution, rate of electrophilic substitution reaction is directly proportional to the electron density of the benzene ring. More rich is the, electron rich is this benzene ring, more faster will be electrophilic substitution reaction. Now, after this is halogenation. Now, second reaction is simply what we call nitration, taking place generally by nitrating mixture, that is concentrated HNO3 and concentrated H2SO4. What you have to remember is, here H2SO4 will act as an acid, HNO3 will act as a base. And function of H2SO4 is to generate NO2 positive electrophile from nitronium ion. That means these will generate an electrophile, and that electrophile is nitronium ion. This nitronium ion will go to the ring and it will result in the formation of nitrobenzene plus H2O. If electron withdrawing groups like nitro, CHO, COH, CN is attached to benzene ring, remember, they will never show Friedel-Crafts alkylation or Friedel-Crafts acylation reaction. But if electron donating groups are attached to benzene ring, then Friedel-Crafts alkylation, Friedel-Crafts acylation will take place. So now this is sulfonation, concentrated sulfuric acid, or you can use oleum. Oleum means this is basically H2S2O7, or it is H2SO4 plus SO3, or H2SO4 fuming. So here generally electrophile is SO3. So that SO3 will be attached to benzene. Finally, it will abstract hydrogen from the medium, and it will result in the formation of benzene sulfonic acid. But remember, this reaction is a reversible reaction. This reaction is a reversible reaction, because if these two are heated, it will result in the formation of benzene and sulfuric acid. Remember this. Generally, SO3 is the electrophile. But sometimes that SO3 can further react with H2SO4 and results in the formation of SO3H positive as an electrophile. So once again, product will be the same. After that, my dear lovely students, there are two more reactions. One is known as Friedel-Crafts alkylation and another is Friedel-Crafts acylation. Have a look. One is Friedel-Crafts alkylation and another is Friedel-Crafts acylation. Friedel-Crafts alkylation generally takes place by using alkyl chloride, but not necessary. Alkyl chloride is not necessary that we use only alkyl chloride. We can use alcohol in presence of acid. We can use alkene in presence of acid. But these are generally used, and it will result in the formation of alkyl carbocation. Now, once carbocation is formed, we have to rearrange this if possible. Suppose this is CH3CH2CH2 positive. Then it will form CH3CH positive CH3. That means isopropyl carbocation after hydride shift. That's why whenever carbocation is formed, you have to check whether that carbocation can form more stable carbocation after rearrangement. You have to rearrange that. Now, here will be no rearrangement because we don't know the value of R. So it will simply, this R will be introduced. So this is alkylation. Halogen has been introduced, halogenation. Nitronium ion has been introduced, nitration. Sulfonic acid group has been introduced, sulfonation. Alkyl group has been introduced, so this is known as alkylation. But this is Friedel-Crafts alkylation. This is known as Friedel-Crafts alkylation. So Cl should be attached to sp3, not to sp2 hybridized carbon. After that, here you can use acid chloride or acyl chloride in presence of AlCl3, say Lewis acid. or you can use acid anhydride as well. But both these can form this carbocation. This is known as acylium ion, but this will not undergo rearrangement as it can form, as it is very stabilized by back bonding. As it is stabilized by back bonding. So no rearrangement will take place over here. And finally, what will happen over here? This H of benzene, any H of benzene will be replaced by this electrophile. So C double bond OR. So this will be the product and then HCl. So this is electrophilic substitution reaction taking place of benzene. But remember, electrophilic substitution reaction rate is dependent on the electron density of this ring. More electron rich is this ring, more faster will be electrophilic substitution reaction. After that, my dear lovely students, we will be having addition reactions of benzene. We will be having addition reactions of benzene. But before this, let me tell you one more reaction first. Let me tell you, if you are having benzene, and if this benzene is treated with, if this is treated with chlorine, that means chlorination is there, but reaction takes place in presence of anhydrous AlCl3. We know this is, both these can form Cl positive, and then Cl positive will replace hydrogen of the ring. That means this is simply normal electrophilic substitution reaction. But if Cl2 is taken in excess, if this is in excess, then another Cl positive will replace another H, another Cl positive will replace another H, another Cl positive will replace another H, another Cl positive will replace H positive, Cl positive will replace H positive. So hexachlorobenzene will be obtained. Hexachlorobenzene will be obtained, and reaction is normal electrophilic substitution reaction plus 6 times HCl. So total chlorine atoms used have been 12. That means you can write down over here 6 times, you can use over here 6 times, I mean to say 6 times chlorine. So this is simply an electrophilic substitution reaction. Similarly, if Friedel-Crafts alkylation reaction is like this, you have an alkene and you are having CH3, CH2, CH2Cl, and reaction takes place in presence of AlCl3. What will happen? Both these, this will remove the Cl and it will result in the formation of this one. This carbocation will be formed first, but before it will attack to benzene ring, it will undergo rearrangement. 1,2 hydride shift. Why? So that it can form more stable carbocation like this. And it will result in the formation of this carbocation. This is more stable carbocation. This is stabilized by 6 alpha hydrogen. This is stabilized by 2 alpha hydrogen. So more stable carbocation is formed. Now this carbocation will attack benzene ring and our product will be like this. I hope this is once again an electrophilic substitution reaction. That's what I was saying over here, that if carbocation is formed, rearrange if possible, but during Friedel-Crafts alkylation, here there will be no rearrangement in this carbocation, as this is already stable because of back bonding. Now, addition reactions of benzene. First addition reaction of benzene is, if we want to add hydrogen, addition of hydrogen across carbon-carbon double bond of benzene is not possible under normal conditions. That's why we take this hydrogenation in presence of nickel, in presence of catalyst, and that too at high temperature. Now, we can say that 6 hydrogens, atoms will be added, one hydrogen atom, first, second, third, fourth, fifth, sixth. So it will result in the formation of cyclohexane. So benzene can form cyclohexane, but not under normal conditions, only under, at high temperature and in presence of catalyst. This is hydrogenation, addition reaction. Another addition reaction is like this. If you want to add chlorine, across carbon-carbon double bond, then reaction should take place in presence of light and in absence of Lewis acid. If reaction takes place in presence of Lewis acid and in darkness, that means in absence of light, that at that time it's electrophilic addition reaction. But if it takes place in presence of light or at high temperature, remember at that time addition of chlorine will take place across carbon-carbon double bond. Then it will result in the formation of this. So 6 chlorine atoms will be added. So you can write down 3 chlorine. And remember, this reaction is actually free radical addition reaction. And we will be having one hydrogen of its own. So one hydrogen is there already. That is of benzene. So have a look. This is known as benzene hexachloride. This is not benzene, but this has been obtained from benzene. This is known as benzene hexachloride. Its another name is gamexane or lindane or 666. 6 carbon, 6 hydrogen, 6 chlorines are there. Okay. And this is, remember, used as a pesticide. It will act as a pesticide and it will be used in agriculture to kill termites. I mean, say white ants. Can be used in agriculture to kill, I mean, say white ants or what we call termites. So this is addition reactions of benzene. After that, this is first addition of hydrogen. We have done this. We have done this addition of hydrogen. We have done addition of halogen as well. So let us delete these slides. Then we have another reaction, and this reaction is the last reaction of this hydrocarbon chapter. So this reaction is simply oxidation by using V2O5. We have different reactions of, I mean, say this aromatic hydrocarbon like ETADS reaction. We can convert this toluene to benzaldehyde by other reactions as well. We have Gutterman-Koch reaction. We have Gutterman what we call formylation reaction. But those reactions will be studied during 12th class, I mean, say syllabus, because those reactions, we will be discussing those reactions in aromatic aldehydes or aldehydes, ketones, carboxylic acid chapter. Now, V2O5, remember. If benzene is treated with V2O5, at a temperature of 773 Kelvin. That means at high pressure, high temperature. Remember, my dear lovely students, this V2O5 acts as an oxidizing agent as well as a dehydrating agent. First, this carbon and carbon, let us suppose, will be lost in the form of carbon dioxide. Hydrogen, this hydrogen and hydrogen will be lost in the form of water. This carbon and carbon is oxidized to carboxylic acid. So it will result in the formation of this one. Double bond will be there. Now it will result in the formation of this one. This is basically CH double bond CH COH COH. This is known as malic acid. This is known as malic acid. After that, this V2O5 will now act as a dehydrating agent and water will be lost over here like this. And it will result in the formation of malic anhydride. It will result in the formation of malic anhydride. So malic anhydride will be obtained. Similar type of reaction can be shown by naphthalene. Say for example, if you are having naphthalene like this, say for example, this is the resonating structure of naphthalene. First, under similar conditions, at a temperature of 773 Kelvin, it will lose carbon dioxide molecule and it will lose water molecule. And it will first result in the formation of phthalic acid. It will first result in the formation of phthalic acid like this. It will result in the formation of phthalic acid. So first phthalic acid will be obtained. And after that, V2O5 will act as a dehydrating agent and water will be lost. When water will be lost, it will result in the formation of phthalic anhydride. It will result in the formation of phthalic anhydride like this. So phthalic anhydride will be obtained. Phthalic anhydride will be obtained. But remember one more thing. If it is treated with V2O5 at a temperature of 300 degrees Celsius exactly, or we can say 573 Kelvin, exactly at 573 Kelvin, it undergoes partial oxidation and it will result in the formation of phenol. It will result in the formation of phenol. So this was all about hydrocarbons. Now we will be having previous year questions. Now, but before doing previous year questions, let's have a break of, I mean to say, 20 or 30 minutes. As you know, I need rest because I am in front of you only and only because of you people. So let's take this after half an hour. So let's have a break. Let's have a break till time is 8:40. That means let's meet at 9:10 p.m. Exactly at 9:10 p.m. Let's meet at 9:10 p.m. Exactly. Okay. But I would want you all to be present at 9:10 p.m. So till then, take care. Bye-bye. And you can have some food till then. You can rest as well. Let's meet at 9:10 p.m. Okay, welcome back everyone. Let me know quickly in the chats if you can see me clearly and you can hear me clearly. Let me know in the chats quickly. If you can see me clearly and you can hear me clearly, let me know in the chats quickly, my dear lovely students. Come on. You can let me know in the chats if I am audible and visible to each and every one. Okay, so this is the last part because time will not allow us to discuss, qualitative and quantitative analysis. But let's discuss previous year questions related to class 11th. So come on. First of all, first question is like this. First question is like this. Very simple question. Number of sigma, pi bonds and lone pair of electrons in what we call pyridine. That means this is the pyridine. This is pyridine. How many lone pairs are there? First sigma bond, then pi bond, and then lone pairs. Have a look. Every this carbon is having hydrogen. This is having hydrogen. This is having hydrogen. This is having hydrogen. This is having hydrogen. So these are previous year questions. Have a look. So this is one sigma bond. 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 This is sigma bond. This is sigma bond. This is sigma bond. Sigma bond. Sigma bond. This is also sigma bond. This is sigma bond. Now, how many sigma bonds are there? 1, 2, 3, 4, 5 of carbon hydrogen bonds, and 1, 2, 3, 4, 5, and 6 of carbon and carbon nitrogen. That means 6 and 5, that is 11. So 11 sigma bonds, 3 pi bonds, and 1 lone pair. 11, 3, and 1. This is the right answer. Now, you try to solve these questions as well. 11, 2, and 1. No, it's 11, 3, and 1. 11 sigma bonds, 3 pi bonds are there, and 1 lone pair is there. Try to solve these types of questions as well. Come on. Then another question is like this. The correct IUPAC name of the following compound. To this compound, you have to write down the IUPAC name. Can anyone try? Can anyone let me know in the chats what will be the name of this compound, of which option is correct one? Let me know. I am waiting for your response. Come on. Let me know quickly. At the rate of Reznov is saying 3. What about others? Come on. Which option is the right option? Come on, my dear lovely students. Okay, Yuvraj is saying 3. Supriya is saying 3. At the rate of Said is saying 3. Okay. So have a look. First of all, you have to number in such a way that this functional group gets lowest number. So 1, 2, 3. It gets 3 if we say number from right side. 1, 2, 3, 4 if we number from this side. So if this is 1, if this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Then this chlorine will act as a substituent, bromine will act as a substituent, methyl will act as a substituent. So it will be simply 1 bromo, 5 chloro, 4 methyl, and then hexane 3 all. Have a look. So it will be 1 bromo, 5 chloro is this one, 4 methyl, and hexane 3 all. That means it is second one. It is not third one. 1, 2, 3, 4. No, it's not like that. Functional group should get lowest number. So it's 2. S exactly at the rate of Ajay, it's 2. At the rate of Sargi, it's not 3. At the rate of Irtiza, correct. Okay. After that, We will be having another. Which of the following molecules represent the order of hybridization? sp, sp2, sp and sp. This is not having sp, this is not having sp, this is not having sp. So this is sp, this is sp, but we have to write down sp2 first. So this will be not the option. Then sp2, sp2 first, sp2, sp2, sp, sp. Then it will be option number second. Simply option number second will be the right answer. After that, IUPAC name of the following compound. This compound is having two functional groups. One is aldehyde, another is ketone. But before that, let me know, is this clear? Yes, this is clear. This is clear. What will be the answer? What will be the answer? I will be waiting. I will be waiting for this. What will be its answer? I will be waiting. What will be the answer of this question? Come on. Come on, come on, come on. Have a look. This having two functional groups, aldehyde and ketone. Aldehyde is main functional group and is a chain terminating functional group. So this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. That means it's having 6 carbon chain. So it is simply hex. Word root is hex. Then after that, we will write down primary prefix, primary suffix, and that is what we call 4-ene. After that, we will write down functional group. Functional group is ul, and ul is present at 1 position. But as it starts with vowel, this e will be lost before this. Before this, we have to write down substituents. Keto is the substituent starting with K, and methyl is the substituent starting with M. So we will write down first keto. So it is 3-keto, and it is what we call 2-methyl. So these are the substituents. So name of this compound will be simply 3-keto, 2-methyl, hex 4N, 1-ul. Hex 4N, 1-ul. 3-keto, 2-methyl, hex 4N, 1-ul. It will be second option. It will be second option. Exactly, exactly. Everyone is correct. Exactly. After this, we will be having another question. Total number of pi bond electrons in the following structure. As we are having 1, 2, 3, 4 pi bonds, that means pi bond electrons. Every pi bond is having 2 electrons. 4 pi bond means 8 electrons. So we will be having 8 pi electrons in this. We will be having 8 pi electrons in this. In total number of pi bond electrons will be 8. Will be 8. Is this clear? Is this clear? Is this clear? Exactly at the rate of Ajay, it will be 8. Exactly at the rate of Aditya Gopala, 4. At the rate of Yuvraj, yes, it's 4. Yes, it's 4. After that, option number 4 is the right answer. The structure of isobutyl group is, we know isobutyl is this group. This is isobutyl. This is isobutyl, in which we are having CH3 at second position in the form of a branch. So this is isobutyl. This is isobutyl. This is sec-butyl. This is N-butyl, and this is third butyl. So this is isobutyl. After that, we will be having another question. With respect to conformers of ethane, which of the following statement is true? Bond angle changes. No. During conformation or rotation, bond angle and bond length remain same. It's only dihedral angle which changes. Both bond angle and bond length changes. No. Bond angle changes but bond length remains same. No. Both bond angle and bond length remain same. Yes, this is correct. Bond angle remains same, bond angle changes. No, this is correct. Bond angle and bond length remain same, but dihedral angle changes. We have already discussed that. After that, we will be having which among the given molecules can exhibit tautomerism. Have a look. For tautomerism, we need, sp3 hybridized carbon attached to, we need sp3 hybridized carbon, but to that, hydrogen should be such that that can form, if that hydrogen is removed, that must be in conjugation with C double bond O. Have a look. This hydrogen or this hydrogen will not take part in, tautomerization, otherwise Brett's rule is violated. Similarly, Similarly, this hydrogen at bridgehead position cannot take part in what we call keto-enol tautomerization or tautomerism, because otherwise Brett's rule is violated. So this will not take part, this will not take part, this will not take part. Therefore, there will be no tautomerism in these two cases. But here tautomerism can take place. Not from this hydrogen will not take place, but this hydrogen can take part in tautomerization. So in nutshell, third is the only option where tautomerization or tautomerism exhibits. So option number one is the right answer. Option number one is the right answer. After that, the correct statement regarding the comparison of staggered and eclipsed conformation of ethane is: staggered conformation of ethane is less stable, no. Eclipsed conformation of ethane is more stable, no. Eclipsed conformation of ethane is more stable, no. The staggered conformation of ethane is more stable, yes, than eclipsed conformation, because staggered conformation has no torsional strain. Exactly, fourth is the right answer. Fourth option is the right option. Fourth option is the right option, my dear lovely students. After that, we will be having another question. Which one of the following is least stable resonating structure? First of all, we know, is this clear? Is this clear to each and every one? This is NH2. This is NH2. This is also NH2. This is also NH2. This is also NH2. This is CH3. This is CH3. This is CH3. This is CH3. This is having a positive charge over here on carbon. Okay. Everything is clear now. Everything is clear now. Have a look. This is also a positive charge. Now, first of all, neutral resonating structure is more stable. So one, after that, resonating structure contains more pi bonds. That means this and this, they are more stable. They are more stable. That means this is the least stable. We have to find out least stable. So let us write down 3 at the end. After that, this and this, both are having, have a look. Positive charge, both are having, these are all having complete octet. In this, all are having complete octet. After that, it is charge rule with the help of which we have to distinguish. O minus, same. But nitrogen having positive charge, oxygen having positive charge. This is less electronegative, so this is more stable. So it is 1, 2, 4 and 3. But our question is, which among the following is least stable resonating structure? So it is obviously third one. It is obviously third one. Is this clear? Is this clear? Is this clear? How come 4? How come 4? Now 4 is not the least stable because this is having more pi bonds. First, you have to check neutral resonating structure is more stable. After that, more number of pi bonds. After that, resonating structure whose all the atoms have complete octet. Then charge rule, in which negative charge is present on more electronegative element as compared to less electronegative element. Similarly, positive charge should present on less electronegative element as compared to more electronegative element. So is this clear? Is this clear? Is this clear? Come on, let me know quickly. Let me know quickly. Is this point clear? First, it should be neutral, and then having more pi bonds, and at the end, this is having lesser pi bonds. So least stable is third one. Least stable is third one. Now the positive charge is more stable when it is present on less electronegative element. Yes, nitrogen is less electronegative as compared to oxygen. That's why this is more stable than this. But here you cannot check positive charge until and unless you will use rule 1, rule 2, then 3, then 4. First, you have to check neutral is more stable than these charged ones. Second rule is that you have to check more number of pi bonds. After that, neutral. This is more pi bond. This is having more pi bond. So these are more, say stable as compared to this. You cannot jump into this rule that this is having what we call positive charge and less electronegative element having positive charge. No, you have to use rules in systematic order. This is having a positive charge and more electronegative element, but this is having complete octet. This is having less electronegative element which is having positive charge, but remember, this is not having complete octet. Hence, this is less stable as compared to this. Remember forever. Remember this forever. Remember this forever. Use say all those rules which I have given to you accordingly, one by one. Okay, after that, write decreasing order of basic strength of the following compounds. You have to write down the decreasing order of basic strength. This is CN, this is NO2, this is OMe, this is NH2. Let me erase this one. Let me erase this. This is nothing. This is OMe. This is a bond over here. Similarly, this is nothing. This is, OMe. This is NH2. This is OMe. This is NH2. This is CN. Have a look, my dear lovely students. This is NO2. Now, you know these groups. This is, minus R group as well as minus I group, but we will not take inductive effect from this position as this is, at a greater distance. So more distance, so inductive effect will be less. So this is having minus R group. This is having plus R group. This is a plus R group. This is also a plus R group. So we know whenever we have to check basicity, remember you have to write down first plus R, then plus H, then plus I. But strong to weak. After that you have to write down neutral species. After neutral species you have to write down minus I, minus H and minus R. But these should be from weak to strong. Have a look. First we have to check plus R. Plus R are 2. So write stronger one, after that weaker one. This is stronger one. This is weaker one. So if this is 1, this is 2, say for example, this is 3 and this is 4. So 4, 1 will be the strongest base. After that, it will be 3. After plus R, we have to use plus H, but no one shows plus H, no one shows plus I, no one is neutral, no one is minus I group, no one is minus H group, minus R. This and this is minus R. But we have to write down weaker first. We know NO2 is stronger, CN is weaker. So I will write down weaker first and then stronger. So this will be the order of basis T. So write down decreasing order of basic strength. Decreasing order of basic strength will be 4, 3, 2 and 1. It will be 4, 3, 2 and 1. Exactly at the rate of Mobina. Exactly at the rate of Yuvraj. This is clear, this is clear, this is, yes, at the rate of Ixa, exactly this is correct. 4, 3, 2, 1 is the right answer. After that, my dear lovely students, once again, a question is write down decreasing order of basic strength. Have a look. From para position, take plus H of this methyl, take minus R of aldehyde, take minus R of, this one, and here no group is attached to para position of this. That means it is hydrogen which is attached to para position of this. So take this as hydrogen, neutral species, because hydrogen neither shows inductive effect, nor shows resonance, nor shows hyperconjugation when it is attached to double bonded carbon of this benzene. Now, what we have to do is first we will write down plus R group. Have a look, but there is no plus R, then we will write down plus H. So which one is plus H? Plus H is 4, so I will write down 4. Then I will write down plus I, but no one is plus I. After that, it is neutral, that means it is 1. After that, minus I, no, minus H, then minus R. But among minus R, write weaker one. We know weaker is aldehyde as compared to nitro group. So it will be like this. Order will be like this. 4, 1, 3, 2. Is any option 4, 1, 3, 2? 4, 1, 3, 2. 4, 1, 2, 3. Yes, this is the right option. Third is the right option. Third is the right answer. Exactly. Third is the right answer. After that, electrophiles are electron-seeking species. Which of the following groups contain only electrophiles? Now have a look. BF3 is an electrophile, but NH3 is a nucleophile. Water is also a nucleophile. AlCl3 is an electrophile, SO3 is an electrophile, NO2 positive is an electrophile. So these are all having electrophiles. This is an electrophile, this is an electrophile, this is an electrophile. So this is also, all are electrophiles over here. After that, this C2H5 minus, no, C2H5, no, C2H positive, no. So these two options are correct. Both are correct, as both options contain electrophiles. NO2 positive can act as an electrophile. SO3 is will act as an electrophile. This is an electron loving species also, because this is a Lewis acid. So both options are correct. Both options are correct. Both options are correct. Both 1 and 2. Both, 2 and 3, not 1. Both 2 and 3 are correct. Is this clear? Is this clear? Because electrophiles are electron loving species, or those species which can accept electron pair, which can accept electrons. Am I clear till now? Am I clear till now? Am I clear till now? Come on, let me know quickly. Am I clear? Am I clear? Let me know quickly. Let me know quickly. I'm waiting for your reply. Come on. Come on, my dear lovely students. I'm waiting for your reply. Come on. Okay. After this, we will be having this one. Question is like, consider the following compound or species. The number of compounds or species which obey Huckel's rule, that means which are aromatic. Now have a look. This is aromatic, so 1. This is aromatic, so 2nd. This is what we call aromatic, 3rd. This is having a positive charge. This is having negative charge. So this is aromatic. So 1, 2, 3 and 4. 4 species are aromatic. So it is option number 2. Option number 2 is the right answer. Let me know quickly. Is this clear? This is having a negative charge. Okay. Let me know quickly. This is tub shape. This exists in tub shaped structure. So this is non-planar, non-aromatic. This is what we call anti-aromatic. This is anti-aromatic. So we are having 4 species over here which are aromatic. Now, yes, in IUPAC, yes, if something says that this substituent is present twice, suppose di, tri in simple substituents or base trace in complex substituents, they are not included in alphabetical order exactly at the rate of exa. Now, a tertiary butyl carbocation, that means this one. A tertiary butyl carbocation is this one. Tertiary butyl carbocation is this one. Is more stable than secondary. Is more stable than secondary butyl carbocation. Is more stable than secondary butyl carbocation. I mean, say this one. Because of which of the following? Plus R effect of CH3, minus R effect of CH3, hyperconjugation of CH3 minus I of CH3. It's having 9 alpha hydrogens. This is having only 5 alpha hydrogens. So this is more stable because of alpha hydrogens, that means because of hyperconjugation. So this is the right option. So option number 3 is the right answer. After that, we will be having this question, and this is very, very, very important question. Have a look. Have a look. Have a look. This is having a positive charge over here. if resonance takes place, can I say positive charge comes in direct contact with NO2 and NO2 is electron withdrawing group? That means in one of its structures, that means if we form a hybrid of this, basically, have a look. Its hybrid will be like this. Let me draw a hybrid of this. This is Y, this is H, and hybrid will be like this. And positive charge will be here, positive charge will be here, positive charge will be, I mean to say, here. Similarly, if I draw hybrid of this, it will form a similar type of hybrid like this. And positive charge of this NO2 group, I mean say this structure will be either at this position or at this position or at this position. If we draw hybrid of this, have a look. Its hybrid will be like this. Its hybrid will be like this. And positive charge will be either from to this position or to this position or to this position. If we draw hybrid of this, its hybrid will be like this. So positive charge will be at this position or this position or this position. Now, you can compare hybrid and you can see that in this hybrid, positive charge is attached to that atom which is directly attached to electron withdrawing group. Similarly, positive charge is attached to that carbon to which electron withdrawing group is attached. Positive charge is present on that carbon to which electron withdrawing group is attached. But this here, positive charge is not in direct contact with electron withdrawing group. If positive charge is in direct contact with electron withdrawing group, such positive charge is less stable. If positive charge is not in direct contact with, say electron withdrawing group, such positive charge is more stable. We have to write down more stable carbocation over here. So can I say more stable carbocation? More stable carbocation will be fourth one. Most stable carbocation will be 4-1 because other three options can form carbocation where positive charge is in direct contact with NO2. But remember, if instead of NO2 electron donating group is attached, then this will become least stable because positive charge in direct contact with electron donating group becomes more stable and positive charge which is not in direct contact with electron donating group becomes less stable. Beta, I will take complete class 12th organic chemistry on Saturday. But first, Wasim sir will take physical and inorganic. After that, I will take organic in the same session. So, this is basically explained on the basis of resonance hybrid. So, the answer is actually due to what we call resonance. After that, here, which of the following is correct with respect to minus I effect of substituents, alkyl group? No. What is this question? Which of the following is correct with respect to plus I? With respect to, sorry, minus I. With respect to minus I. So these are minus I groups with respect to minus I effect of the substituents. So let me erase this one. You have to tell me the minus I order among these. Minus I order among these is simply based on what we call electronegativity. So F is stronger than oxygen, than nitrogen. So first one is the right answer. F, O and N. Second is also the right answer. Now N, O and F. No. N, O and F. No. These two are, correct answers both. Both are the correct answers because F is more electronegative than oxygen, is more electronegative than, nitrogen. I hope this is clear. Both are correct. Both are correct, my dear lovely students. It's not only one, both are correct. 1 and 2, both are correct. After that, the statement is like this. The correct statement regarding electrophile is, electrophile can be either neutral or positively charged. Yes. neutral as well as positively charged, and can form a bond by accepting a pair of electron from a nucleophile. Yes, this is correct. So this is correct. Electron, this is electrophile. Electrophile is a negatively charged species and can form a bond by accepting pair of electrons from a nucleophile. Okay. Electrophile can be either neutral. This is negative. No, this is not correct. Electrophile is a negatively charged. No. Electrophiles are generally neutral species and can form bond by. No. This is more appropriate answer, that electrophiles can be either positively charged or neutral species and can accept electron pair from neutral, nucleophiles. So first one is the right answer. First one is the right answer. First one is the right answer. Okay. Okay. After this, have a look. Which of the following statement is not correct for a nucleophile? What is meant by nucleophile? Nucleophile means nucleus seeking. Nucleophile means nucleus loving. So nucleophiles are not electron seeking. Nucleophiles are not electron seeking. Nucleophile is a Lewis acid. What is meant by Lewis acid? Lewis acid means which can accept electron pair, but nucleophiles are Lewis bases. So this is incorrect. This is incorrect statement. Nucleophiles are nucleus loving. That means they are not electron seeking. This is correct. Ammonia is a nucleophile. Yes, that can donate an electron. That's a nucleophile. Nucleophiles attack low electron density sites. Exactly. So nucleophile is basically a Lewis base. So here we have to choose what we call incorrect option. So nucleophile is a Lewis acid is incorrect option. So option number 2 is the right answer. After that, arrange the following in increasing order of stability. Have a look. Have a look. This is having 3 and 3, 6 and 2, 8 alpha hydrogens. 8 alpha hydrogens. This is having 9 alpha hydrogens. This is having 3 alpha hydrogens. This is having 3, 3, 6 alpha hydrogens. This is having 0 alpha hydrogen. So lesser the number of alpha hydrogen, lesser will be the stability. That means E is the least stable. After that it is D. So E and D, that means either 1 or 2. After that E, D and C. E, D and C, that means both are correct. Now E, D, C. After that E, D, C and A. E, D, C and A. E, D, C and A. Now, this is the right answer. E, D, C, A and B. E, D, C, A and B. This is basically like this. This option is actually like this. This option is actually like this. This is A over here. So, which among these is correct? So, first it is E, then it is D, then it is C, then it is A, after that it is B. Okay, so this is the right answer. Option number 2 is the right answer. Am I clear? Am I clear till now? Am I clear till now? Come on. Now, next question is, what is the hybridization state of benzyl carbonium ion? What is the hybridization state? As it involves in hybridization, so it's hybridization of this carbocation is simply sp2. So this is the right answer. This is the right answer. So this is our option. Option 2 is the right answer. Exactly, my dear lovely students. Now, there will be another question. Compound X on reaction with ozone following by zinc H2O, that means it is reductive ozonolysis, gives formaldehyde. One of the products is formaldehyde. So it is like this. Formaldehyde is this. Another is 2-methyl propanol. 2-methyl propanol. Propanol means it is actually this one. 2-methyl propanol. So it is 2-methyl, then it is propanol. So 1, 2 and 3. 2-methyl propanol. What will happen? Replace, remove this and form a double bond over here. So it is like this. CH2, double bond CH, then it is CH, single bond CH3, then it is CH3. So number this 1, 2, 3 and 4. So it is 3-methyl but1-ene. Is any option 3-methyl but1-ene? Yes, it is option number 2. Option number 2 is the right answer. Exactly, Aditya Gopala and others. Exactly. We will be having another question. Which one of the following is suitable to synthesize chlorobenzene? It is simply benzene upon chlorination in presence of anhydrous, ferric chloride. That means simple what we call halogenation reaction. This is much more suitable to synthesize chlorobenzene. This is much more suitable to synthesize chlorobenzene. Yes, second option is the right answer. After that, we will be having another question. The major product of the following reaction, following chemical reaction. What is the reaction? Is this clear to each and everyone? Is the reaction clear to each and everyone? Reaction is like this. Reaction is like this. It is CH3, then it is CH, then it is CH3, then it is CH double bond CH2 plus HBr. In presence of peroxide like C6H5CO whole 2 and then O2. This is what we call benzoyl peroxide. So this is simply anti-Markovnikov's addition. So a reaction product will be CH3CH, CH3, then it will be CH single bond CH2. Here you have to add bromine and here you have to add H. That means it will be 1, 2, 3 and 4. So it will be like this. It will be 1 bromo 3-methyl butane, 1 bromo 3-methyl butane, 1 bromo 3-methyl butane. So it will be CH2, CH2, CH, CH3, CH3. So option number 4 is the right answer. Option number 4 is the right answer. Exactly, exactly, exactly. At the rate of Aishu, exactly, exactly, exactly. Come on, come on, come on, my dear lovely students, come on. Next is, which of the following alkane cannot be made in good yield by Wurtz reaction? Remember, Wurtz reaction is not considered as better method to prepare that type of alkane which can be formed by different amine say radicals, or in general this is not good method to prepare unsymmetrical alkane. Have a look. 2,3-dimethyl butane, it's like this. 2,3-dimethyl butane is like this. 2,3-dimethyl butane is like this. Can I say this can be formed by similar type of radical? Have a look. Identical type of radicals. Then N-heptane. N-heptane is this 1, 2, 3, 4, 5, 6 and 7. Whenever N-heptane is obtained, it can never be formed by similar type of radical. Either it has to be formed by methyl and hexyl radical, ethyl or pentyl, propyl or butyl. It can never be formed by similar type of radical. Hence, this is simply that alkane which can never be formed in a good yield, or this will be always minor product. N-butane. N-butane is this one. CH3CH2, CH2CH3. Have a look. This is also an alkane which can be formed by similar type of radical. So this can be formed in good yield. N-hexane. N-hexane can also be formed. N-hexane can also be formed from similar type of radicals, by combination of similar type of radicals. Hence, this can also be formed in a good yield, but this can never be formed in a good yield. Hence, this is the option of this question. After that, which of the following compound is most reactive in electrophilic substitution, electrophilic aromatic substitution reaction? Remember, aromatic electrophilic substitution reaction, its rate is directly proportional to electron density of the ring. Electron density, it is directly proportional to electron density of benzene ring. Remember this forever. Now, have a look. This NO2 is electron withdrawing, so it will decrease electron density of the ring. Here hydrogens are attached, but here it is OH which will donate electron because of plus R. This will also donate electron because of plus R, but it will withdraw because of minus I, and we know minus I is stronger than plus R. But in nutshell, we have to check which ring is having more electron density. Obviously, that benzene ring to which OH group is attached. So, which of the following compound is most reactive? Most reactive is this phenol. Most reactive will be phenol. Is this clear? Okay, that's great. That is great. That is great. After that, we will be having which of the following is a free radical substitution reaction? Acetylene with HBr? No. This is electrophilic addition reaction. Methane with Br2. Methane with Br2. That means bromination. This is free radical substitution reaction. Yes, propane with HBr in this is free radical addition reaction. Benzene with Br2, this is electrophilic substitution reaction. So we have to write down free radical substitution reaction. So it's methane with Br2. Let me write down this 2 with a white color. So this is, say Br2 is this methane, and with Br2 in presence of light is free radical substitution reaction. This is electrophilic addition reaction. This is what we call free radical substitution reaction. This is free radical addition reaction. Remember this. And this is electrophilic substitution reaction, aromatic electrophilic substitution reaction. After that, another question is this: alkyne to cis-butene. Now let me know quickly, alkyne to cis-butene, which of the following can be used? This is Birch reduction, it will result in the formation of trans-butene. This can be used, and it will result in the formation of cis-butene. I hope this is clear to each and every one. And instead of this, you can use PD calcium carbonate and small amounts of sulfur or quinoline. You can use PD BaSO4 with small amounts of sulfur or quinoline. You can use simply what we call nickel boride or P2 catalyst as well to form cis-butene or cis-2-butene. After that, we will be having another question. And another question is, among the following, the reaction that proceeds through electrophilic substitution reaction is simply this one. This is benzene and chlorine. This is electrophilic substitution reaction. Benzene, chlorine in presence of, say AlCl3. So this is simply electrophilic substitution reaction. So you can zoom out this if you are watching on mobile. So this is clear. After that, which one is the correct order of acidity? Already we have discussed such type of questions. Correct order of acidity is sp hybridized carbons first, then sp2 hybridized carbon, then sp. But so if sp is having electron donating, so we will write down this one. Why? Because it's having CH triple bond C having a negative charge. This is having CH3 C triple bond C having a negative charge, conjugate base. This is having CH2 double bond CH having a negative charge on this carbon, and then it is this one. First, we know among these carbons are more, say electronegative carbons. So negative charge present on these two will be more stable. So if these two are more stable, their acids will be more acidic. After that this, after that this. But among these two, this acid is not having electron donating group. This is having electron donating. So electron donating decreases the acidic character or stability of this negative charge. So hence we will simply write down third option. I hope this is clear. Yes, exactly at the rate of Vinia. Now don't worry. We don't have to start new stream because our stream 12 hours will be at 10:30. So it's 9:50. So you don't worry. We have much more time. So after that we will be having another question. But before that, let me know in the chats, is this clear? Or let me check on a mobile. Yes, this is clear. First, we have HC triple bond CH. This is treated with NaNH2. And ammonia is there acting as a solvent. Now what will happen? This will accept this H positive, NH3 will be lost, and we will get HC triple bond C having a negative charge and then Na positive. First of all, we will get this. After that, this is treated with CH3CH2Br. Have a look, CH3CH2Br. Now it will act as a nucleophile and Br will be lost. That means it is normally SN2 reaction. So our product will be, let me write down product over here, HC triple bond C, then CH2, then CH3. After that, my dear lovely students, this is further treated with NaNH2. In presence of ammonia. So this will act as a base, it will abstract this H, ammonia will be lost. and it will result in the formation of C triple bond C, CH2, CH3. This will be having negative charge and Na positive will attract to this. After that, this will simply react with, have a look, it will react with this one, CH3, CH2 and then Br. A normal SN2 reaction will take place and it will attack to this and Br will be lost. So we will get C, CH2, CH3, that means CH3, CH2, then this CH2 will be attached to C, then it is triple bond, then it is CH2, then it is CH3. So 1, 2, 3, 4, 5, 6. So hex 3-ine. Why is this? This is why. So why is hex 3-ine or 3-hexyne? So it is first one. And what is X? X is this one. X is this one. This is X. So it is 1, 2, 3, 4. So this is but1-ine. 1 butyne and hex 3-ine. So this is the right option. After that, my dear lovely students, which of the following cannot be used as halide component for a Friedel-Crafts what we call reaction? Chloroethane can be used, isopropyl chloride can be used, chlorobenzene. Chlorobenzene cannot be used because here chlorine is attached to sp2, so we cannot replace this chlorine or we cannot form a carbocation over here. So this is basically the halide which cannot be used in Friedel-Crafts alkylation reaction. After that, we will be having this one. In the reaction with HCl, an alkene reacts in accordance with Markovnikov's rule to give a product 1-chloro, 1-methyl cyclohexane. Have a look. This is 1-chloro, 1-methyl cyclohexane. That means if we add HCl to this, Cl will be added to this according to Markovnikov's rule. So it can form, similarly, this is having a double bond over here. Have a look. This is basically a double bond over here. This is a double bond over here, double bond CH2. So Cl will be added to this, H to this. So both A and B is the right answer. Both A and B is the right answer. After that, the reaction of C6H5CH double bond CH3 with HBr. What will happen? Br will go to this place, H will go to this place. So C6H5CHBr, C6H5CHBr, CH2, CH3. That means fourth is the right answer. Fourth is the right answer. It's electrophilic addition because it takes place in absence of what we call Lewis, in absence of peroxide. Now, which of the following compounds will not undergo Friedel-Crafts reaction? Remember, Friedel-Crafts reaction, whether it's alkylation or acylation, it's having a limitation that those species in which electron withdrawing group is attached to benzene ring, they will never show Friedel-Crafts alkylation. So nitrobenzene, it will not show Friedel-Crafts acylation. Xylene can show, toluene can show, cumene can show. After that, my dear students, we have already discussed this. So big thank you from my side to all of you. So this is all about today's session. So thank you very, very, very much. So I am really very much thankful to all of you. So thank you and God bless you all. So it's only half an hour left, so we cannot discuss other portion. As you know, we can teach up to only 12 hours. But before ending this stream, I would want you all guys, do comment me after end of this stream. Do comment me from which place you were watching, and second thing, write down your name and use prefix doctor, DR, or use prefix engineer if you are NEET student or JEE student. So two things you have to write down. One, your name with prefix doctor or engineer, and second, from which place you have watched this session. And third, do you really like today's session or not? And I'm really very sorry that I can't take this session yesterday because I was down with fever and body ache. Still I am having fever, still I am having body ache, but this session was for you all because I love my each and every student and I'm always there for my students there. So I will be sharing this PDF on Unacademy Telegram channel, and let's meet day after tomorrow in the another marathon session which will be of class 12. But I will be waiting for your comment, not here, but in I mean to say comment section after I end this session. So thank you and God bless you all.